we start? Thank you. So, good morning, everyone. Welcome to the third day of the conference. So we are in the equator of the conference, and it can only get better, especially after yesterday's party. I hope you could enjoy. I was enjoying it a lot. Yeah? Thank you, Ramon. I don't know if Tim is here. It was a great experience. Thank you. So today we are on the first session of Advanced Insert Theory. Remember, tomorrow we will have the second one. And we will have very interesting presentations, 5 presentations, and the topic is basically in all of them, these non-closure phases or fading signal. So we are all looking forward to these new advances in this topic. And I remind you, please think on these seed questions or these recommendations on ESER, because I guess we will have to gather a few of them concerning this particular topic. So I would like to introduce the first speaker. It will be Jacob Matthew Connolly from the University of Leeds. And the title is A Comparative Study of Phase Bias in C-band and L-band INSA.
Hi everybody, I'm Jacob. I'm a PhD student here in Leeds. Yeah, I'd like to present some results on phase bias, comparing C-band and L-band. So I think there's been some talks already on the subject, and there's some more after this. Okay. The phase bias is a sort of nuisance signal that we see in time series INSAR that mostly affects multi-look short-term interferograms. So interferograms where we want to use short temporal baseline to improve coherence, and multi-look to also improve coherence. And sort of the main way we're sort of diagnosing this problem is by looking at the loop closure. So you're probably mostly familiar with this by now, but you can create a closed loop of phase by 2 or more smaller interferograms and a longer interferogram spanning the same timescale. And if these interferograms are multi-looked, then the loop closure can be non-zero. And these sort of small contributions that we see in these small interferograms can contribute to bias deformation. So this is a figure from Ansari et al. In 2021, and you can see on the panel on the right, left, it's quite heavily biased, or at least it looks like there's deformation velocity downwards. And this method on the left is using short temporal baselines. The method on the right is a PS processing scheme that's less affected by phase bias. It uses generally longer interferograms. You can see that the majority of the deformation doesn't actually exist in this interferogram. So hopefully that convinces you that phase bias is an interesting problem to study if you're not already convinced. But the main conclusion from the study is that it varies by line cover. So sort of pointed towards the idea that variations in vegetation and soil moisture could be causing this, and causing some sort of signal that we see inside time series. So that leads us on to motivation for this talk in my study, to try and understand a bit more about the mechanisms that cause phase bias. And if we know that it varies by land cover and the sort of types of vegetation that we see on the ground, then it sort of tells us that there's some mechanic happening. And if we look at different wavelengths, then hopefully we can see something there. So I'm mainly focusing on trying to compare the bias in L-band and C-band. Specifically, I'm looking at phase closure as a way to sort of diagnose the problem. And then ultimately, what can we learn about the underlying physical mechanisms from this data set? So for C-band, generally, they'll be scattered by the top of a canopy and some of the sort of smaller branches at the top. And L-band, it can penetrate a bit further, hitting some of the larger branches in the tree trunks themselves. So you get a different sort of scattering depending on the vegetation. So I'll be focusing on how how and where the phase disclosure presents itself at L-band, comparing that to C-band. For our study region, we're looking at Milan in northern Italy and its surroundings. So we're mainly dictated by where L-band data was available. So we're using data from ALOS2. As you know, ALOS2 doesn't have complete coverage over the world that's sort of freely available. This is data was gained through a research agreement. We have almost a complete time series for our time period, so September 2020 to 2021. So it's generally 14-day repeat with some larger gaps in there as well. And the other advantage of using this area is that we can take advantage of the C-band interferograms from LIXAR. So looking at land cover, you can see that there's a large urban area where Milan is, and you also have a large amount of cropland and grassland across the middle band. And along the rivers, you can see quite high vegetation, or at least tree cover. And so those are the main areas I'm focusing on. So the middle cropland area, the tree cover, and then the urban area towards the north. So we can first construct some C-band closure loops. So I'm using 4 6-day interferograms and a 24-day interferogram. The LIXAR processing system uses 5x20 multi-looking. And so if we sum the 6-day interferograms and subtract from the 24-day, we get our closure phase. You can already see some correlation with where certain areas of land cover are. So across the middle band where the crops were, you can see generally non-zero. Where the city is, it's generally 0. And we can also sum this for the whole time series. So if we do lots of connected loops across our study period, you can sort of see the phase bias, or just the loop misclosure build up. Comparing it to land cover, you can see where the city is. It's generally fairly flat in the map. So this is down to generally being quite coherent. Across the cropland and grassland, it's fairly non-zero. We can separate that out by land cover a bit further. So if we do the whole time series and do the cumulative mean closure phase for each class across the whole period, and these results are in line with other studies where we find that grassland and cropland are contributing the most to the phase misclosure, with tree cover and then urban being below that. You might notice that urban is still fairly high in comparison. I think this is because there's some of the sort of tree cover vegetation class mixed in with the urban class, particularly in the city area where we have pockets of vegetation that are misclassified when we downsample the land cover map to the interferogram resolution map. So it's something that I need to look into a bit further, but I think in general it's what we expect. So we can also look at L-band now. So for L-band I'm using sort of triplet phases, triplet loops. So in this one it's 2 14-day interferograms and a 28-day interferogram in June, July 2021. You can see, again, it's a similar story. We have a fairly flat closure phase, so close to 0 for where the city is, and then around the city, and then along the river, you can sort of make out more of a red tinge there. So to sort of visualize this a bit better, we can downsample the closure phase a bit more to make it a bit easier to see. You can see where the city is, again, fairly flat. But I think the most important and sort of interesting result is along the river where we have the more dense vegetation. We're getting more non-zero closure phase. So if you remember, this is quite different from C-band where it was mostly across the cropland and grassland, whereas here it's across the sort of heavier vegetation. So we can separate this out a bit further for L-band and C-band. You can see that tree cover actually comes up on top. And so sort of points towards the idea that the phase misclosure might be being caused by volume scattering within the vegetation. So for L-band, you're going to have more volume scattering across sort of larger branches and tree trunks and things like that. Whereas C-band, you'll have more volume scattering for sort of smaller trees, cropland, and sort of lower-lying vegetation. So those are the main results so far in the study. So fairly brief, but I think it's quite interesting conclusions so far. And there's definitely more work to be done. Essentially, as expected, cropland and grassland exhibit the highest cumulative phase closure. Yeah, for C-band, and then for L-band, it seems to be more on the forested areas with the thicker vegetation. So the main conclusion is sort of that the volume scattering might be the main mechanism that's causing this non-closure frown loops. Obviously, going forwards, I think more needs to be done, particularly looking at different vegetation types. So drier or wetter climates and different levels of sort of trees and sort of shrubs and things like that. Just to acknowledge that the LS2 data, as I said, obtained through a research agreement, and say thanks to Milan and Jesse for posting Elixir and sort of discussion on phase bias. I've also got a poster, so if you'd like to discuss my poster, it's on change detection or this work more, I'll be there tomorrow afternoon. Yeah, poster number 50. Thanks.
So it seems we have quite a bit of time for questions, so let's just open it to the audience. I don't think we should start too early with the next one, so we have 5 minutes.
Okay, I just had a question. Why is the closure phase always seem to be have the same sign? And what's the origin of that?
Yeah, it's a good question. I think so I think there's always sort of bias towards your shorter interferograms. So because you have you're creating loops of your short interferograms and you're minusing your longer interferograms, then that sort of phase inconsistency is usually always one way. In terms of the actual physical mechanisms, I'm not entirely sure why that would be the case.
I was wondering, for a fair comparison between the C-band and L-band, if you would have used 12 days for C-band as well, because you use 6 days. So these things are very time sensitive.
Yeah.
That's one comment. And then, yeah, obviously the results are not intuitive. I would have expected more closure for the L-band, but yeah, maybe it's because of the time. And to answer your question, Charlie, I think you have to wait for UGS presentation. It's not always the same sign, actually. Yeah, it's not the same sign.
Thank you. I just saw your graphs roughly, and when I recalculate the radians to centimeters, I get roughly similar values. Am I right?
Sorry, can you repeat the question?
I remember that in your graphs it was 0.6 radians for L-band and 3.5 radians for C-band. Just roughly recalculating, it's like 18 centimeters, both of them.
Yeah.
So it's similar in radians, similar in
Oh,
centimeters,
okay, I see, yeah.
but heavily different in radians.
So, yeah, are you saying it's similar sort of distance
Yeah.
for both C-band and L-band?
So if we measure it in centimeters, we can quantify it more general.
Yeah.
Thank you.
In your study, you relate the cumulative closure phase to the land use. For the understanding, I would suggest that you also relate it directly to the coherence. In addition, I mean, it's not, you should do it for the land use, but also to look at how it relates to the coherence. Also, with the different frequencies, that may also give some indications how you can model it or understand it, I think.
Okay, thanks.
Hi, how sensitive is the phase closure bias to the level of multi-looking you do?
So it can increase with more multi-looking. So I think it varies on the sort of type of terrain you have, particularly if it's very vegetated, then you'll probably have more of a bias, more multi-looking you have. I think the main sort of factor is sort of the length of the interferograms. So as I mentioned, it's quite sort of time sensitive. So generally, the shorter the interferogram, that has more of an effect for sort of the bias you can see.
Okay, just could you help me to just go back to the slide 19? So just one slide back here. Okay, so I saw that you observed the phase. So the closure phase is not zero even in the urban class. So what is the reason behind for this one? Because basically that's a winter closure phase. We have problem with the water content, something like volumetric target. So in the urban cluster, basically why we don't have it should be very close to zero. But why I saw it's not non-zero now, and what exactly the reason behind, the physics behind, what is the cause?
So I believe it's the urban class obviously doesn't cover completely urban areas. In between, there'll be sort of vegetation within that class, and obviously variations in sort of weather and sort of moisture levels within that will cause different levels of variation in vegetation across our time. So I think there's still obviously a bias within that class, but in general it's less because of the sort of more stable scatterers versus vegetation.
It means when you calculate, maybe there is some vegetation inside that window, even in the urban, so maybe that's missed classification.
Yeah.
Okay. Thank you.
Yeah. So I think the sort of main issue with that is it's quite a high resolution Vancouver map, but when I downsample it to resolution of interferograms, some of those classes get mixed up, so it's not completely accurate.
Okay, I think we have to move on. The next speaker is Yasser Maksudi from University of Leeds, and the title, which I think sounds like a good seed question, towards universally applicable phase bias correction for short-term multi-looked interferograms, challenges and progress. Please.
All right, good morning, everyone. So in this presentation, I'm going to give you an update over our recently funded ESA project, which aims at developing a universally applicable phase bias correction for short-term multi-look interferograms. So let's make the introduction brief. So it has been shown in several studies that the velocity, which is estimated by the multi-looked short-term interferograms reveals a systematic signal, which is also called as the fading signal, which actually cannot be explained by any of genuine deformation or any atmospheric or topographic signal. And we previously developed an empirical mitigation strategy for the phase bias correction. And as a summary of the method, we use the observations are basically the loop closures, as you see on the left side of these equations, delta phi, and the unknown terms are the bias terms, which are shown by these delta values in these equations. So this is basically an undetermined system of equations. So in order to solve this rank deficient system, basically what we introduce in as an assumption that the bias is an interferogram is linearly related to the sum of the biases in the shorter interferograms which span the same time. So what this assumption means, basically, it means that although the bias is changing in time, then the ratio of the 12-day bias and the 6-day bias, and also the 18-day bias and the 6-day bias remains constant. And so this was the main assumption that we had here. So this ended up to this new set of equations, as you can see at the bottom. And then this, in this equation, A1 and A2 are the calibration factors, as I mentioned, which can be estimated using the method that I fully described in the paper, in the published paper below. And this can be easily solved by any least square inversion, and then after estimating the delta phi, the interferograms can be corrected accordingly. So we compared the method with in a highly vegetated region in Turkey, and as you can see in the left scatter plot, we have the original velocities in the x-axis and the phase linking approach in the y-axis, and it is quite clear that the velocities are biased in the first plot. But in the right scatter plot, as you see, we have our corrected estimated velocity versus the phase linking velocities, and again the distribution shows that we had a better match between these two after correcting the interferograms. So one of the main benefits of the algorithm is that our mitigation strategy is immune to long-term coherence loss, because it is basically only dependent on the short-term interferograms in the system of equation for estimating the correction terms. And also, unlike the phase linking approaches, as our proposed method only requires, as I said, the short-term interferograms. It doesn't rely on the availability of the long-term interferograms and long-term coherence for the phase linking approaches. But anyway, the universality of the method needs to be further investigated. So today, basically, as a part of our ESOP project, we recently finished the phase bias characterization stage. And so what I'm going to explain today is actually to use one of the main symptoms of the phase bias, which is the closure phase, non-closure phase. So what we are going to show you is the loop closure time series in different regions, the loop closures in ascending and descending, the effect of filtering and multi-looking, the land cover dependency of the loop closure, and also the polarization dependency, and finally, just making some correlation with some environmental proxies. So these are the selected frames that we use in this study. We selected one ascending and descending frame in Turkey. In Turkey, the average rainfall is about 300 millimeter per year. It is vegetated. In some areas, we have forest. And also, we have one frame in Azores Island, which is densely vegetated with a very dense forest. The average rainfall is about 900 millimeter per year. And also another frame in Italy, which covers the Campi Flegrei volcano. The average rainfall is about 500 millimeter per year. It is also, have a pretty dense vegetation, but not as dense as Azores. And finally, two frames in Tian Shan, which have an average rainfall of 250. So in Turkey, Campi Flegrei, Azores, the acquisitions are 6 days, and in Tian Shan, it is 12 days. So in the first experiment, I'm going to show you how the time series of the loop closures look like. So the x-axis is time, the y-axis are the mean values of the loop closure. So basically what you can see here, this is in Turkey. And so each point in this plot shows the mean value of the loop closures in a single loop, which is obtained using an 18-day interferogram and the corresponding 6-day interferograms. So you can see how they change in time. And so if you look at the peak values in this plot, you can see that the peak values always happen sometimes in early June. So this is the peak value of the loop closures that we have got with the value of around minus 0.2 radian. And so we did the same for 3 other regions. The top left is in Italy. And again, you can see the same seasonal pattern that we have. But this time, the location of the peak value is a bit different compared to Turkey. And this time, we have the peak values in May, which basically is due to the different precipitations, different vegetation growth that we have in Italy compared to Turkey. In Tian Shan, the story was a bit different. And the peak value was about minus 0.1 radian, which is much more smaller comparing to Turkey and Italy. And also the peak values occurred sometimes in March. So every year, this is repeated every year, the same pattern. And finally, in Azores, we had the largest values of the loop closures with a peak value of about minus 0.4 radian. And it is more complex comparing to the others. We cannot derive a seasonal pattern. We cannot see a seasonal pattern in Azores. And this, I mean, in this region, we have the vegetation throughout the year. And so it is not, I mean, we do not, because of that, we cannot see such a seasonal pattern here in Azores. And so, I mean, this was not only about the 18 and 6-day interferogram. You can see the same pattern in the other loop closures as well. This is, for example, the 12 and 6-day closure phase, exactly the same pattern, the same location for the peak of the loop closures, but basically different values, which is expected. And if you want to see the cumulative sum of these loop closures in different regions, you will come up to this plot. The bottom plot is the one that we obtained from Azores, and the cumulative rate shows that it has a very fast rate of change in Azores. And then we have the plot for Italy, and the next plots are for Turkey, and finally the top one is for Tian Shan, and that's where we have the least concern about the phase bias. So next, I'm going to compare the ascending and descending. So for this purpose, I selected one ascending and descending frame in Turkey, and you can plot. I plotted them in the first one, as you see in the top. And in Turkey, actually, the ascending and descending were acquired in the same day. There was not any difference in that, but the timing were basically different. And the blue one are the mean value of the loop closure for ascending, and the orange one are for descending. And so this is for Turkey. For the bottom plot is for Tian Shan. This is 12-day acquisition, and so again you can see that we can see a good match between the descending and ascending, and this is also quite clear from the scatter plots on the right. And so in this way, we wanted to see how the phase bias is dependent to the look direction. And so again, if we look at the cumulative phases, especially for the ascending and descending ones, the top ones are for Tian Shan. As you see in the cumulative plots, they are completely matched with each other. They are overlapping each other, and pretty much the same trend in Turkey, the ascending and descending frames, which are shown by blue and orange. So this suggests that the phase bias is a lesser concern in the estimation of the east-west velocities, but takes on greater importance when you are estimating the vertical velocities. Then the effect of filtering. So it is a very common practice to reduce the phase noise using filtering. And in Comet Lixar system, we generate both the filtered and unfiltered interferograms, as you can see in the bottom. The unfiltered interferograms are simply multi-looped by factors of 4 and 20, but no filtering were applied, whereas in filtered interferograms, we have an additional Goldstein filter applied over the interferogram. And it is important to know how much this filtering will increase the closure rate. So this plot shows again the same time series of loop closures. The blue one are the unfiltered interferograms in time. And so the Goldstein filters are by orange. And we also apply the boxcar windows of size 10 and 20, which are shown by green and red in this plot. And as you can see, there's a significant increase after applying any type of filtering to the already multi-looked data that we have here. And we did the same in Turkey and Tian Shan, and the same pattern, but the main difference is that the values of increase in the loop closures is smaller in Turkey and particularly in Tian Shan. And this basically is due to because they are less vegetated, the precipitation is smaller, so the effect of filtering is also smaller. So we cannot say generally that the filtering has the same effect everywhere. And also maybe in this scatter plot you can see the effect of filtering in a more clear way. So in Italy, Turkey, and Tian Shan, and also I plotted the slope of the regression line, as you see here, and the highest value was for Italy, and then the lowest slope of the regression belongs to Tian Shan. Next, I wanted to show the land cover dependency of the loop closure time series. But before I go to the loop closure time series, it is good to have a look at the cumulative loop closures in Tian Shan and Italy, which are plotted on the left panels, and compare them with the cumulative loop closures, which are to compare them with the land covers in the right. And so the land covers are derived from the Copernicus Global Land Cover Service. And so here I plotted the croplands with yellow in the right side. So, and if you if you compare the cumulative loop closures, which are shown in the red in the left panel, you can see that there is a correlation between the croplands and the loop closures, both in Tian Shan and also in Italy. The same pattern. In Italy, you can see the concentration of the croplands are in the coastal regions. We can see the same pattern on the cumulative loop closures. And this is, in this plot, you can see the mean value of loop closures in different land covers. And so basically, as a general result, the croplands has the highest. The croplands and shrubs had the highest values of the loop closures. And the urban regions, which are plotted in purple in this plot, it's barely visible, but they has the lowest values of the loop closures. And also it is interesting to see that how the forest regions and the croplands regions are comparing with each other. And on the right plot, you can see that this, you can see the forest on the x-axis and the cropland on the y-axis. And as it is clear from the scatter plot, both the forest and the croplands has a seasonal pattern in the loop closures, but there is a systematic difference, a systematic offset between the forest and, let's say, land covers. The croplands. And if we focus on the different forest species, different forest classes in Italy, we'll come up to this plot. And so again, as you can see here, the highest values of the loop closures belong to the open forest, and the lowest values belong to the closed forest. And so the open forest has, less canopy cover, and the signal penetration is higher. So that's ended up to larger values of the loop closures in the open forest. And so pretty much the same results in Azores, although in Azores the differences are more pronounced comparing to what we saw in Turkey, especially when we compare different forest classes. You can see they are quite different from each other in Azores. And again, the open forest has the largest, the closed forest has the smallest. And so basically, although this kind of loop closures will result to some biases in the velocities, but on the other hand, this could be used as a kind of loop closure signatures for discriminating different maybe forest species or different, or in general land cover classification, which it needs further investigation, by the way. And next, the loop closure time series in different polarization. And so in the right panels, you can see a single loop closure in VV and VH. The first one is loop closure in VV, and the same loop which is plotted in VH. And the histogram shows that the values of the loop closures significantly increase in the VH comparing to VV. In VH, we have different scattering mechanisms comparing to VV, and also the coherence is basically lower in VH comparing to VV. And if I want to plot this in the whole time series, then I will come up to this plot. So in this plot, I'm comparing the VV and VH in a frame in Turkey. The orange one is the VH mean loop closure, and the blue one are the VV ones. And so there is a slight difference in each of the mean values of, and I mean, this maybe experiment could be repeated in different land covers to see how they change in different land covers. And also the scatter plots show the same thing, a slightly increase in the loop closures in the VH. And also finally, I wanted to show you how the loop closure time series can be compared with some vegetation indices. And because as we saw earlier, there seems to be a good correlation with the vegetation indices as well as the vegetation growth as well as the loop closures. So I selected the NDVI, which is a widely used metric for quantifying the health and density of vegetation, and I obtained from the Copernicus Global Land Service. It is every 10-day data from the spot vegetation collection. I plotted them in Turkey and Italy. So we can see a match in the increase and decrease of the NDVI and the loop closures, although in some cases we see a lag between the peak of the NDVI versus the, yeah, sure, thanks. And the peak value of the NDVI and the mean loop closures, which is basically because of the NDVI is a measure of the vegetation greenness rather than the vegetation growth. So maybe selecting some other proxies for the vegetation we can find a better match with the loop closures. And we have the same pattern in the soil water index as I showed by the SWI. And again, I obtained them from the Global Land Service of Copernicus, and they are obtained from the scatterometer measurements. And again, in some cases there are some differences, which is basically these are the mean values, and the soil water index maybe is not reliable, it's not meaningful when we have a dense cover of vegetation. So maybe in the next part I need to check this in different land covers. So as some take-home messages here, the loop closure time series has a seasonal trend, as you see, and it is different in different regions. And also in ascending and descending, there was not a significant change of loop closures in ascending and descending. In the effect of filtering or any other box called filtering can significantly increase the closure phases. And I showed the land cover dependency and also the polarization dependency. And I compared with some environmental proxies. So in the last slide, just for our future directions in this project, so we just finished the phase-wise characterization, which you can see here, but the next step is algorithm consolidation, which we need to check the universality of the algorithm and then implement the processor and do the scientific validation using the phase linking approaches. And finally, we will do a large scale demonstration by using the Comet Lixar system before and after running the correction. So the final output would be an open source package which take any stack of interferograms and provide the correction. So that concludes my presentation, and I'm happy to take any suggestions, questions, or comments. Thank you.
Thank you. There is room for one short question.
Hi, thank you for the presentation, very interesting. I was wondering how does this loop disclosure is influenced with the multi-looking? So if you have different multi-lookings, like 30 meters or 100 meters of pixel resolution.
That's a good question. Actually, what we compared is, because the data that we had were already multi-looked by factors of 20 and 4. So what we did, we applied some boxcar filtering, which pretty much the same as multi-looking, and you saw that they significantly increase the loop closures in time, but with different values in different regions. But it is a good practice to check this with maybe the full resolution originally, before any multi-looking, and then check these with different multi-looking factors.
Thank you, Yasser. So I introduce the next speaker. It's Elizabeth Wick from the Stanford University. And we continue now with the topic as a proxy in this case for soil moisture. So the title is INSAR Closure Phase Time Series for Soil Moisture Measurement.
Hello, I'm Elizabeth Wigg, a PhD student at Stanford, and today I'll be talking about a way to measure soil moisture from INSAR Closure Phase Time Series. Now, the reason we might be interested in soil moisture data from INSAR is that SAR can deliver measurements at field scale, enabling higher resolution than passive radiometric measurements and more complete coverage than in situ measurements. So the goal of this presentation is to show one way that we can relate closure phase time series to soil moisture. We'll show how we do this with a simple model and with some real data. We use a model for the dielectric constant of soil at different moisture levels based on Salar and Ulaby. Changing soil moisture, such as the sequence shown on the right of rapid rainfall events and slow drying, changes the real and imaginary parts of the dielectric constant. We'll show that these changes can affect the closure phase. We start by defining closure phase as the phase that comes from a circular combination of 3 interferograms taken from 3 INSAR image acquisitions. Combining the phases from interferograms 1, 2, 2, 3, and 3, 1 produces a closure phase. In the case of ground deformation, shown on the left, the closure phase is always 0 as all phase components are canceled out in the loop. So the arrows going down sum to the same length as the arrow going up. This is also the case for any individual pixel in an interferogram that has not been multi-looked. Like deformation, atmospheric noise and other single-layer phenomena do not produce a closure phase. However, when multiple layers of scatterers are changing independently, the signals from the layers interfere with one another, and the interference signal varies in time and from pixel to pixel within the multi-look window. In the multi-looked image, the closure phase arises from scattering interaction of multiple layers, such as changing soil moisture below the ground surface and changing vegetation canopy above it. Therefore, non-zero closure phase arises from multi-looked, multi-layer materials that are changing over time. We create a scattering model to demonstrate how this can happen. We start with a simple 2-layer model. Here the layers represent the ground surface and subsurface for soil moisture. We derive the received echo, normalizing the phase and path delay to the return from the ground surface. The received echo has surface term S sub S and a depth term with amplitude S sub D, whose phase relative to the surface term varies with the dielectric constant. After making some simplifying changes to our math notation for the depth of scatterers and the dielectric constant, we can calculate the return from 2 such echoes, where the only difference between them is a changed dielectric constant of the medium, which results from changed soil moisture. We interfere these echoes to generate an interferogram. To model multi-looking, we take the expected value of the interferogram, assuming that we are using enough looks for a stable statistical average. This has an added benefit of simplifying the modeled interferogram, as many of the cross terms go to 0. To find the expected value of our modeled multi-looked interferogram, all we need is the radar cross-section and dielectric constant of the medium. We can extend this by calculating the closure phase across 3 interferograms where the dielectric constant changes in all acquisitions. While this equation for the triplet signal is very long, it is also quite simple. Again, it only depends on the radar cross-section and the dielectric constant in the medium. The closure phase is simply the phase of this triplet signal. We can explore the properties of the closure phase in this model by calculating a Taylor expansion of the exponential terms here. When we compute a Taylor series expansion of each of the exponentials in the model, we find that the linear portion, that is the first two terms of the expansion, produces an entirely real result, meaning that there is no closure phase produced. Thus, it is entirely the nonlinear elements of this model that have an imaginary component and can produce a non-zero closure phase. We see the result in this figure. For our soil moisture time sequence on the left, the first order linear approximation has zero closure phase at all points, seen in red on the right. While the second order approximation accurately matches the exponential version for small x. We can also see that the nonlinearity means that large derivatives or rapid changes in soil moisture have an outsized impact on the closure phase. The sharp increases in soil moisture here produce large spikes in closure phase, while the slower decays produce significantly smaller closure phases. The next step we take in our model is to calculate a cumulative sum of the closure phase. Why would we want to cumulatively sum closure phase? An analogy can be found in interferometric phase. Each interferogram shows velocity over a time interval, so we cumulatively sum the velocities to find displacement. Analogously, time-varying dielectric properties of Earth's surface produce a non-zero closure phase. Because the closure phase relates to the soil moisture change over a time interval, we cumulatively sum closure phase over time to derive a time series of soil moisture. On the left, we see the closure phase produced by our model for this time series of soil moisture, now for depth x at centimeter scale. You can see it has negative spikes, unlike the original soil moisture signal, and the peaks are not aligned in time with our peaks in soil moisture. On the right, we calculate a cumulative sum of the closure phase, and we notice a trend, as some of the previous presenters have also noticed. The nonlinear response of the model to changes in dielectric constant means that if we have a sequence of dielectric constant changes that are rapid in one direction and slower in the other, such as rainfall events and slow drying, the closure phase will respond much more strongly to the large change than to the sequence of smaller changes. Over time, this can produce an apparent systematic bias where the positive closure phases from rapid increases can dominate over the smaller negative closure phases from slower decreases, or vice versa. Closure phase is most responsive to large changes in dielectric constant across all three interferograms in the triplet. When we cumulatively sum the closure phase, this bias leads to a trend. Assuming a consistent asymmetry between the time spent wetting and drying, we fit and subtract a line to detrend the cumulative closure phase. So once we have this solid line on the right and subtract the dotted line fit, what we get is shown in red here. I'm calling this the detrended cumulative closure phase, and we can see in blue the soil moisture time series for comparison. We've averaged the soil moisture values over the 3 days included in the closure phase triplet. And it is evident from this figure that the detrended cumulative closure phase is anti-correlated to the soil moisture according to our model. Now let's see if we can use this relationship to estimate soil moisture. On the left, we scatter the detrended cumulative closure phase against the soil moisture. We find that they have a correlation coefficient of -0.87. We find a consistent trend line in black, and we use this trend line to generate an estimate for the soil moisture. The estimate is shown on the right and appears to track the soil moisture fairly closely. Now let's see how this can look in real data. To generate the closure phase, we use a Sentinel-1 INSAR swath in central Oklahoma, US, multi-look to a pixel size a bit smaller than a kilometer. We validate with 37 in situ soil moisture probes taking daily measurements at 5 centimeter depth. We look at data over 3 years from 2018 to 2021 using only adjacent scenes for triplets, so we have short temporal baselines. When we calculate the closure phase, the signals from the atmosphere and deformation are canceled out around the triplet, leaving only the closure phase signal. We create a time series of sequential closure phase triplets and calculate the cumulative sum over the time series. As in our model, we find that a cumulative sum of the closure phase results in a trend at nearly all sites, indicating that all sites likely have some unevenness in the rate of wetting versus drying. We once again fit a line to the trend and then remove the trend to find our detrended cumulative closure phase. I'll be demonstrating the process at one site in Seminole, Oklahoma. Without cumulatively summing and detrending the closure phase, it does not seem to correspond particularly to the soil moisture, as we can see on the left. But when we see our detrended cumulative closure phase derived from INSAR on the right and compare it to the soil moisture, we see a pretty clear anti-correlation between the two. This also seems to follow the model. So next, we'll try scattering detrended cumulative closure phase against soil moisture. The correlation between the two is negative 0.77 at this location, and we can again see a trend in these data points. We again use this correlation to create a fit line in black and then estimate the soil moisture values. So when we do that at this site, the prediction appears to track pretty closely between our measured and estimated soil moisture. It doesn't capture all the variation in soil moisture, but it does a decent job here. Now let's compare some other sites in our swath. Seminole is an example of a very clear linear relationship between detrended cumulative closure phase and soil moisture, but the Lahoma site has a weaker relationship, and the Hinton site exhibits practically no relationship at all. When we use these fit lines to estimate soil moisture, we see that while the estimate at Seminole tracks the soil moisture closely, Lahoma's does less well, capturing the soil moisture in some places, but overestimating periods of low soil moisture. At the Hinton site, the estimate fails to capture the variation in soil moisture at all. We might wonder whether there's any common way to estimate soil moisture at all sites. We plot the fit lines between the detrended cumulative closure phase and the soil moisture. Then we calculate the average of all the well-performing fit lines and use this fit line to estimate soil moisture from closure phase at all sites. We find that whether we use every site's individual best fit or the universal fit line, we find equally accurate results. This is promising as it suggests that from site to site, the detrended cumulative closure phase behaves similarly. So it may be possible to come up with a universal rule describing closure phase from soil moisture across locations, at least within a region. We might wonder about any relationship to terrain. And so we test that here. We find that the eastern side of our swath tends to have better estimates than the western side, and that pasture land tends to produce better estimates than grassland, which has better estimates for soil moisture than cropland. This may be because uneven irrigation patterns can complicate soil moisture signals in agricultural areas, and it likely also has a component related to vegetation growth or change in vegetation moisture, which results in greater moisture changes above the ground and therefore can have a stronger effect on the closure phase signal. So in conclusion, we've shown with our model that non-zero closure phase can result from interference of a surface and scatterers at depth. The surface and scatterers could include soil moisture, a vegetation canopy, snow cover, or other factors. I think many of the presenters in this session have discussed other possibilities, and Yujiya, who is presenting in 2 presentations, has a paper that differently frames the mechanisms leading to this interference. Here we've shown that varying soil moisture with time leads to non-zero closure phase. An asymmetric soil moisture time series with different rates of increase and decrease can produce a bias that leads to a trend in the cumulative closure phase because of the nonlinear response of closure phase to dielectric changes. Detrended cumulative closure phase agrees with in situ soil moisture to a varying degree, and the level of agreement seems to be correlated with terrain type and vegetation density. This method could yield soil moisture at finer resolution than is possible using radiometric remote sensing, opening up new possibilities for high-resolution sensing of soil moisture. Lastly, I want to mention that we have a preprint out covering the material in this talk that you can find using the QR code or going to bit.ly/wigphase. Thank you for your time, and I'm happy to take any questions.
Thank you, Elizabeth. So we have time for a couple of questions. Anyone?
So do I understand correctly that the soil moisture you estimate is not for single dates, but is the average soil moisture for the 3 dates with which you calculate the closure phase?
Can you repeat the question?
Is the soil moisture that you estimate the soil moisture for single dates?
Oh, it's averaged. Yeah, it's averaged across the dates in the closure phase.
Across the 3 dates with which you calculate the closure phase?
Yeah, it's actually what I do here in the real data is I average across the whole time period included in the triplet, just because in situ soil moisture sensors have some variation. So I was hoping that by including more data and averaging over the whole time period in the closure phase, we'd get a bit more accuracy with the in situ data.
So you cannot separate single dates, but you always have 3 dates together.
Yeah, with this method, you couldn't separate single dates.
Thank you for the presentation. Very nice presentation it was. Just one question about soil moisture measurement you're talking about. Is it for the surface or at the depth?
So with Sentinel, we're likely not penetrating very deeply into the soil, especially when it's wet. So we are measuring roughly surface soil moisture. The in situ sensors that we're comparing to are at 5 centimeter depth, which was about as shallow as I could find for comparison.
And have you looked at the type of the soil that you have, or just you did comparisons between in situ and in-soil measurements, just regardless of what type of the soil you have?
What soil type?
Yeah, you didn't consider, right?
No, we didn't incorporate soil type.
So you can you say that if you had runoff at some locations, it was just all based on whatever you had in soil?
Yeah, and I think that the soil moisture would have a comparatively large effect on the soil moisture dielectric constant compared to the soil type. And also, since we're measuring a change, soil moisture isn't typically soil type isn't typically changing at the same location. And what we're measuring is changes. What is changing is soil moisture.
Thank you.
I'm just wondering, your model, how dependent do you think it is on the vertical gradient of the soil moisture? So if you have a particular kind of average moisture within your penetrated volume, do you think it's a significant factor whether there's like a drying trend where it's there's a vertical gradient in the moisture versus a kind of basically a homogeneous difference between the dates?
Yeah, so are you saying from day to day?
Yeah, like if you had, if it was drying on one particular day, so you have a vertical gradient in the moisture, and then another day when it wasn't, so it was homogeneous, then your difference would have a vertical gradient in it. And I'm just wondering if your model considers that, or if you think it would be a factor in the phase.
Yeah, our model doesn't explicitly consider that right now. We're kind of assuming the soil is a homogeneous volume. And again, because the C-band data doesn't penetrate very far, it's kind of a small volume. It's possible there's some dependence on the the gradient in the soil moisture, honestly, I would guess that that would have a smaller effect than whatever vegetation is over the top of the soil. Like, I think that our signal of the soil moisture is more likely to be inaccurate due to vegetation than due to not modeling the gradient of moisture in the soil correctly.
Okay, thanks.
So thank you. That's a very good presentation. The real application, so when you deliver the some moisture for the whole map, so for the bad soil is okay, it makes sense that it's some moisture. But when it comes to vegetation targets like forest, so what exactly the phenomena you observe here? It's not exactly the some moisture, or maybe it can be vegetation growing something to one. What are your comments on that one?
Yeah, I think that absolutely over a place like the forest, and kind of as Yasser showed in his presentation, you're likely to be measuring vegetation moisture changes or vegetation growth changes. And so I am looking to apply this over the forest soon and see which signals are more dominant, whether it's a vegetation signal or a soil moisture signal. And it's also tricky because the vegetation and the soil are correlated, right? If you have more moist soil, you're likely to have more moisture in the vegetation, perhaps as it is able to grow more with more water availability. So definitely an interesting question.
Okay, so we move on to the next speaker, which is incidentally Din. And his talk is Efficient Earth Surface Monitoring with Thomas R. from PSDS to ComSAR and the vital role of phase linking technique. Please.
Okay, good morning everyone. I am Den Ho Tong Minh from Israel, so I am a research scientist over there. So we're waiting a little bit for, okay, slides coming now. It's coming out. It's coming. Okay, thank you. So, so in the previous talk, we're talking a lot about the closer phase, and then how we deal in, how we characterize in two perspectives. So the first is about how we can interpret the physics behind that closer phase, try to use that information, try to use that signal to exploit for some monster, for example. And another approach is we dealing with that problem based on statistical methods. So basically that when we go to a certain application like deformation, we don't want certain closer phase here. We want it should be close to zero, or in the perfect way it should be zero, even when we're dealing with multi-looking and so on. So in this talk I discussed a little bit about that one. So a little bit few words about the context. So we, as you know, that sentence one is very good, but also is challenging because there is a lot of data available. So are we ready to dealing with that data in entire big data? So usually that's in the literature. There is a very good proposal about a Swenso estimator. So this is a very good performance, very good algorithm, and very good scheme in terms of the distributed scatterer. So what about when we're dealing with other stable target like persistent scatterer? So our objective is we just a little bit discussion about how phase linking working, because you heard a lot in the previous talk that with the phase linking, there is usually that's the way to verification, a way to validation, or something with the other processing in time of SPAT, for example. And then I will introduce about algorithm, what we call the ComSAR. So basically that's algorithm to combine the BS and the DS together in the framework of the phase linking. And then I a little bit introduce for the TOMOSA. That is my one to implement that algorithm, and it's open source recently. So So in the last 20 years, so we have a lot of algorithms to dealing with the star data. So what exactly why we have many algorithms? Because with star data, we have a lot of degradation because as a function of time, every change in atmospheric temperature degradation. So the main formula for that problem is we need a long time series data. And based on that time series data, we are able to find a certain persistence with the good coherence, something like persistent scatterer or a good distributed scatterer. So we have some methods, something like, okay, so BS or SPAS, or if we combine together, we can gain more information, and maybe it's the best performance with BS and DS methods combined together. And in the frameworks of the DS, we are very good solution for the bit inside data. And recently I proposed to combine with BS, or what we call CAMSA. So just a little bit for visualization, what exactly it is. So so I refer to the image on the top on your left. So basically with the BS, we just need one reference image. You will have a certain network like this one, like a star, like Big Bang Bump, and you see that's that figure. So why we just need one reference in that BS? Because BS just one point. So if we just take one reference, it is single loop. It is single loop. So if you take the closure phase on way 0, so there is not necessary to combine a certain network in just a BS point. So when we go to the DS, it should be have to do some kind to dealing with the decoration. So with the distributed scatter, they're dealing with decoration based on a certain kind of minimize the decoration in terms of time, in terms of geometry. So that's why they will have a certain network like this one. And recently that, not really recently, that's about 15 years ago, so people try to come up why we had to develop a certain network and try to find which is the network with the best. So why not do everything together and put everything together? And when we put everything together here, and that the key problem is it's a lot of work have to do, a lot of equations have to show, and a lot of equation, a lot of metrics to have to do inversion, and it's complicated. And people figured out, okay, we have to find a way to do it. It's made more simple. So, and then the way people do it, they try to inverse the below, the BS, the full network, to go back to this BS, a single reference network. So basically, what the BS network is, they want to do it, they want to transfer that all possible combination to a just equivalent single reference problem. So, and that's the problem is a fail linking. So, so basically, that's the product we have the end images available. So if we combine everything together, we have something like n time with n-1 divided by 2. So in case of the BS network, so it's just about n-1 value is sufficient because we have a 0 closure phase. So fail linking is a statistical method. So remember, so in the previous talk, when we're talking about the closure phase, it's always referred to the other aspect of the problem. That is, we want to retrieve the signal inside the closure phase. So we want to do something like physics interpretation for that problem. But in here, we prefer the problem based on statistic methods. So we want to avoid that closure phase non-zero. So basically, the problem is we combine everything together and transform it into a single equivalent, a single preference time series data. So the problem is quite straightforward nowadays because you can see here. The way we combine everything together is we just put in a certain covariant matrix, like coherent matrix. Here you see that is two-dimensional matrix, and then if you concerned in a certain position in column M and the row M, you will see the problem is just the minimal problem like this one. So you have something like a certain kind of wave factor, and then we tie with the cosine of the phi n m. And the other parameter is the theta n and the theta m. That's the parameter we want to estimate from their optimization. So all the proposal during the last 15 years for the fail linking, it's just different. It's just different about the wave factor here. So the gamma frame here. So here it's a little bit main characteristics of the main linking algorithm. There's a lot, but here we can classify into approach. Basically, it's based on the computation for the problem, and the other one is based on the coherent matrix to improve the data before we do the inversion. So based on the first one, since the words of the Guarnieri and Tebadini is they propose to you. That's one in the frameworks of tomography SAR. So basically, that even in tomography SAR, with just a few images, they can exploit the best information to improve a lot in terms of the phase calibration in the tomography work. So the idea of phase linking is from that literature. And then after that, there is exploit for that concept to do for example, with the phase triangle in the squeezer, and the other one with eigenvalue decomposition, and so on. So, so you see here, every algorithm is different about how we are using the wave factor during the optimization. And here it's a little bit of performance. So the performance is ordered from low performance to high performance to facilitate the visualization. So basically, the coherent and the EVD, the eigenvalue decomposition, is almost similar performance. And then we go to ME and go to maximum likelihood and go to regulation and go to compression. While the compression is very close to the lower bound, because that during the compression process, we are able to cancel out all the noise in the compression version. So, and then recently, I just think about the rules of concept, how we can use the recent AI technology like deep learning to learn something, because you see with the phase linking, the algorithm is there, and then a lot of proposals, and not necessarily which one is the best one. So if we are able to put everything together in kind of framework, and like for deep learning, we can gain something for the next generation. Here's just the first concept where there's not much to say, but this one is just a very simple synthesis data set to performance to see, okay, and then we see the quite positive that you see in the E and the F, the last slide. So you see with the E's and the F, we are able to reconstruct the data with respect to RD1. So the input, you see the input is the big one. So the input is the real data, something like one. It's always noisy like this one. But when we do phase linking, we are able to retrieve the signal for our problem. Okay, so that is the problem of phase linking. So, and then we move from the BS to the combine with the DS. So the key problem when we combine is we have to able to be sure that the quality of the distributed scatter we put together with the BS should be quite, say, similar quality. It means we have to find a way to enhance, to emulate the DS to quasi BS. So the way to do that one is we have to be careful that when we do the phase linking, there's a certain kind of assumption that it means that not all the bit cell can be the same distribution. So we have to be sure that we dealing with a certain kind of Gaussian distribution target. So to do that one, we have to be sure that we have to find a certain bit cell which share similar statistic behavior, something like statistical homogeneous bit cell, by applying a certain test like t-test or like Anderson test. And then based on that family, we can form the main actor. So basically that's the covariant matrix like this one. And then we deal with the phase linking to find the best optimal n-1 phase value. And then if there is a certain fit with the model, we can replace that value with the original one data. So whenever we're done with the BS processing, we improve the quality of the DS. We put together with the BS, and the processing of the BS, DS is almost the same classic traditional BS methods. So the BS, the DS is powerful, but the problem is we have to do the full covariant matrix. Like the first line you see here, you have to do the full covariant matrix here. Like in this example, it's just about 90 by 90 matrix. It's easy to do eigenvalue decomposition, but you know now syndrome 1 is something like 400 images and 400 image, 400 by 400 matrix. It's not really easy for computer to do the inversion, and maybe in future we have maybe 1,000. So it's not really efficient to do inversion with that kind of matrix. And then what the problem is, if we have a new future acquisition available, what we had to do, we had to recalculate everything. So the idea is, instead of to dealing with the full network like this one, we divide by a certain mini stack. For example, I divide in the second line, I divide by 10 by 10, so we have a mini stack, 10 image, 10 image, 10 image, 10 image. So instead of dealing with the covariant matrix of about 90 by 90, we're just dealing with 10 by 10 image, a 10 by 10 covariant matrix here, and it must be straightforward to do inversion. And then during this mini stack here, we do fail linking inside 10. So we will do the fail linking. We will do fail linking for this one. So basically, there is a mini stack about 10 images. So we do the fail linking. So we got the 10 weight factor, and then we do a certain coherence summation in that original 10 images. So we put it together. We take assumption and we take a summation focusing, and we got the compression version like this one. So basically, we are able to exploit the fail linking to deliver a certain way to sum the original single look complex data from 10 images to 1 image like this one. So we repeat the procedure for the other mini stack, and we got about 9 compressed single look complex version here. So, and then we are able to do fail linking again to join link everything together. So we have the compressed version. So whenever we have a new acquisition data, so instead of dealing with 90 by 90 image, we have to here just 9 images, and the new future acquisition available. So the problem is really a lot, so we don't need to recalculate everything. So whenever we need, we are able to use in that compressed version to link with the full time series data. Okay, and then we implement this one in the Tomos software. So this is open source. So if you want, you can go to my GitHub and you see this one. And the concept is very friendly in terms of the big data processing. For example, with true image and with a size like this one, it requires a lot in terms of the DS processing, but just about 45 gigabytes for the concept. So it's very friendly in kind of the big data processing. And then a little bit of demonstration for how it's going on. So you see, using with the complex algorithm, we get a lot in terms of the denser point target for analysis. So basically, through image, we see the phenomena is almost the same, but on your right side, you see a lot of information available. And then we move to a little bit more focus to a certain small area here. So on your top, on the left, so I do exactly the same images, but in the small area here, so the previous one is very big one, so 250 kilometers by 350 kilometers. Here, the small one, and we put together the small and the big one, and we see the correlation is almost similar. The error is something like about less than 1 millimeter per year. So we a little bit focus on about the small error here with 3 different data sets. So with single ones, ascending and descending, and also with Cosmos schema data. We see the same spatial distribution. Of course, if we go into a little bit detail like something like with the profile from A to B, we see a little bit different, but it's very tiny. So, and then we have some validation because there is data here. So not so much to say, but the conclusion to summarize is the fail linkings, I repeat it here, this is the way to handle in statistical way. So it's not the physics, we don't want to retrieve any physics information signal here. So if you want to do retrieve some information, something like some monster, you have to avoid this techniques. And then in future research, I think the deep learning can be a valuable tool to improve data performance. And then Tomos is my first domain public tools available to my knowledge. I don't know the other one. And then there is also some research and some forum to discuss on everything. So I'm free over there, on way available over there for you. So this work is supported by just a very tiny project. So I'm open to join with you in a certain kind of project to do future work interesting for community. Okay, I'm done. Thank you a lot for your attention.
Thank you very much. We do have time for a couple of questions.
Okay, I'm available, everyone. Okay.
Thanks for your good presentation. So I have two questions. First one is why you name your toolkit TOMSA, because TOMSA in our community we may refer it to something like tomographics, and for work in urban scenarios and for separate different scatters within 1 pixel. So this is my first question. And the second one is I have seen one of your slides that you have a comparison between PS plus DS and your compressive sum maybe. I find more points can be found in your method. So I was wondering, because you didn't use the full stack in the diagrams, and so how it can be guaranteed that more points can be kept if less in the diagrams was used. Would you explain a little bit on this? Thank you.
Okay, thank you for your question. So maybe I try to rephrase your question for everyone to follow, but maybe if it's not correct, maybe correct me. So the first question is about the Tomosa name. So yeah, why is the name of Tomosa? Because this might be in Tomosa. So from that one, I have a lot of course for cytomography, for interferometry, for polarimetry. And Tomosa is not immortal, it's just an advanced technique for interferometry. So I have, how I can say, from end-to-end processing for Tomosa. But when I give the public the domain tools, so I just focus on the back case with dealing with the BS and the DS processing. That's why I keep the same name, Tomosa, but people confusing about the Tomosa techniques and the Tomosa for the BS and DS. That's the first question, is correct. And the second one is when people combine the BS and DS, people do it separately. People try to enhance the quality of the DS, and then they put the BS separately, and then wherever they are able to improve the DS to become the quasi-BS, and they put it together. So the same thing we do with compression. We do compression with just the DS, and then we combine with the BS. So we don't do anything with compression with the BS. We don't touch that one. Is this correct for your second question? Okay. Okay, thank you. Yeah. Okay.
Okay. So thank you. I think we should proceed to the next. Thanks a lot. So we proceed to the next presentation. This will be given by Yuje Zheng from the California Institute of Technology. The title is Modeling Soil Moisture with Cumulated Closure Phase of Interferometric SAR Measurements. Please.
Good morning. My name is Yuje Zheng. I'm now at University of Texas at Dallas. So this work is started when I was a postdoc at Caltech, working with Hirash Fatahi. So my topic today is about the intricacies of modeling soil moisture with closure phase bias. Many talks before me have already discussed what is non-zero closure phase, what is short temporal bias in time series, so I don't have to do that anymore. I'd just like to highlight the connection between these two phenomena. So they both share the same governing process, a process that induces complex changes, not just phase shifts in interferometric measurements. And because of this connection, we can actually use one to correct for the other. So last year, we have a study published about using sequential closure phase to do bias correction, and the study area was the California Mojave Desert, and we find a lot of bias in the area surrounding the dry salt lakes. So I'm not going to get into details here because it's not the focus of today's talk, but what I really want to show you and what really gets me here today is we really want to understand closure phase bias, not as noise, but as a signal. Take a point adjacent to the Bristol Dry Lake as an example. So this is the closure phase bias we extracted for this point. So you can see that there is, we observe this cumulative uplift signal that's about 4 centimeters in 4 years. And it's not linear, it's rather episodic uplift episodes. What's interesting is when we compare the precipitation records in this area, you can see that the uplift episodes align very well with the precipitation events. And if we superimpose the cumulative precipitation events, this relationship is even more evident. And we know that INSAR correlation can be infected by rain events in these type of hyper-arid regions. For example, from this plot presented by Jordan et al. 2020, you can see that whenever it rains, we have a transient loss of correlation, and then there is this gradual recovery of correlation as the soil dries. So we're thinking, could we be seeing the same thing here? The soil drying process, to be specific, but not just in correlation, but in phase. And to really understand that, this is a nice correlation plot, but it's not causal. So we really need to dive into the physical models. And very luckily for us, we don't have to do that ourselves because the INSAR community has already produced a few interferometric models for soil moisture. For example, the Dizan et al. 2014 has described very nicely how soil moisture change impact the interferometric phase. What we do here is that we build upon this analytical model and we discretize it. And the advantage of doing that is with a discretized model, it's very easy to implement for numerical simulation. And secondly, it's easier to adapt to more complicated scenarios where you might not be easy to get a solution analytically. And thirdly, the reason I like it so much is that we can actually start from single-look radar returns and work our way through interferometry, multi-look, time series analysis, so you can really understand the whole process. So here is our general approach of trying to understand closure phase bias as a signal. We'll simulate a series of single-look complex images that go through different soil moisture time series. And we'll specifically experiment with 2 types of environment. The first would be an arid environment where we would see, so it's like a desert environment. Usually the soil moisture is at a low level, and except when it rains, you have a sudden increase in soil moisture and then a gradual decay. And the second case is a wet environment, which more like agricultural fields or croplands, where you have a soil, where the soil moisture is usually maintained at a high level, except when the weather gets dry and you have less rain, and then the soil starts to dry out. And then the farmers will need to irrigate more to recover the soil moisture to its preferred level. Okay, so let's look at the first case, an arid environment. And here I'm showing you on the left is an example of in situ soil moisture measurements at a desert, in the Mojave Desert in 1 year. So you can see, as we described earlier, soil moisture was generally low except when there's these isolated rain events. Now imagine a time period in one of these deserts where there are 3 distinct rain events. So the y-axis here is soil moisture, and then these bumps are post-rain soil moisture variations. And for simulation purposes, we made both the magnitude and the duration of these post-rain soil moisture variation to be different. What we do now is that we simulate 100 soil acquisitions that go through these rain events. And then we form interferograms, and we multi-look them, and then we do time series analysis of different bandwidths. And these are the resulting time series. And when I say bandwidths, for example, bandwidth 1 analysis, it means that it uses a network that only has connection 1 interferograms, and bandwidth 5 is only have connection 1 through connection 5, and full network is using all possible pairs. So you can see this diverging time series, which is what we see in real data as well. And
I would just like to quickly point out that we can learn a lot from these simulations about the origin of bias, why it's cumulative, why it's fading, etc. But okay, so I'm not gonna get into details here because the time limit. Rather, I'll just show you what the closure phase bias look like. So that's the difference between the bandwidth 1 time series and the full network analysis. As you can see here, the simulated closure phase bias closely mimics what we see in real-world data. And first of all, it's cumulative, and as you can see, it also confirms that the uplift we see in these biases corresponds to the drying in the soil. And secondly, the amount of uplift is really a function of how much the soil moisture varies and how long it varies. So it's it depends on both the soil moisture decay rate and variation. And slower decay and greater variation result in larger uplift. And yeah, so to sum up till now, we have this forward model that we can start from soil moisture values, and we will end up with a predicted bias time series. And now we can validate that with real-world data. So continuing with our California Mojave Desert example now is a full frame, so we can include an in situ station, which is the fourth station marked by the cross in the map there. And on the right is the in situ soil moisture measurements for this station. Taking the soil moisture measurements at SAR acquisition dates, we can feed them into the forward model and generate a predicted bias. And we can compare that with the observed bias, which actually matches really well. So now we can have some good confidence that our forward model in this error environment case works pretty well. And now we can start to think about how to work the other way around from closure phase bias to soil moisture. And thanks to this incredibly simple form of bias, and when we have a bias that looks like this, we almost can have a good guess of what the soil moisture looks like. We know the uplift in bias corresponds to the soil drying. So we can make a guess of the soil moisture that looks something like this. And then we can feed our guess of the soil moisture into the forward model and generate a predicted bias. And we may get something like this. That just means that we have overestimated the soil moisture variation, so we can go back and modify our guess and then generate another prediction. So by doing this search, we'll eventually arrive at a solution that fits the bias, fits the data. So to sum this up, basically we're proposing a 3-step inversion scheme. The first step is to identify a disturbance window or disturbance windows. And this is where soil moisture values derail from their base values due to either a rain event or something else. And the second step is we try to describe the soil moisture time series with a base value and an exponential decay model that describes its evolution in the disturbance window. And the third step would be to search for the parameters that gives us the best fit to the bias time series. So now let's see how this works with real data. Coming back to the real data example from the Mojave Desert, this is the bias that I have just shown a few slides ago. The first step is to identify the disturbance windows. So it will look like we have two, but actually I find it's much easier and more accurate to actually identify these disturbance windows from the phase gradient instead. So in the phase gradient, each of these peaks or upward triangles corresponds to one disturbance event. And with some threshold on the baseline variations, we identify 6 disturbance events for this case. And with that, we can start to populate the soil moisture time series and start to search for the best parameters. And this is after some quick search. This is the result. On the top panel is the derived soil moisture in orange or yellowish color. And on the bottom is the fit of the observed bias versus the predicted bias. And on the top, it's also I also plotted the in-situ soil moisture measurements, so you can see the comparison between the two. Overall, it's a pretty good agreement. Oh, yeah, and interesting, I find that bias gradient itself may be able to serve as a proxy for soil moisture. This is because previously we have used bias gradient to identify the disturbance windows. So, and also usually the bigger the disturbance, the bigger the gradient. So that's why you see this nice correlation. I do have to point out that you can see that the bias gradient is more symmetric when the soil increases, rises, and falls. But so that doesn't capture the really asymmetric nature of soil moisture wetting, soil wetting and drying process. But nonetheless, this could be an effective proxy, which I think a lot of the presenters have shown earlier before as well. Yeah, so now let's go to the second scenario, which is a wet environment, or agricultural field-like environment. This is on the left, again, is an example of how in-situ soil moisture measurements vary in an agricultural fields in 1 year. As you can see, it's mostly maintained at a relatively high level, and when it's summer, it gets dry, and then there's increased irrigation and an attempt to bring the soil moisture back to its desired level. And similarly, like before, we simulate for 3 different disturbance events. Each of these events will have different magnitudes and duration. And repeating the steps for simulation, we can generate a predictive closure phase bias. And you can see now it's opposite. It's basically a mirrored image of what we see for the arid environment case. You have this cumulative subsidence in bias. And the subsidence episodes corresponds to soil moisture increase, and the magnitude also depends on the amount of increase and how fast it increases. And slower increase and greater variation will result in larger subsidence, apparent subsidence. Yeah, so now let's look at some real data. And this is a data set in the Central Valley, California, consists of only connection 1 and connection 2 interferograms. So they have a temporal baseline of 6 or 12 days. And yeah, so they can, so I have checked all interferograms. They retain very good correlation over the agricultural fields. So the map here is a closure phase bias velocity map. You can see that the color is mostly blue, which means it's the bias is negative. That means it looks like a subsidence. And the outline of the bias aligns very well with the agricultural fields. The bias is actually quite big. As you can see from the scale there, it's from -3 centimeters to 3 centimeters per year. And on the right is an example of the closure phase bias we see from a point that's marked by the yellow cross there in the Sacramento Valley. So you can see this is the familiar shape of cumulative subsidence, episodic subsidence. And now if we compare the precipitation records in this region, you can see that the subsidence actually happens when there's, in the summer, and when there's not much rain. So that also confirms our simulation model earlier. So we can do the same thing again for the inversion. So on the top panel is the predicted and observed bias, and on the bottom is the orange dots are the derived soil moisture from the bias, and the gray dots are SMAP soil moisture. So unfortunately, I was not able to find any in situ soil moisture measurements here. So, but it's tricky to compare these two because we know that SMAP soil moisture is of much larger spatial scale. It's really an average over kilometers of space, whereas the bias pixels is about 100 meter in size. But nonetheless, I want to point out that you can see there is this wetting period in summer in both derived data sets. And yeah, so in summary, we have produced a discrete soil moisture model that can link soil moisture variation to closure phase bias. And the advantage of this model is that we can really make it as complicated as we want to adapt to realistic scenarios. Right now, we are using the simplest form. And we have also shown some observations of closure phase bias in 2 different environmental settings. One is in desert regions where you see the bias as uplift, and one in the agricultural regions where you see the bias as subsidence. And we have shown some forward model that can link soil moisture variations to bias accumulation very nicely, and I have shown some initial results for the inversion. And there are some potentials of using closure phase bias for modeling soil moisture. And one is because you can see that the way we link soil moisture variation to bias accumulation is very straightforward. You can very easily visualize it. This is comparing to trying to work out the inversion directly, either with closure phase or with the SAR amplitudes. And of course, it offers potentials to detect drought onset, produces high-resolution soil moisture maps, and scale, and it really scales with global time series products. Of course, it has its limitations. For one, it has limited temporal resolution, which is in turn limited by SAR acquisition intervals. And also, our inversion scheme is at its very early stages, and it has yet to be tested with more extensive data. I think that's all I have. Thank you.
Thank you for this very interesting presentation. So, yeah, please go ahead.
Yeah, nice talk. I have a question for you, but also for the other speakers. My takeaway message from all of this is that if you want to detect soil moisture, use sequential interferograms. But if you wanted to avoid soil moisture, you would use longer time span interferograms, and that time span would be dictated by the decay time of that property. But what bothers me a little bit is, I think at Yasser's talk, he showed annual cycles, which suggests maybe that time span is annual.
Yeah, so I really think the simulation can, okay, sorry, I'm trying to go back there. The simulation can really help us understand about the time span you need to have to avoid the bias, because you can see here, the reason you have this cumulative bias in short temporal baseline is because, first of all, you have this asymmetric response from soil wetting and drying. So that produces a signal. And when you use short temporal baseline only, you have a short memory. So you can't really distinguish what is a real deformation and what is not. And so that's why you see the bandwidth 1 analysis, it starts to build up. But once you have pairs that actually span this rain events, so it knows that like before, what is like before the rain and what is like after the rain. Like, for example, if you see for the first rain events for a bandwidth 5 analysis, it doesn't really show much bias. So basically, it's not how long that you need a threshold for the temporal baseline. It's more about the what's happening there. Like in this example, if it's a desert area, and you probably just need pairs that have longer durations than the rain, than the post soil moisture disturbance time. And for agricultural fields, it might be more complicated. So it really depends on that.
But this bandwidth 5 included
1, 2, 3, 4, 5.
What
Yes.
if you avoided the short ones and just kept the 5?
That's fine. Yeah, sure.
It would be better.
So another great thing about the simulation is you can easily try that with the simulation and see how well it works. Yeah.
Yeah, there is one more. I think we take one more and then we defer the rest to the roundtable, which will be tomorrow after the second session in this topic. So anyone who wants to discuss this further after this question, please come to the roundtable tomorrow. There is one question over here.
Thank you so much for the nice presentation. Now that you have the simulation tool, I was curious, in a weird world where there's a rain, but it never dries, so there's a step function, and what would be the response of what would be the result of your simulation?
So are you saying that if it's like a step function and then never dries? Yeah,
Right.
so I think it will look something like the full network. But I don't know. So that's, again, it's a thing that we can try out with the simulation.
It's interesting that it seems to be more sensitive to the gradual drying phase.
Yes,
than the
yes,
step
yes, it
itself.
is. So we find that it's not only it's sensitive to the speed of drying and also the amount of drying.
So you can try a step function and see what happens.
Yes,
Thank you.
we can do that.
Yeah, I think not to steal the coffee break from everybody, I think we have to close now and return for the roundtable tomorrow.
Thank you very much, everybody. Welcome to Subsidence and Deformation 1. Let's make a start now, even though we've got a few people coming in, just so that we don't overrun into lunchtime. I know how keen everybody will be for food. So with that, can we have our first presenter down, please? That is Soo-Ki Lee from Kangwon National University.
Hello everyone, my name is Soo-Ki Lee from Kangwon University, South Korea. Today I present our research. Title is Iron Mining Induced Substance. Mapping, that's okay. North Korea derived by improved combination scatter with optimized point scatterers. We called ICOPs for insert time series analysis. Too far? Okay. This is study area. Musan mining site. Musan open pit mine, North Korea, close to Chinese border, which is located in Musan-gun, North Hamgyong province. Musan mining, also known as one of big open pit mining, the Korean peninsula with the topography. This mining site has hilly topography with high elevation area. In the figure, we represent the time series images of Musan mining site from 2000 to 2021 derived by optical imaging from Landsat 7 and 8 satellite. Mining surface deformation refer to the changes in the surface level caused by subsurface mining activities. These changes can affect environmental and social impacts, including ground substance, land instability, and damage to infrastructure. To mitigate the effects of surface deformation, mining companies generally employ various ways such as monitoring of substance and implementation of mitigation measures during the mining process. So we suggest two topics in order to monitoring of mining site. First, estimation of elevation changes using DEM. Second, time series analysis based on ICOPs. In this research, we use two of DEM as the topography reference for generating the SAR. Besides, the DEM will be used to evaluate the change of topography condition in the study area. This table information of this table shows information of DEM in this research. we use SRTM-DEM. Acquisition date is 2000. ALOS-DEM acquisition date 26 to 2011. Copernicus DM acquisition date is 2011 to 2015. So SRTM DEM minus ALOS DEM means elevation changes during 2000 to 2011, and also ALOS DEM minus Copernicus DEM means elevation changes during 2011 to 2016. Figure show the evaluation site and the western dumping site, eastern dumping site, and elevation changes from 2000 to 2011 are made by subtracting the values in the LOSDM from these in the SRTM DM to determine changes that are increasing in the eastern dumping area and west dumping area marked with blue. Elevation change was generated by subtracting value from the Copernicus DM in the ALOS DM during 2011 to 2016. The eastern area has distribution of elevation changes in the northern and southern areas. In the western area, the western area, there is a distribution changes in the northern part in the dumping area. This result is we estimate of volume changes. The iron ore distribution pattern in the Ansan formation is similar to that of Musan group at the Musan mine. The Musan group is considered to be the eastern extension of the Ansan group. In this study, the average density of ore produced at the Musan mine was estimated to be approximately 3.4 times 10 to 3 kilometer per cubic meter over the average density of ore produced from the Ansan formation. So as a result, the estimation mass change in 2000 to 2011 approximate 88.99 megaton in dumping area, and for 2011 to 2016 about 69.87 megaton. This is the second suggest in order to analyze the surface deformation of Musan mining. We use the SAR data from Sentinel-1 seabed provided by ESA. The Sentinel satellite has visitation repeat of 12 days, which can maintain the temporal resolution on detecting deformation. So, for SAR data was acquired from October 2016 to August 2022, which contained 168 scenes. Also, we use ascending track and 156 paths and 174 plane, and we use the IW mode and VB polarization. We propose the time series method we called ICOPS. Inside time series analysis is a powerful remote sensing technique that can measure surface deformation with high spatial and temporal resolution and has been widely used in various applications. So we propose the use of improved combined scatters interferometry with optimized point scatter we called ICOPS, time series analysis for INSA application in the continuous monitoring of surface deformation. ICOPS have two key points. First, use of combined scatters. This advantage is highly applicable, such as rural area or agricultural area. And the second, the optimization of point scatters based on the machine learning. And this advantage have improved precision. PS characteristic has known as the phase stable target of radar. We know that the vegetated area like the blue box not produce the PS points caused by lack of coherence. So for the area with not vegetated but also not high coherence area, maybe have coherence characteristic that can be used to analyze, like yellow box. Therefore, we can evaluate they can be used extracted the deformation data to increase the spatial coverage. Pixels with similar signal characteristic result of test on the images become broader than averaged and applied to original pixels. This called distribute scatters DS. After obtaining the DS as complement of PS points, it can be processed with PS points to perform the time series analysis. Along with the PS and DS points could improve the spatial coverage and measurement with maintain the quality of the measurement point. This is our research workflow. We have three main processes. First is pre-processing, and then time series analysis, and last, optimization processing. The INSA pre-processing step include SSC co-registration process and interferogram formation, and these are generated. These formation using single reference and multi-reference format, which will be applied on time series processing. PS processing need a single reference, and then DS processing need multi-reference format, so we make both them. PS processing uses stems. The PS points analysis was carried out based on the stems algorithm, and stems algorithm based on ADEI. So selection process based on phase characteristics suitable for finding the low amplitude natural target with phase stability. And this figure is PS processing steps and the result of PS points. And the distributed scatter process was processed to enhance the coverage of measurement by. We used SHP identification and additive spatial coherence estimation or the temporal coherence estimation. So we use the FASH method and then SHP identification and additive estimation, DS candidate, and find the final DS. The process is started by select and analyze a single pixel, and then the other pixels were also being processed based on fast statistically homogeneous pixels. And those signals are averaged and applied to form a distributed scatter characters based on the statistically homogeneous pixel value. Then estimating additive spatial coherence of possible interprogram. Then DS points was obtained by defining the threshold on the spatial and temporal coherence at the last stage. After the PSDS points were determined, we performed unwrap phase and using MCF method or available interprograms. An error estimation also conducted to reduce the error from topographic error and atmospheric condition. Then for time series deformation estimation was carried out by using SVD approach on deformation rate to derive time series deformation measurement. MPD derived from this step will be processed on optimization process. Keep the algorithm. I show the result. Result mean deformation map at the Musan. As a result, eastern dumping area P1 has experienced constant substance since 2016. It reached a maximum rate of deformation, 18.63 centimeter years in this area. And then P2, western dumping area P2 has mean surface deformation, 11 centimeter per year was recorded. And after 2016, American census the North Korea sale of mineral resource. So we make the time series analysis. This the accumulation of deformation for each year from 2016 to 2022. So profile deformation from A to A that show the deformation increasing from 2017 to 2021, then has slowed in 2022. We show the maximum deformation 121 centimeters. The western dumping profile deformation, then from line C to C that has shown the maximum accumulation about 70 centimeters, and D to D that also shown the maximum deformation 78 centimeters. The western dumping area known as dumping area which had traditional sloping dumping from the profile known the center area has soil compaction due to load of the surface and low slope has accumulation and debris. This is conclusion and discussion. We conduct the analysis mining capacity by evaluate the change of elevation from the DEM. ICOPS method has been applied to assess the rand substance in Musan mining complex. Integrated of DS points into PS points has increased the coverage of area in long time observation by more than 40%. And distribution of surface deformation in Musan mining was located in eastern dumping and western dumping area. Further analysis show the substance deformation related with the soil compaction from the dump materials. Thank you for the listening.
Maybe time for one very quick question. Otherwise, we proceed to the next speaker because it's already late. So the next speaker is my co-chair, Rachel Holley. Please, Rachel.
Right, so I have to say this isn't quite what I was planning to present when I wrote the abstract. One of the problems with... Okay, is that any better?
Yeah.
Right, so this isn't quite what I was planning to present when I first wrote the abstract. Unfortunately, one of the problems of having to write abstracts so far in advance, there was something that I was hoping to put in here that I wasn't able to. But actually, the material that I wrote for the abstract and the things that I have in around it are actually a reasonably good overview and recap of some of the issues with elevation models in INSAR. So perhaps in terms of high science, there's the chunk that I can't present and I'm perhaps missing, but I figured these days a lot of people, particularly younger students, are working with SRTM data and global elevation models and haven't necessarily had very much exposure to some of the problems you can get with elevation models in other data sets and with other ways of working. So this is a little bit of a review of some of those issues, particularly relevant to mining areas. So I'm just about old enough to remember before the glory days of the SRTM era, when people were having to do 3-pass INSAR because we didn't have elevation models. So I think I started INSAR the same year that SRTM was released, which ages me somewhat these days. But these days we have lots of global DEMs, we have SRTM, we have GLO30, we have lots of other good information on this. And if we have height errors, we can do stack processing, regression for height, problem solved, right? Not quite so much. So just a very quick recap. The sensitivity to height scales with larger baselines, steeper incidence angles, shorter wavelengths. So this is actually something that starts to become relevant for some of the more recent smaller SAR satellites. They tend to have fairly large baselines. They're mostly X-band, so the shorter wavelength. So actually, that performance with height starts becoming more important. People used to processing Sentinel-1 with the very short, nice, tight baseline tube won't necessarily see some of these issues. But once we start getting into these other data sets, they can and are important. Some of the issues we see, so poor DEM alignment. In this particular case, there's a section of high resolution DEM which was properly aligned. It was mosaicked with a wider, I think, GLO30 DEM around the edges. And because the high resolution had a poor georeference on it, it was made using, I think, local LiDAR data. When the two were mosaicked, they didn't line up. The GLO30 data was offset. And you can see in the image on the left, there's really quite considerable signals along those mountain ridge crests, where all of the topography is slightly to the left of where it should be. And on the right, once we did proper alignment, those signals all disappear. Another problem you can have if you have low resolution SAR, DEM data compared to your SAR. So you can end up with the problem where if you have steep, quite sharp topography, you have the tops of all your mountains are missing in the DEM and the bottom of all your valleys are missing in the DEM. And you end up with this really characteristic pattern, which, again, most of you using SRTM data won't have seen. But it's very easy to correct with a higher resolution DEM. And if I flick between the two, you can see that all of that elevation noise disappears. The other problem that we have a lot more in the mining industry in particular, but lots of other applications too, is the topography has actually changed. So GLO30, the most recent global DEM that we have access to, was made, I think, between 2011 and 2015. For environmental applications, that's pretty good, but you can do an awful lot of mining in the time since then. So you can see in this example, the pit here was partly present in the GLO30 DEM dataset, but there are an awful lot of fringes both in the pit and on the waste piles down in the bottom left. If I reprocess that with a higher resolution recent DEM, you can see that most of that signal disappears. The waste piles, the fringes you see on the waste piles start matching their topography. There has been a little bit of change since even this up-to-date DEM was made. Some of those fringes are actual deformation because those waste piles have uncompacted material which then sinks over time. But you get a really good improvement in your quality by trying to use proper up-to-date DEM data. But why can't we just do a height regression? So these days, most stack processing algorithms allow you to do a regression for your height. Across your stack, you can then correct your topography. It works really nicely when it works. So in this example, it's, I think, a Cosmos SkyMed image. In this area, we were processing across a facility. There wasn't an existing DEM data set that had the facility in it. It was recently built. So we started from scratch with a bare earth ellipsoid, and we generated our own elevation model. And you can see the blue sections on there are the raised pipe racks. So they're the high parts of the facility, and we've essentially mapped out the facility purely using that height-based correction. But there are some limitations to this. So sometimes there won't be enough SAR images in the stack, particularly if you're working with commercial data. You don't have your nice 6 or 12-day Sentinel acquisitions. You have to work with what you've got. You also can't do these stack-based regressions anywhere where you have varying coherence, or where there are periods of time where you don't have coherence. Correlated baselines are another issue. So again, some of the new SAR satellites have issues where the baselines vary through time. And a lot of these processing chains and processing algorithms make the assumption that the baseline distribution averages out over time and is essentially random. Where that isn't the case, you have to start being really careful with what assumptions your processing makes. So the example I've got here is actually a historical example. I stole it straight out of my Fringe 2011 presentation. It's ALOS 1. But the same can be true for quite a lot of the newer SAR satellites. Small baselines, you would expect me to say aren't a problem, and they're not, but they do limit our ability to model the topography. And that's particularly a limitation in urban environments. So sometimes a little bit of baseline is nice, some of the time. And applications where these limitations matter. So I'm going to talk quite a lot about mines, but it's also important for things like volcanoes and also for new infrastructure. And any time we're neglecting the impact that DEM changes can have, we're going to be limiting what we can do, particularly for these applications. Mine sites, they're particularly tricky for elevation change, partly because having the mine, the point is to try and change the elevation. But there are lots of different processes that go on. They excavate the pits, but they also have waste piles, stockpiles. TSF is a tailings storage facility, and they are often built sequentially, so every few months to few years, they will raise the level of essentially the dam holding back the mine waste. You often got a lot of co-occurring deformation. So you have both height changes and settlement of dumped material or triggered instability, for example, if you've had a failure in the area before. And you have to have both an algorithm and a data set which allow you to pick apart those different contributions properly. And because different parts of the mine are changing at different times, you'll have intermittent patches of coherence which are incoherent for a short period, pop back into coherence again, but with completely different topography and a completely different motion regime to what they had before. And that will change in one area of the mine at a different time to it does in the next area and the next area. So it's quite a complicated jigsaw puzzle to try and put together. It's also somewhere where really timely results are crucial. We don't have 6 months to sit down and try and pick apart all these contributions, because we're trying to do mine safety monitoring to make sure that populations aren't at risk, for example, or workforce aren't at risk. It's really important that we have this data quickly. So there are, of course, alternative DEMs. There are lots of different sources. You can acquire DEMs, say, from airborne data, drones. You'll all have seen the kinds of data sets you have in Google Earth. We can get it from bistatic radar, which is what a lot of the global DEMs tend to be, and also from stereo-optical data acquisitions. So this, for example, I think is a Pleiad image, stereo-optical. You can use it to refine the elevation model, really quite at a very localized scale. Which DEMs you can use depend on what you're trying to do. There are obviously limitations. It's lovely to have really frequent, high-resolution elevation models anytime you want them, but that comes at a cost. So what you're trying to do with that data has to justify the increased cost. But there are also some technical barriers. So things like cloud cover can affect airborne and satellite stereo. There'll be flight restrictions. There's limits on where you have archive coverage. And you also have problems as soon as you start introducing small areas of DEM coverage in sticking them together properly, making sure you've done the mosaicing correctly, georeferencing them properly, and getting them quickly. If you have an area of the mine that has become coherent, you want to be getting an elevation model within, ideally, sort of 11, 12 days for your next SAR acquisition. That's quite a tough requirement, even for the commercial DEM availabilities that we have. Oh. And just as an example of what I mean by when an area becomes coherent after a change, this is a tailings storage facility which has recently undergone a dam raise. So they've added material onto the top of an existing tailings dam. And you can see the first image we processed after the change. As soon as the coherence returns, we're getting quite a strong apparent uplift signal, which exactly matches where they've put the new material. Now, we understand what that is, but trying to explain that to a client and putting it through the automated alerting procedures that say, hey, we've got deformation here, obviously doesn't understand why it's seeing that signal. So if we can get a quick, up-to-date DEM and remove that height error, then we get better, easier to use results. Recently, there are more improvements in the availability, the quick availability of those DEMs, for example, often just because satellites are now coming in constellations with faster revisits. So we get down to the point where we could potentially get acquisitions in days rather than having to wait months like we needed to a few years back. But that does, again, rely on things like cloud cover. The other thing we've looked at recently is retrospective studies of tailings storage facilities, for example. A lot of the operators in recent years have become really kind of wide awake and clued up to what's happening with their tailings after some of the terrible dam failures that have occurred. But one of the problems with tailings dams is many of the construction methods mean the older phases are buried underneath the later phases, so they build up on top of existing structures. And if you want to understand the stability of those existing structures underneath, you want to know you're on stable foundations. But sometimes past mine operators didn't keep records, didn't accurately record what they'd done, when they'd done it. So the satellite archive has a lot to add for that. We can go back in time, we can show the operator how their mine was built before they bought it, for example, how the tailings dam was constructed, and also how stable it was before they put anything else on top of it. And that's great, we've got that huge SAR archive going back 30 years, but what we don't always have is DEMs. We have the wide, coarse scale global DEMs, but it's much better to have data close in time to when the interferograms were produced. We want to have a DEM data set that matches, if possible, at least each time period where nothing changed, or even each interferogram. And so this is an example of a recent study we did. It's a bit of a schematic rather than exact data for unfortunate commercial confidentiality reasons. But basically what we have for this site is split up time periods based on when we know that the surface was changing. So when they were doing these phased dam raises, we can look at the INSAR in time periods between those raises. We can try and find an elevation model that matches those as closely as possible. And then we can get a deformation history for the whole structure throughout a fairly long period of time, but without those DEM artifacts that will skew the interpretation. There are lots of potential sources for those. Once you get into historical data, you have to sometimes start combing around and cherry picking data from here for this time period, data from here for that time period. There are some other sources of frequent historical DEMs in development, and that's one of the things that I unfortunately can't talk about today and hoped to. But in conclusions, so we mustn't forget, I think, that the standard INSAR approaches with a global DEM and a stack-based regression don't always suit things that are frequently changing or have really fine-scale topography, for example, urban applications. And whatever we do with the decisions we make in the future for SAR processing, for example, and SAR data supply, needs to bear in mind the fairly specific needs of these kinds of applications. On that note, we had a discussion, I think, in the Monday session about the co-registered SLC products. And just out of interest, I took one of the examples from my presentation here, and last night very quickly ran it, a very quick test through the processing, and tried geocoding the SAR image with and without the high-res up-to-date DEM, and you can see there's a really large shift in the position of that mine. There might be things that we can then do to try and mitigate that and reverse the geocoding correction to then do the processing, to then geocode it again better. But if you're trying to do rapid monitoring for safety of life applications, that's quite a big barrier to getting timely, accurate, good results that are easy for the mine to understand. So I will leave it there. Thank you very much.
Thank you for the nice presentation. Any questions?
Did you look at some TandemX data? Because with TandemX you get a DEM and you can do the INSAR in time. And this can improve results a lot. I didn't do this for INSAR, but for glacier offset tracking, and got much better results when you instantaneously get the DM together with the INSAR acquisition.
For sure, you absolutely can, yes. And it's a really nice, neat way of doing it. Obviously, commercially, it comes at a cost. Sometimes the application will justify that cost, and when it does, it's really brilliant. But it's nice to have a range of different options for different sites. You can't always get TandemX data where you want it, for example. There are other mission requirements. There are other sensors that aren't TerraSAR X for your SAR data. So it's nice, for sure, that's a really good example when you can use it, but it's nice to have the full range of others as well.
I just had one comment on the co-registered SLC slide. I completely agree. Yours is a very specialized case. Maybe you should not be using geocoded SLC for such detailed stuff, but maybe that should not hold up the rest of the community from using that approach. I see this as an extremely specialized analysis, not a very common sort of use case. So it was just a comment on that.
Yeah, for sure. I absolutely see the benefits of the geocoded SLCs for a lot of users, and I wouldn't say don't ever use them. my position on it, I think personally, would be as a community, there are enough applications. Mining may be quite specialised, but there's quite a lot of it, particularly in the commercial world. There are also volcanoes and ice applications and a lot of urban INSAR, again, commercially, but also I think in academia, looking at building scale deformations and digital twins and engineering models of buildings. And all of those things rely on being able to refine your heights in radar space and get height corrections out, which then affect the geocoding. So we can argue about the size of each of the market sectors, but I guess I'm just saying, don't forget about us.
Okay, it's time to pass to the next speaker, Zara Sadeghi. I hope I pronounced well your name.
Hi everyone. The project that I'm going to talk about today is entitled an INSAR analysis and corner reflector experiments for infrastructure stability monitoring using Sentinel-1 imagery. This project was defined by National Grid and implemented by Spotted, National Grid, and Cranfield University. So, National Grid Energy Transmission owns and maintains the high voltage electricity transmission network in England and Wales. And some movement of the electricity tower can make unacceptable safety hazard, which National Grid is required to correct this movement, which can be very expensive. So in order to avoid this or prevent this, National Grid conducts their own invasive analysis annually to monitor the assets most at risk of movement. So it costs over £6 million per year for monitoring only 1% of their assets. So due to the need for monitoring the health of National Grid assets and the expensive cost of their invasive analysis to monitor their assets, National Grid defined a project to use INSAR for monitoring the stability of their assets with at much lower cost and without need to physical access to the assets. So National Grid defined this project and delivered to Spotted to answer these questions. Could a synthetic corner reflector be sized, designed, and installed on assets, such as towers, such that the asset itself becomes a radar reflector? Could a team find National Grid energy transmission assets that can be selected as natural reflectors in selected NGET sites? And question 3, could more than one synthetic radar reflector be installed on a single asset to get multiple asset motion readings from a single asset, for example, to measure the asset motion of each tower leg or each corner of substation? So in order to answer question 1, we designed corner reflectors for NGET assets. In the design phase, we had these assumptions to have sub-centimeter uncertainty in displacement and having signal to clutter ratio equals to 10 decibel for a typical UK rural landscape away from woodland. So these assumptions, using these assumptions, we designed trihedral corner reflectors with a size of inner leg as 70 centimeters. So we also had some special adaptation for installation of the corner reflectors on electricity tower, including mounting for ease of installation to tower and alignment of the corner reflectors towards the specific satellite descending tracks. Also, we installed nets over the corner reflectors to prevent it get filled with debris. Also, we designed drainage holes to prevent it get filled with water. And also a small chain between the corner reflector and tower to prevent falling. So the first test site was NGET D-site test site in the UK, in which we had 2 test towers. So first we installed the first test corner reflector on Tower 1 on 2nd of November 2022 with 100% clear view towards the Sentinel-1, descending Sentinel-1 track. It was track 154. And the second test corner reflector was installed on Tower 2 on 7th of December 2022 with 0% clear view towards the satellite, which was obstructed by the body and arm of the tower. These pictures show the installed corner reflector on the 2 test towers in the NGET test site, in the D-site test site. Before looking at the SAR data, we did some pre-processing steps or some processing steps. So we downloaded Sentinel-1 images of track 154. We downloaded 3 images before installation, 6 images after installation, and 1 image after removing the corner reflector from the tower. And all of the images co-registered with respect to the first image after the corner reflector installation. And all of them geo-referenced using a high-resolution LiDAR DM. So if we look at the SAR image in the area of the installed corner reflector, for 1 image after the installation on the left-hand side, and 1 image before the installation in the middle, we can see the bright signal coming from the corner reflector on the tower on the amplitude map. And also, if you look at the amplitude time series of that pixel, we can see more than 1.5 times jump in amplitude after the corner reflector installation, and a significant jump of corner reflector after removing, the drop of the amplitude after removing the corner reflector. We think that if we install a bit larger corner reflector on tower, we could have a more strong signal, because in the design phase we assumed UK typical rural background, which is a bit different from the site test site, which was more cluttered and having urban structures. And as we expected for the corner reflector 2 on tower 2, there wasn't any specific clear signal or jump in amplitude value because of the obstruction made by the body of the tower. Also, in order to investigate the impact of corner reflector installation on PS selection of a PS INSAR analysis, we applied a conventional PS INSAR analysis using SAR-PRUS and 13 Sentinel-1 images after corner reflector installation and 15 Sentinel-1 images before corner reflector installation, both from the same descending track. So on these two images, you can see the selected PS pixels over the temporal average of amplitude. So on the right-hand side after the corner reflector installation and on the left-hand side before. So as you can see, we've got selected PS points at the position of the corner reflector after installation, while we don't have any selected PS pixels in that area, I mean inside the green box. So it means that installing corner reflector on a tower can help us to detect as PS pixels in the PS processing and then monitor its stability. Also, this is a velocity map of the very small area, and we looked at the amplitude time series and deformation time series of the same pixel. And as you can see, there isn't any specific deformation event for that pixel. And in order to answer question 2, we did a PS analysis using SAR-PRUS and Sentinel-1 images in 3 different NGT test sites, which includes the line of towers and also substations. You can see here on the left-hand side, as an example, the velocity map result of one of the sites. And the result of this experiment confirmed that some of the towers can be natural radar reflector and selected as PS pixels because of their orientation relative to the Sentinel-1 satellite, and some of them can't. And as we showed, installation of a corner reflector can be helpful to be selected as a PS pixel. In order to answer question 3, we installed 3 corner reflectors in a L-shaped format in an open grassy area on the Cranfield University test site. And we implemented 3 different layouts for this L-shaped format to make the corner reflector closer and closer together in both along track and across track direction to find the minimum distance between 2 corner reflector that still can have 2 distinct signals from the corner reflectors. So we did a similar processing on the SAR images, this time from another descending track, 81. 3 images before installation, the corner reflector, and 1 image after each layout installation, all correlated with respect to the first image after the first layout installation, and georeferenced using a high resolution LiDAR DM. So as I mentioned earlier, we implemented 3 different layouts in an L-shaped design. So we kept the central corner reflector at the same location in each layout, and then decrease the distance between the corner reflector in along track and across track direction to achieve what we wanted. So in the first experiment, we put the corner reflector with 60 meter distance from the central corner reflector in along track direction and 20 meter distance from the central one in across track direction. So if we look at the first image, amplitude image of the first image after the first layout, which we named I1, and compare it in the same area before installation, we can see three distinct signals related to the three installed corner reflectors. Also, we looked at the amplitude time series of the three corner reflectors. As you can see, after the installation of the corner reflector, there is a significant jump in the amplitude value. In the second layout, we kept the central corner reflector at the same location and decreased the distance of the corner reflector in along track direction to 30 meters, and also put another corner reflector with 10 meter distance from the central corner reflector in across track direction. And again, if we look at the first image after the second layout, which we named I2, and compare with the image before any corner reflector installation, we can see that we can say there are two distinct signals in along track direction, but sounds the signal in across track direction starts to overlap. So if we look at the amplitude time series of the two corner reflectors located in along track direction with 30 meter distance, we can see a jump of amplitude at I2, which is the image, SAR image after the second layout. On the left-hand side, you can see the amplitude time series of the central corner reflector. So that's why we've got jump of the amplitude at I1, I2, and I3. Okay, sure. So if you look at the amplitude time series of the bright pixels between the central corner reflector and that one located with 10 meter distance in across track direction, we can see for all of them there are jump of amplitude at I2, but for one of them this jump is larger, which is related to the corner reflector located with a 10 meter distance in across track direction. So it means that the signal between the two corner reflectors in across track direction start to overlap. And if in the third layout, we put the three corner reflector only in across track direction, kept the central one, put one of them with 5 meter distance and another one with 10 meter distance in opposite direction. If we look at the image I3, which is acquired after the third layout, we can see the signal of this corner reflector is overlapping. So we looked at the amplitude time series of the bright pixels between the central corner reflector and that one located with 10 meter distance. Again, we can see a significant, we can see jump of amplitude at I3 for all of them, but for one of them, this one is more significant, which is related to the corner reflector installed with 10 meter distance. We also looked at the amplitude time series of the central corner reflector and that one with 5 meter distance, and for both of them we can see significant jump of amplitude at I3 and the signal overlaps. We also looked at the RGB color composite analysis using the images acquired after each layout. I1 as red, I2 as green, and I3 as blue. This helped us to reassure the location of the central corner reflectors with white color. The corner reflectors located in along track direction in the first and second layouts with red and green color. And in the bluish area, the pixels affected by the corner reflector installed in the third layout in across track direction. So as conclusions, we showed that synthetic corner reflectors can be designed, installed, and used for monitoring of displacement of NGT assets. Some NGT assets like towers can be natural radar reflectors because of their orientation relative to the Sentinel-1 satellite. Design of a larger corner reflector, like with 1 meter inner leg, or an array of small corner reflectors and installation on the NGT towers would improve the signal strength. As long as the spacing is more than approximately 30 meter along track or 10 meter across track, the corner reflectors should be visible as distinct targets. This translates to 1 to 2 corner reflectors per tower, but multiple corner reflectors per substation. It is recommended to investigate how practical could be installation of 2 corner reflectors on an electricity tower with regards to the size of the tower to still have 2 distinct signals for future study. Thanks for your attention. Happy to take any questions.
I think we're running a little bit behind, so unless there's any urgent questions, maybe we could save them for the end. Right, and then our next speaker will be Otmar Frey.
Thank you. Good morning. I want to talk about some activities we have been doing over the last couple of years, and specifically an extension of that on a car-based radar, SAR and INSAR, also from the drone. So you see some pictures here on the title slide where you can see implementations of a L-band SAR system for a repeat pass acquisition. And the main idea is mobile mapping of surface deformation. And I will start out with a quick recap of what we have been doing, mainly with the L-band, and then the extension is basically that we try to do that concurrently with L-band and KU-band. So this is still work in progress, as you will see, with some first results. So the implementation of that sensor configuration, including a KU-band system, and the L-band system is on the right-hand side here. Sorry. So do a quick recap, then show you a bit the motivation, why we do L and KU-band concurrently, and show some first results on this simultaneous acquisition, and do a summary and outlook. So we have been doing a couple of demonstrations of this L-band based, the INSAR for surface displacement measurements based on a car, or also with drone experiments. So you see that sort of a summary slide here. I'll pick one of them to show a bit more details. So this includes surface displacements, a landslide in Switzerland, glacier movements. We also did some tomographic tests with some opportunity baselines that we got with the drone-based acquisitions, which I'm not showing here. So this was already shown previously. I just keep this one here for basically showing you, those who haven't seen that yet, how this system works. So we're driving by on a site, on a car, so we need a road. So that's the main disadvantage with this approach, of course. So if you have a road in front of a slope, moving slope, you can use this system. We're driving by, typically taking synthetic capture of a couple of, let's say, 50 meters, 100 meters, 200 meters. And with that, we can produce a high-resolution image, also at L-band, and do this repeatedly to get displacement measurements. This is, I hope this is running if I click here. Yeah, so this is a short overview for this specific site with the data products, so like processing chain to obtain the displacement map. So So this is a quite fast-moving landslide in Switzerland, which became more famous in June again because a massive collapse happened. There's a small village close by, so people had to be evacuated. Our measurement is from 2020, so when times were still a bit safer, but already fast-moving. So you see displacements within 4 days up to a couple of centimeters, so it's really fast. So this is the L-band case. So why now L and KU band? So there are several reasons. We think with the L-band system, we have basically successfully demonstrated that we can do mobile mapping of surface displacements. So this is a nice complementary tool to other systems. And there's also in-house, but in other companies or like providers as well, of course, KU-band systems that are stationary or quasi-stationary that are also established to measure surface displacements. So now KU-band doing SAR would be an advantage in terms of getting higher resolution if you're further away, so to complement a bit this resolution loss with the stationary systems. And if we can operate it simultaneously from the same setup on the car, we can, of course, try to benefit also from the 2 different frequencies. There's for sure different temporal decorrelation times and displacement velocities, sensitivities with the 2 systems. And we are also interested in just the technical aspect of it because KU band, the INSAR is of course challenging, as we also see later. Is a technical thing we want to tackle because we want to be flexible in terms of having different frequencies for agile platforms such as these. So this is the system we are using. So it's this L-band SAR system, an in-house development, and we are kind of abusing the gamma portable radar interferometer as a SAR system. So you basically have the same back end in terms of the radar, but instead of these long antennas that are rotating, which is the usual setup, we have horn antennas, as you can see here, mounted on the car that we can operate simultaneously with the L-band system. Just a few words on the system characteristics. Both systems are FMCW radars. Technically, both are capable of doing 200 megahertz bandwidth. The thing with the L-band system is that we are not allowed to transmit more than 100 megahertz bandwidth in Switzerland, I think in many other places as well. But technically, you could do also 200 megahertz bandwidth to get a range resolution close to 1 meter with some windowing included. Then, of course, the azimuth resolution depends on your antenna size technically, but in our case, often we don't drive like a full synthetic aperture, so it depends still on the range distance if we go further away, depending on our configuration. So this is also still a bit variable depending on our setup. So this is the first site where we started to do combined L and KU band measurements. We thought it's a nice site. It turned out to be like suboptimal since it's a super steep one in terms of the geometry. It's in the Swiss Alps, and there's actually also some monitoring going on the side with the stationary system with long-term monitoring. So here again, you see just the way we operate the system. So we drive by repeatedly a couple of times every time we're there, but of course also then come back later in time over a couple of months, and we try to build up a time series like this. So I want to start out with some coherence images of that site. So basically, this is a top view of the situation. The car will be driving this direction and viewing towards the slope here. So that's the steep slope. And below, there's a bunch of trees. So to remind you, it's not the same extent. So the KU band is kind of blown up a bit compared to the L band in this view graph. So these trees here correspond to that section down here. The extent of the beam width is different, both in elevation and also in azimuth. That gives a slightly different viewpoint. So the L band system has a 40-degree beam width, so quite large beam width, whereas this is much less in the KU band case. Yeah, so clearly the the sensitivity is quite different. So this is a very short interval, 4 minutes. You can see that with L-band you have a very, very high coherence, even in most of the vegetated area, whereas this is of course not the case in KU-band, but still in the rocky area you get a substantially high coherence, so over a very short time. So this confirms that this is okay for repeat pass, but of course it will be different for longer times, as we will see in a minute. So this is the phase, so I didn't really further process that. So you see in L-band it's fairly stable, so there should be no movement within this short time, whereas in KU-band we see some artifacts which still are in the processing. So this is just like out of the box, no corrections applied additionally, just topography corrected data. So now if you compare that 4 minutes with a period of 4 months, of course the situation looks much different. So I picked here a quite extreme case with acquisitions once in winter time, as you can see in the imagery here. And the same situation in summer with grown vegetation and no snow, of course. You can think, of course, that in terms of deformation, this is not an ideal time span in any case, because there's different characteristics. But just to look at the coherence, we can see that, of course, with L-band, we still have substantial coherence, whereas it goes down really dramatically at KU-band. So where you can really see the different behaviors that are expected, but I think are nice to have as a complementary tool with L and higher frequency systems to actually be able to measure the different characteristics of surface displacements and decorrelation. So we have then ongoing campaigns. Actually, this is almost in the same area, a bit further up the valley. So in this area, as in many valleys, the upper parts and several instances are moving in one or the other way. This is basically the first measurements we did at this site. So at this time, first try also with KU-band, which did fail at this specific time. So this is between 21 and 22. So also quite some time in between, so half a year. And you can see that in this area, see a picture on the right-hand side, there's quite a bit of vegetation. And then in the upper part, there's mostly a rocky area, but you still see, of course, a bit of snow as well, so where you have decorrelation areas, and also areas with debris that is decorrelating much faster. But you can nicely see the different characteristics of the coherence with this L-band system over the different land cover, and still giving you quite a bit of coherence also in some of the vegetated area over such a long time period. I just picked, or actually a colleague, Rafi Gadouf, who's a co-author of the paper and was measuring with me a lot over there, has picked a few close-ups in the upper area. So this is taken from somewhere up here. And this is just to highlight the nice feature about the resolution we get with this L-band system. So even like a couple of kilometers away, you get substantial resolution to actually see features. So here is a debris area where you have much more decorrelation than in the other area next by, and potentially there are also some deformation patterns than visible, but in this case it's mostly decorrelating because there's too much change over time. So now this is, as promised, now really this concurrent L and KU band imagery from the same site. So this is also to show you a bit the different extent of the imagery that we see. So on the left-hand side, the L bands are, as I said, it's 40 degree azimuth beam width. So we get quite a wide view, even though we're not driving a very long distance. So in this case, it's something like 100 meters, and the road is actually a bit curvy. And you see that also this leads to some, let's say, variation in the backscatter. This is not corrected here. In the KU band case, you can see that really nicely. Yeah. What you also see is that for KU band, we have substantially higher resolution. This comes, of course, by the twice as much bandwidth in range, but also the azimuth resolution is better, and depending a bit on the situation of the geometry, of course. So now looking at at some phase and coherence for these imagery. So I picked a few. So we're starting to build up a time series, as I said. So we were like measuring like 3 times now, like with half-year intervals. And of course, every time we're there, we also do a couple of measurements. So this is a time span for the L-band data of 1 hour and 17 minutes of the same area. So where you see the coherence and the phase on the left-hand side. Again, here the phase is not further treated, so this is just topography correct that we process directly to the digital elevation model using a time domain back projection approach, using accurate navigation. So this is basically what comes out of that, then doing just the interferogram, so no other phase corrections applied so far. Then the same thing for the KU band imagery, and you can see, of course, I flip forth and back a bit here. The dramatic difference, of course, in the coherence for this particular area, because the lower parts here are vegetated areas, so forested areas, but you can see that in the upper parts, in the rocky areas, you get still very good coherence, and of course, some phase patterns. So there's you see a good phase measurement, but of course, it's not something you can use directly for deformation, so there's a lot of work to do. I think it's mostly related to already atmospheric, but also, of course, maybe some remaining baselines that we have since we're driving on a relatively narrow road. We have a more or less okay repeat pass, but still, of course, it's not perfect zero baseline. And then you get easily some fringes, and there may also be some still motion-induced areas that need to be corrected. So didn't check for that for this particular case yet. So now looking at the longer time span, or 4 months, for this side here, as you see that for L-band, as previously, we have still quite a nice coherence, and also the phase looks very smooth, so this is easy to correct. Also not corrected here is, of course, not displacement, but mostly atmosphere probably. But this is not problematic to correct. So this is similar as what we had to do for this Brienz landslide case, where we can easily correct that and then actually look at displacements. Okay. So this is the KU band case, and I switch forth and back again here. So you can see 4 months here in this case is very low coherence, of course, a KU band in the vegetated area. There's still some phase patterns that you can retrieve in the upper parts of the rocky areas, but the coherence is also pretty low there. This is partially due to different characteristics still, because one of them is in June and the other one is in October, so there's a good chance there had been some snowfall in between already, so there's also natural cause for that. Then coming back to let's say the October within 1 day, 17 minutes, so very, very short time span, just to have a look at this as well, because that looks much nicer for KU band and shows complementarity. So L band is a very clean phase, super high coherence. Everything looks great, and also at KU band, you have quite a good coherence, except of course in the forested areas, and the phase pattern in this case also looks a bit smoother, so probably less atmosphere in October. So this is something we can work with, but it's of course a start into this direction. So to summarize these activities, we can do high-resolution repeat paths, the INSAR from Agile platforms at L-band for sure. So this is operational, you could say. We need a decent INS GNSS. At KU band, we are sort of on track, but not really there yet to really use that as a tool. But we believe this is something we can get working for specific applications, complementary to the L-band case. We get good SAR focusing quality with our approach. High resolution imagery, so I think we're on track there. There's still some work to do with the KU band to do some residual corrections. The behavior is as expected, so this is not big news there, but I think it's a nice tool to have and actually to have the two frequency options to do some measurements, different characteristics in terms of decorrelation and displacement sensitivities. Just a bit of outlook. So we're working further on building up this time series and doing tests, also with different people interested in that, towards developing services in this direction as well. And on the development side, there's also a development led by Charles Werner, which is downsizing the L-band system so that it can actually be put on smaller drones, not such a large one as we were flying. So total payload will be below 8 kilograms for quadcopter drones and also other platforms. With that, I would like to close, and thanks a lot for your attention.
Thank you for the nice presentation. Time for one quick question.
Hello. I saw in the Q-band image that the intensity of the Q-band image in the middle has a drop in the intensity. Could you?
Can you speak louder?
Sorry. In the image, I don't remember the number of the slide, but in the intensity image of the Q-band radar, I saw that you have it seems like there is a slight drop of the intensity in the middle, like in the middle of the valley, of the mountain. Sorry. Do you have any explanation for this, or?
Yeah. So I mean, this is the road is quite curvy. So and we don't really correct we don't really correct for everything in that sense. So we do like a weighting in terms of how fast we drive. But if you're really rotating the antenna a lot, then yeah, this is what you see there. So with the L-band, it's less pronounced because the beam pattern is more graceful, let's say. Yeah.
Thank you.
Maybe if you scream, it's still possible. Yes. So this is, you can actually check because it's, since a couple of years, it's available for everyone. So it's by the Swiss Office of Topography. It's a dam that is originally based on LiDAR dams, LiDAR acquisitions, but it's also updated with optical photogrammetry. This one is probably 1 meter spacing. So originally it was 2 meter spacing. This is even better now, so they upgraded. I'm not exactly sure. So it's pretty good. Elevation should be, I don't know, around 1 meter, depending, of course, on where you are. So it's pretty good digital elevation model. And it's also something you actually need, of course, to get good results.
Thank you. I think we need to move on now. So I'd like to welcome our next speaker, Manuela Bonanno.
Okay, good morning to everybody, and thank you for staying here so long before lunchtime. So today I'm going to talk about the main results that we have achieved through an extensive national scale INSAR processing made through the full resolution parallel small baseline subset approach. For the analysis, investigation of the deformation phenomena relevant to the built-up environment, relevant to the main Italian cities of the Italian territory, for sure. This has been done through the exploitation of HPC infrastructures, in particular GPU parallel processing techniques. And the main results I'm going to show you are relevant to the exploitation of large multi-temporal SLC data stacks relevant to X-band Cosmos Schema datasets, but I'm going to show you also the preliminary first results relevant to SAOCOM-1 data. L-band SARCOM data. So we will just say a few words about the full resolution piece bus processing chain. We will focus on the parallel implementation. Then we will move on the experimental part, so the results achieved on some of the main Italian cities. There is no room to talk about in details about the overall results we have achieved, so we will focus on some representative case studies, and then we will move on the developments. I have, there is no time to talk about, and there is no reason to talk about the advanced NDSR technique relevant to, called small baseline subset, because I'm pretty sure that you know the capabilities that are well demonstrated over the last 20 years for this very important DINSAR approach for detecting deformation relevant to both natural and anthropic hazard scenarios. Basically, we start from a large stack of SAR images that are properly combined in order to generate a large number of small baseline, small in time and space interferograms. They are combined together and inverted in order to get two main products, the mean deformation velocity maps, and for each single covariant pixel, the deformation time series. But one key point of this bus approach that is the core of my presentation is the fact that this bus can be applied in two different spatial resolutions. The medium spatial resolution and the full spatial resolution that exploits multi-look and full resolution DINSAR stacks, respectively. The first one, the medium, exploits multi-look interferogram and analyzes deformation phenomena relevant to large areas, so regional scale analysis, in particular volcanic seismic events, while the second one, which is the focus of my talk, will be exploits full resolution data stacks and is able to detect localized displacements relevant to single buildings and infrastructures. This is the simplified block diagram of the full resolution bus DINSAR technique, which basically consists in four main blocks. We start from two stacks of DINSAR interferogram, the full resolution interferograms, and then we exploit also all the low pass components coming from the low resolution piece bus processing, which are relevant to deformation, orbital ramps, and atmospheric phase creams. They are put together and subtracted modulo 2 pi to the full resolution interferogram in order to get what we call HP I-pass residual interferograms. Then the residual interferogram, HP, the residual interferograms are based on two different phase components, linear and nonlinear phase components. For the estimation of the linear phase components, we exploit a model, linear model, through the phase unwrapping step performed on the second block, the central one, the heaviest from a computational point of view. And the linear phases components are relevant to the velocity, the topography, the residual topography with respect to the DM, the thermal dilation, which is basically associated to metallic infrastructure, and whenever available, we have also some the azimuthal position, which depends on the availability of various Doppler centroid on the data stacks. So we retrieve these linear phase components through the phase model, and once found these components, they are modulo 2 pi subtracted to the HP residual interferograms in order to get the nonlinear phase components. Okay, this one. And the linear phase components are, the non-linear phase components are assumed to be already unwrapped, so we don't need to apply another phase unwrapping step, and so we just can go to the inversion of the system and to find the HP deformation time series. Once found the deformation time series, we can sum up all the linear, non-linear, and low-pass deformation time series in order to get the full resolution deformation time series. Okay, So this seems to be quite straightforward, but for sure we need to face some drawbacks related to the very large increase of the available data stacks, full resolution stacks, both in terms of number of images to process and number of pixels to process because of the size of the images. So we have to face about the problem relevant to the exponential growth of the processing time and the consequent data processing load and complexity. So to face this problem, we need to adopt advanced HPC solutions, infrastructures, and in this case, we adopted mainly the GPU power, the GPU-based parallel solutions that are particularly important in the central blocks, the red and the green one, because they are, as I anticipated, they are the heaviest from a computational point of view. So they are also characterized by a pixel granularity. It means that every single pixel can be implemented, can be solved in a separate way. So they are particularly suitable to be used with the GPUs-based parallel solutions. And so in this case, we speed up the processing and we move from weeks of processing to, let's say, a few hours to process the overall full frame, getting high scalability and the computing performance without losing the accuracy of the algorithm, because we didn't modify the algorithm, but only the implementation, moving from CPU-only based to CPU-GPU based. And so on one side, we have the parallel techniques, the HPC infrastructure. On the other side, we need to have data, so very high resolution data. And in this case, we can fully benefit from the availability of X-band Cosmos Skymed, the first and second generation data set all over the Italian territory through the Map Italy project. In this case, we had 4 satellites of the first generation. Unfortunately, one, CSK3, we missed one satellite in October 2022, but thanks to the availability of the recent 2 satellites of second generation, we can go on with the processing and make very long-term deformation time series, benefiting from the overall data set starting from 2009. And so we here move to the experimental part. So we are going to show the main results that we have achieved throughout the Italian territory by exploiting full resolution piece bus analysis and Cosmos Skymed first and second generation dataset. For sure, we don't have space to talk about in details of all the deformation phenomena that we have achieved, but we can just zoom in some particular specific test cases that are representative to our analysis. So let's start with the first data set, which is our favorite one, the Napoli Bay Area, because we live and work there. So we are also center of competence for the Italian Civil Protection Department. And in this case, we continuously monitor the Campi Flegrei caldera. We can see here the different behaviors seen from ascending and descending orbits because of the east-west deformation components of the caldera. But in this case, we are not interested. Here we have an example of the uplift of the last 13 years of the deformation of the caldera, Campi Flegrei caldera. But in this case, we are more interested in analyzing the formation relevant to the built-up environment, so localized displacement. And now we are going to zoom in some specific cases. For example, here we have the connection of the high speed with the Napoli rail station. And we can see the plot relevant to the deformation time series that we have achieved through CSK-CSG datasets. I have highlighted in black and red the triangles, the different data, just to understand the perfect overlapping between the acquisition and the capability of continuously monitoring the dataset, the investigated phenomena. Here we have another example on the northern part of the Capodichino airport. In this case, we don't have a linear behavior, we have a non-linear behavior with a lowering of the deformation up around 2016. Here we have, let's move to another data set in Roma, central Italy, the capital of our territory, and we have exploited both ascending and descending orbits, always for a civil protection department, within the agreement between IREA and civil protection department, but in this case with another intent, that was the writing of the guideline for the use of DINSAR measurements for the good interpretation of the deformation for built-up environment analysis. In this case, we can retrieve many different deformation phenomena, for example, the Roma Fiumicino Airport subsidence, the almost linear deformation pattern of the Grande Raccordo Anulare, we can see due to the compaction of the soil in that area that is coming to the infrastructure. Another, in this case, non-linear behavior due to the thermal dilation of a metallic structure in the central part of Rome. Or for the descending orbits, the deformation path of the Roma Fiumicino Airport. We can see the clear non-linear behavior. Now let's move to a northern case study, Venetia, that is particularly important for its heritage, so cultural and historical heritage. For the island, main island, we can see the fish-shaped island. We don't see any clear deformation behavior, but if we zoom in, we can see some spot of deformation in specific structure or single buildings. Here, the case of the hospital close to the northern part of the island. But here, for sure, we focus on some infrastructure, big infrastructures. We have the MOSE, that is the connection between the island and the Adriatic Sea. And we can see very important deformation behavior, so some point of the structures. And now we have to analyze also not only cities, main cities, but also small towns, for example, La Spezia, that is particularly interesting for after the collapse of the river bridge Magra, occurred in 2020. And so for this one, we have investigated both ascending and descending orbits. And we can see the different behavior, blue and red, due to the presence of east-west components and due to the deformation relevant to the landslide. The body of the landslide is pushing towards the right shoulder of the bridge. And we assume that this kind of behavior, this kind of movement is the responsible of the uplift of the bridge and of the failure of the bridge, as we can see in this picture. And the last case, just to go throughout the Italian boot, so from north to south, the Catania case study, we can see the clear behavior relevant to the Etna, Mount Etna volcano, but also in this case we are more interested in some localized deformation, as in this case the Catania Harbor. So, many cases where the X-band satellites works very fine and many deformation phenomena that are detected, but we have also some cases where X-band is not completely useful to detect the deformation, as in this case. Here we have the Ponte della Musica bridge, and we can see that the bridge, the deck of the bridge is blind, so X-band is not useful, is not capable to detect the deformation. Maybe because of some strong deformation behavior or some vibrational effects. We don't know the causes, but we decided to move on L-band investigation through SAOCOM 1 constellation. That is the Argentinian constellation in cooperation with the Italian Cosmos SkyMed and Italian Space Agency. through strip map data with 5 meters of spatial resolution and 23 centimeters, we made a processing on the same area. For sure, in this case, the time frame is different because it's only 3 years, 2020, 2023. But we can see that the deck is full of points, and we can also detect some deformations relevant to the thermal behavior of the bridge, of some metallic structures of the bridge. And so we have been encouraged to move on, and these are the very recent results with Alban SAOCOM 1 data on the Napoli case study. We showed these descending orbits just to make a comparison between what we get in Cosmos SkyMed. We can see that this area, this red area that is corresponding to a trash loading. We can see here the zoom-in view, okay. It was not possible to detect through Cosmos SkyMed, maybe because the deformation behavior is quite big. We are talking about 25 centimeters in almost 3 years. So maybe because of the phase unwrapping problems, X-band was not very good. And in this case, L-band can give us a very big help. So moving to the conclusion. Before concluding, just further developments relevant to the new planned X-band constellation throughout within the PNRR framework. Italy is going to launch in 2026 a new constellation of X-band made of 10 satellites. But what is very important in this case is that we are not talking about sun-synchronous orbits, but we are talking about medium inclination orbits. We can see here the main characteristics. So thanks to this characteristic, IRIA CNR started some simulation on these data sets. And for example, we made a simulation considering 6 satellites with a medium inclination orbit of 49 degrees. And 6-day repeat pass, and these are the results. So we can get some more information on the deformation, also because we can get some information relevant to the north component that at the moment is not easy to detect with sun-synchronous orbit. So this can be very encouraging for us for getting in the future, maybe by benefiting from both CSK, CSG and IRIA data, also to get the full 3D deformation field of, for example, the Italian territory. So we are waiting for the new constellation, and meanwhile, thank you very much.
Thank you for the presentation. One question.
I just didn't catch it on your last slide. You had the 10 satellites. You had 6 plus 4. Was that 6 sun-synchronous and 4 mid-inclination? Is that the distinction?
This one are medium inclination?
Yeah, like the top bullet says 10 satellites, 6 plus 4. What's the difference between
No,
the 6
they are
and the
all
4?
medium inclination orbits.
They're all mid-inclination. Okay.
Yes, they are going to be planned in this way. The difference is because they are going to launch 6 in the next years, and then they are going to decide on launching also the next 4. But the overall system is medium inclination orbit. At least what they are going to, they are planning.
Okay, thank you.
It's a completely different idea because we need to get some more information on the deformation. And so we want to benefit from that.
Okay, I think we need, you have another question? Very quick.
The new, as you can see, is around 23-30 kilometers. But we can, the
The
coverage,
question
the ground
is
coverage.
all over the world? Or?
No, Italian. Sorry, I did the temporal, the ground coverage in the world. No, it's for now. Is for the Italian territory. There are some spot areas. Depends on because they are going to launch like a fixed number of satellites that cover the Italian territory. If they want to, if needed, they can move some satellites to other specific test sites, but they have to be. For example, for military reason or some other stuff. So, but the aim is the Italian territory.
Anyway, maybe this will be also decided
exactly.
in the future. You know, what will be the acquisition policy will be decided probably in the future.
Yeah.
Anyway, I think we need to close this session. Thank you to everybody, and have a good lunch.
Yes, yes.
Hello, good morning. We are right on time with the first session of the afternoon, so welcome. I'm Deodato Tapete from the Italian Space Agency, and I'm very pleased to co-chair this session with John Dance. So please, John.
Thank you. I'm John Dales with the Geological Survey of Norway. We have a continuation today of the displacements and deformation sessions with 5 very interesting talks lined up. And we're going to start off with Urs Wegenmuller for Gamma Remote Sensing, who's going to tell us all about his work with ISI.
Thank you for the introduction and good afternoon, everybody. So this work was conducted at Gamma Remote Sensing. I was supported by my colleagues Raphael Kadouf, Christoph Magnar, Nina Jones, and Dazio Strozzi. So, to give a little bit background, this work was performed within Eurostar's project with the name Ramon. The objective was to develop landslide services considering innovative elements. And these innovative elements included terrestrial radar measurements. You saw maybe the presentation just the second last before the lunch break with the terrestrial car-borne L-band radar, so we did such measurements. But then the element I will report here is to use novel satellite data, and at the time ISI was still a plan, and then during the acceptance of the project it became a reality with first satellites. So the idea is not to present really this project that I cited, but to share our experience with ISI and especially ISI interferometry. So in three cases I have nice data, and so this will make the main part of the presentation. So with differential interferometry and S-bus type processing over Mojave. Then a PSI test over a part of Tokyo in Japan, and S-bus test over a disco island in Greenland. But before moving to this quite nice examples, let me spend one slide on the relatively frustrating first 2 years of the project. So ISI started to launch satellites in 2018 with one in January and one in December, and then further satellites were added to this, and including in January 2021 the X6, which is very useful and is the one mainly used in this study, and you will hear why. So before 2021, with this X6 launch, the spatial baselines of repeat observations have been too long for differential interferometry. There was or is no strict orbit control to keep the satellites in a narrow orbital tube, and so we got plenty of examples to try, but sometimes it was 10-kilometer baselines or 1,800-meter baselines, and so you got maybe faint fringes in some slopes which are nicely oriented, so that you have the best chance to get a little bit of coherence. But overall, it was not useful data, and this changed then with X6. So it is still drifting, but because it's in a one-day repeat cycle, the drift is 200 meters per day, and that makes a reasonable and easily usable baseline for repeat pulse interferometry. So over the Mojave desert area, I used this as to look into some data characteristics. Backscatter and coherence, phase, height information, and displacement information could then also be retrieved. Okay. So I got a big stack of data, so 51 street map mode X6 scenes acquired in a period slightly longer than 51 days, and it's high resolution data with range and azimuth pixel spacings around 1 meter. And you see in this baseline time plot the drifting of the orbit, so it's relative to one date, and so you see it was about a 10-kilometer drift, and then I don't know if there was a maneuver or if this happened, it moved into the other direction and then again slightly back and then again in the other direction. So overall there were longer periods, long means 20 days and so on, when it was substantially drifting in one direction. So one consequence is, for example, that the temporal and spatial baselines are highly correlated. So you have to be careful when running two-dimensional regressions with such data. Here, backscatter image is shown. So it's actually not just one scene, but it's the average over all the scenes. And so the radiometry is then very nice, and you see very clearly in the section shown on the right. This is a very nice site because it includes a range of corner reflectors, I think managed by JPL. And so that's very useful to investigate some of the characteristics of the sensors, like the point target respond, which we did, of course, and found that spatial resolution is actually not much worse than the sampling, so it is really a high resolution data with about 15 dB in one dimension and 12 dB between the peak and side lobe level. Looking at the backscatter images already showed that somehow the contrast in the near and far range is very low. And this is also confirmed here in this coherence image. So again, an average over many pairs with less than 3 days intervals and shorter than 200 meter baselines. So you see, if you look carefully in the near range and far range, significantly lower coherence, and the signal noise is the reason for this. So the noise equivalent sigma 0 that we determined not in this scene, but in a more alpine scene where you also have radar shadow, so you can quite easily see the noise level there, was something like -16, -17 dB in the center, and up to -11, -11 to -12 in the near and far range, which is, of course, not so nice for quite some applications, and for interferometry it means some coherence loss. These are just examples of interferograms, so you see it works, you get phases and maybe also some phase ramps sometimes, so maybe related to processing or baseline inaccuracy, but overall you see nice phase images. So based on this, on having many pairs available, we determined on one hand terrain height correction to Copernicus DEM. So here on the left-hand side you see the Copernicus DEM, and on the right side the improved one based on the ISI stack. So the color scale is very fine between plus and minus 5 meter. So you see small details, so you see the height is a little bit noisy in the flat area, for example, in the Copernicus at 1-2 meter level. And you see that the higher spatial resolution of the ISI data helps to get a slightly better resolution. So some of the features, if you look carefully at it, are just a little bit more accurately represented in the updated DEM. And we were quite lucky that the time series also shows deformation phase over
wet part, so probably changes in moisture underneath resulted in some displacement, and so we could demonstrate that it's also useful, of course, such a dense time series to get information on fast displacements. So here it's in the order of up 2 centimeters over 67 days. We got then another stack, again quite many scenes over part of Tokyo, and so there we tried single reference PSI type processing. Now doing this with a very, very short total time period, you cannot expect to get a lot of deformation information, of course. But still, it's very interesting. So to get updated point heights, and based on the point heights, you can get a very accurate georeferencing, and you can check this by comparison, for example, with an optical background in Google Earth or so. So the plot shows that the scenes selected were nice in the sense that you had really uncorrelated spatial and temporal baselines. So that makes it a good data stack. And the rest of the images would be along one of the axes, just in one direction. And so that would not really improve it, but make it more delicate. And I jumped directly to the results. So you see here a lot of points. And if you look carefully at it, even more carefully than you can maybe based on what you see that the position of the points corresponds very closely. For example, you have metal structures above the road which are at several meters height, and so because of this height, the georeferencing is initially wrong by some meters, but with the height correction determined based on the time series, they fall then exactly in the right location, and so it's really very precise georeferencing then. So the statistical height estimation error that you get from the phase standard deviation and the baseline set is 15 centimeters. And you can do other things like a coherence product. I'm always a fan of this. So you get also thematic information on the scene. So it's a combination of coherence, actually here average coherence over many very short-term interferograms over the area, then combined with the average backscattering and the backscatter temporal variability. And so you get this color image which corresponds nicely to land use. So you see fields, forest, water area in different colors. Then the test over Disco Island in Greenland. The site was actually selected as an alternative to having a Swiss alpine test site, which was our intention, but there was no coverage at all with this X6 satellite over Switzerland, and so we looked for a site with coverage and with fast displacement phenomena, and we knew from a project that we did with other data sets that in parts of Disco Island you have this situation, and so I acquired a stack of data over Disco Island for us. So we wanted to evaluate the potential for height differences estimation relative to Copernicus stem and displacement rates. So here you see the results. So the height corrections are quite substantial. So you see here a scaling plus minus 30 meters, and you have reductions of 30 meters in some parts. It's mainly melting of glacier ice, and then you also see some positive values maybe in the accumulation zones. So in a qualitative sense, it definitely makes sense where you see the differences. And on the right-hand side, you see the displacement rate. So the scale is between -2 meters per year and +2 meters per year. So it's determined on a short period. But to have a better feeling for the velocities, it's converted to a meter per year. And you see fast movements, and if you zoom in, you see also the high resolution really gives you nice details on some processes. So it's very useful if you have plenty of X-band data with short intervals. That's definitely great to work with. The features you see are glaciers, rock glaciers, landslides, maybe also some snow fields that transform. So the ISI data are well suited for differential interferometry, PSI, S-bus type processing, provided the spatial baselines are sufficiently small. The high spatial resolution of X-band time series with a short one-day time interval are particularly well suited for the mapping and monitoring of local millimeter to centimeter scale ground motion. So not millimeter, centimeter per year, but between the acquisitions. Drifting orbits and narrow swaths limit, nevertheless, strongly the applicability, so I can still not do anything in Switzerland, if I understand correctly. High noise equivalent sigma 0 values also reduce the backscatter contrast and coherence, and so should also be avoided in the future. So as recommendations, I formulate that operating the ISI satellites in narrow orbital tubes would strongly improve the INSAR applicability. And using higher gain antennas or increasing transmitter power would reduce the noise equivalent sigma 0, resulting in higher quality backscatter images and higher coherence. So all the applications, I think, would benefit. Okay. That's it.
Thank you, Urs. We have plenty of time for questions.
Thank you for your presentation. I have one question on your recommendation. So you mentioned recommending an orbital tube of less than 500 meters. So is this like an empirical number, or you actually did some calculation and come up with this number? Thank you.
This is more pragmatic. So if I have the choice, I would say 20 meter or 100 meter, but I can live with this bandwidth. I can easily live with 500 meter.
Yeah, thank you. One follow-up question is, I understand this number is also having to do with, for example, the life of the satellite, right? Because if you want to control the orbit, you need to burn more fuels. So on that side, do you have any considerations to balance between the lifetime of the satellite and the orbit tubes?
I think it's not my job to do this. But my feeling is just that the value of the data would be so much higher if it were with a well-controlled orbit. Of course, I'm quite interested in interferometry, and so maybe leaning more towards this as an important application, but also change detection. Many things benefit if you have shorter baselines and clearer signals, more contrast. So I think it's not recommendations that are uniquely for INSAR work, but also other applications would benefit. And I think the choice of applications which are pushed at the moment by ISI, that relates strongly to this limitation. So interferometry is not something pushed or something promoted, because it's difficult to do it with these satellites.
Okay, thanks. Thank you.
Yes, thank you, Urs. Great that you could share this experience with us. I was wondering the orbit quality, the orbit precision. Can you comment on that?
Yes. So it looked okay. I have to admit I did not list now the exact numbers, because initially that's an important thing we check when we get first data sets. So I cannot say now it's 10-meter geocoding accuracy but the phase trend, for example, may not be related to inaccurate orbits, but also maybe to processing issues. So maybe I have another image to that I can share. So with tracking, I get this azimuth offset on the right, and so that should not be like this. So there's other things we checked and which may be improved. But I think the orbit accuracy is okay. So we did not see fringes. I mean, maybe like slight orbital fringe, but I think that's okay. You have atmospheric phase in a similar manner anyway.
I was wondering, because you had the corner reflectors in this Mojave site, that you may do some calculations.
I mean, it was done, and each scene is, on one hand, georeferenced and also georeferenced to or co-registered to the other scenes, and so you get each time the number. I just did not list it, but it's not a very high number, so it's not like 50 meters wrong, the orbits or something.
Thank you, Urs. We will see you in a bit, actually, with your next presentation. So I now introduce Sigurian Johnson from King Abdullah University of Science and Technology. All slopes in Iceland are moving. I would say a quite reassuring message.
Yes, good afternoon, everybody. On the slide is sort of the conclusions. All the slopes in Iceland are moving, so we can go right to the questions. Any questions? No. The work I'm presenting is very much based on what Yunmeng Kao did when he was a postdoc with me. He's now in New Zealand. And the idea was just to look at Iceland as a whole. It's a very dynamic place. Everything is moving. I mean, there are glaciers, there are volcanoes, there are earthquakes, there are geothermal exploitation areas. It's diverging. It's the mid-Atlantic ridge. It's going 1 centimeter to the side. There are earthquake zones in the north and south. Basically, a lot of things are moving. So at this high latitude, you have a good overlap between neighboring sentinel tracks, and you can cover the whole country with 3 ascending and descending. And we did just sort of brute force approach, sort of. We just looked at the data, processed it in a sort of SPAS approach, processed lots of interferograms. We had some atmospheric or tropospheric corrections I will tell you about, and paid some attention to the weighting of our data. And then we estimate velocities, seasonal signals, combined tracks into different velocity maps, ascending and descending, and estimated the near vertical and east velocity. So a bit about the atmospheric processing. This is a code that Yunmeng developed. He calls it ICAMS. It's based on global atmospheric models, like, for example, GACOS. What we do differently is that we pay some attention to the stochastic variability of the atmosphere. We will make smarter interpolations between the sparse points of the model of the atmospheric or the tropospheric model outputs. And this makes a difference. We also do slanted path integrations instead of just using zenith delays. And here shows that it actually quite significantly outperforms all the programs like GACOS and PIAPS. And he presented this in a JTR paper about 2 years ago, and you can go on GitHub and try this for yourself, for your data. It works particularly well, of course, where the model outputs are good. And they're good where you have many weather observations to constrain your model outputs. But of course, where it's far away, it can also produce garbage like all these kind of methods. Now, just here is one example of a raw time series output. You see quite a lot of tropospheric noise with ICAMS. This is fairly well cleaned out. There is also still huge residuals due to turbulent part of the troposphere. So we pay attention to this by estimating the full covariance structure of each image, assuming that the sum of the variances is what we see in the interferograms. So here you can see just how differently they are weighted, and this helps to get better velocities and seasonal signals. Now, then we combine the tracks, produce a descending velocity map, ascending velocity map, and produce a near vertical. And here red is up. I like to have red, it's hot, like volcano, it's going up. So it's roughly 3 centimeters per year that Iceland is popping up at present in the middle, and this is mostly believed to be due to decreasing size of the Icelandic glaciers. Now, this is not the first time this has been done. Rowan and Sigmundsson did this a few years ago using a little bit less data. We are improving on this with more data, better tropospheric processing, full time series, full weighting, and we show that by comparing with continuous DPS that we get lower errors. We got this, I'm very happy we got this out earlier this year because also about the same time as we got this out, the European Ground Motion Service added Iceland into the processing. So you can actually see all this by just going to the European Ground Motion Service. And the rates are quite similar, but the way in which they do it is of course quite different. There's a lot of temporal filtering while we do spatial filtering, and we want to preserve the temporal variability. We are interested in when we have changes in rates, because this is often a signal of new activity and some interesting things geophysically. So let's look at one example of that. For example, there is an indication of acceleration of uplift. For example, if you look at these 3 points in the middle of Iceland, and you look at the time series, they're quite noisy because now I here reference them to a point maybe 200 kilometers away. And you see evidence for both seasonal signals. There's a lot of seasonal snow loading in Iceland. Has a magnitude of up to 2 centimeters per year. And then if you model it as a linear rate, the seasonal rate, this would be the residuals. And you see they're not flat, they're curved. And this is indication that there is some acceleration in the system. And if you model it with acceleration term, you it seems to indicate that the rate of uplift is increasing about 1 or 2 millimeters per year. So that's pretty substantial. And this is a bit surprising because when you talk to the glaciologists, there is not, the glaciers in Iceland are getting smaller, but there hasn't, during this time frame, there has not been a rate increase in ice loss. There was in the 10 years before, but not there. So we don't quite have a good explanation for this apparent acceleration in uplift. Now, if you go to the east velocity, red means west. If you're sitting on Eurasia, you see western part of the country moving. You can try to model this simply with some buried dislocations, shear dislocation, and opening dislocations. Pretty much mimic the plate boundary of Iceland. And then you remove it. And what is left is plenty of small-scale signals. They are due to geothermal areas which are being exploited. Pressure is dropping. There is volcanoes going up and down. There are lava flows which are subsiding. There are glacier edges that are deforming. And in Reykjanes, close to Reykjavik, there's a big signal due to recent volcanic activity. So we want to look a little bit in detail here. If you look, for example, in this area, which is outside of most of the area, where there are no volcanoes or major activity, and then you kind of stretch the color scale a little bit and drape it onto a shaded relief map, you see a systematic yellow to red hues. Here I reversed the color scale. So red means east displacement. So pretty much all east-facing slopes are moving eastwards. Pretty much all west-facing slopes are moving westward. It's not uniform. There are some hot spots, but it's pretty systematic. And it doesn't really matter where you look. And I mean, this comes from different independent data sets. If you look here in central part of North Iceland, which is quite mountainous, you see the same thing. You see a lot of westward-facing slopes moving west, eastward-facing slopes are moving east. And some hotspots clearly within. And this is often a rate around 5 to 6, 7 millimeters per year of near east velocity. And I mean, here close to the capital, same thing. So it's pretty much everywhere in Iceland you see this, maybe least here in the east that you don't see too much. And the reason for that is that the fjords are all east-west trending, meaning that the slopes are mostly north-facing or south-facing. So we actually don't see as well the slope motion on these kind of slopes. So look a little more into detail. If I focus here in the area close to the town of Akureyri in North Iceland, you see the same thing. You see a number of valleys. They are glacier kind of formed U-shaped valleys. You see a hotspot here. This is in fact a well-known landslide, very clear in the geomorphology. It is not moving much. It's about a centimeter or two per year, but it's clearly moving faster than the neighboring slopes. If you look into, let's look at the cross-section across these three valleys, and they are very beautifully U-shaped glacier-formed valleys with flat-topped mountains. And if you look at the east velocity here, and here is 0, you clearly see that all the east-facing slopes are moving east, and the west-facing slopes are moving west. And if you look at the vertical component, you see both sides are going down. But that's actually a smaller signal, and the reason is that I'm exaggerating here the topographic profile. In 1-to-1 ratio, it looks like this. So these are in fact not so steep slopes, but they are still steep enough to have these slopes going down. So how does this look in reality? So I show you a photograph on the map. It's sort of this arrow. I'm standing here and I'm taking a photo into this valley, and this is how it looks like. You see some farm in the foreground, and then you see these slopes. They are fairly gentle, they're fairly uniform, and they have a little bit of vegetation, not much, but they look like mostly consistent of fairly unconsolidated materials. So sort of gravels and soils in a mix. So I go to another location in one of these valleys. Here you can see it. So you have these fairly uniform kind of sloped valleys. And then if you look straight into the slope, you see something like this. You almost see flow structures here. You can see how these tongues of unconsolidated materials are simply approaching you. And they are moving. We see them moving by this couple of millimeters per year. And you even see the flow fronts. It's almost like creep. You see it happening. So it's maybe not surprising that just all these slopes are showing these kind of signals. There may be some frost-thaw cycles that it heats up and then comes down, and it goes a little bit further down the slope each time. What is maybe more surprising is that up here, high on the slope, it's also moving. And there you have not so much soil. You have basically exposed, horizontal, old lava layers. Most of Iceland is made up of piles of old lava layers, tertiary lava layers. And one would think they are stable. Why should they be moving? I mean, this is just solid rock on top of each other. So try to understand that. If you look at cross-section, you have a pile of lava flows. But what is interesting, you have these soil wedges. Due to erosion, you have these wedges of soil in between. So if you think about that, you're looking down with a radar down to this slope, you could get some reflections of these lava flows, which I believe must be stable. And then you have maybe some reflectors, some rocks, buried rocks in the soil, mixture of soil and gravel that could potentially be creeping in these soil wedges. And then you could have other rocks due to erosion, which would be rolling down and would be completely unstable and incoherent. So you could try to model this or simulate this in a way by saying, okay, in one resolution or one pixel, I have a number of scatterers. Some are reflecting strongly, but many are reflecting to my signal in a little way. So I use here a single-tail gamma distribution. I would say, okay, if you have a number of scatterers randomly distributed in my, this is a resolution element or my pixel, and I have these scatterers, and these are the stable ones. And then I have another random set of those that may be creeping somewhat coherently. And then I have yet another set of scatterers which are completely random. And then if you would like to look at the phase contribution, you would think that all these stable ones should have 0 phase with respect to some stable reference, while the ones coherently moving, maybe not quite coherently, but moving, would be having a similar kind of phase signature. And then the random ones go to a random location and random reflectivity and phase. And if you sum up these contributions, you would tend to get a coherent motion, but with a reduced magnitude, depending on what would be the ratio between the stable scatterers and the ones that are creeping. If they're roughly half-half, you would have a roughly half rate, while the random ones would not contribute. So I think this may, in part at least, explain what is happening higher on these slopes. So the bedrock itself is probably not moving, but these wedges in between. So you have like pixels which are partially moving and they show up. Back to this map, and one more thing I wanted to make. I was looking into this area because there had been some mud flows in this part of the country. Again, this peninsula shows the same thing. The east-facing slopes are all looking yellowish to red. There are hotspots. If you look at this hotspot, there's another well-known landslide which is of concern. because it empties into a fjord and could cause a tsunami if it gets destabilized quickly. And here's another one. We had here about a year ago a mud destabilization. I have here a photograph taken from above going across a road. There were 2 cars on the road when it happened and kicked them off the road. Luckily, nobody got hurt. And the question would be, was this something I could see coming? And this is clearly in an area where we have motion ongoing in the years before. Here's another location. It is a little bit similar. This was 2 years ago. This farm was hit by a number of mudslides. This is in an area which is located here. So this is roughly 8 or 10 kilometers from north to south. Here are these mudslides that took place mostly in one evening. And this is all happening in an area where we see motion in the years before. But these mudslides are not a response to a long-term creep. They are a response to a very sudden rainfall events that takes hours to maybe 2-3 days. And therefore, it's a little bit difficult to see if there is any acceleration. And in my noisy time series, I don't really see evidence for any acceleration. It's just steadily going on, this soil creep. And I can say, okay, so there's nothing there. I can say this slope is more likely to fail in a mudslide rather than some other slope. Okay, so with that, I just conclude. We see everything moving in Iceland. There's glacial isostatic adjustment, plate boundaries, geothermal fields, volcanoes, slopes, glaciers, you name it. Very widespread slope motion. I would say almost all slopes are seen moving. It's pretty remarkable. Faster motion on some hotspots, clearly, usually on landslides that we see clearly in geomorphology. And then we see these unconsolidated slopes moving all over the place. And even those that have exposed lava layers are moving. And I believe this could be due to some type of coherent creep in the soil wedges between the lava layers. And we do not see any clear speed-ups for mudslide failures. And I think, well, this is maybe not very surprising, given the nature in which these mudslides are triggered. So, with that, thank you for listening.
Thank you, Sigurjón. Are there any questions? Yes, please. Over there.
Thanks for the nice presentation. So I'm a little bit doubtful, actually, and the reason is closure phase. We observed very similar signatures in Tibet. I think Eric's postdoc processed a lot of data, ARIA, multi-locked interferograms, SPAS, very similar approach. And all the foreslope, backslope, everything was moving. So I'm sure if we look at multi-locked interferograms, worldwide, not only Iceland, everywhere is going to be moving. So at least I think some of this, maybe, I don't know if you guys have looked at PS analysis and full covariance matrix estimation, just to make sure that it's not closure phase.
Right.
So I wouldn't exclude it.
So I have not done a quantitative comparison, for example, with the European Ground Motion Service, but I mean, you see similar velocities all over the place in that type of processing as well. And I mean, I showed you near east and near vertical, but I mean, it is clearly, obviously, in the individual interferograms, if they're long enough time span. And then when you look at these slopes, I mean, at least the lower parts of them, it's not surprising. I mean, you almost see how the soil is buckling. Nobody has really understood how quickly this process is, but having it at 1 or 2 millimeters, 3 millimeters per year is maybe not so surprising. So, and I mean, there are places there where it's, I mean, we looked at correlation with slope, and of course there is some, but I mean, it's still no clear correlation with slope. Some fairly gentle slopes are moving faster than other slopes which are steeper, and there are also slopes which are in fact not moving. So it's not like it's, I mean, initially we just thought it was, I mean, a few years ago we just thought it was a processing artifact or something. We were looking at tectonics, but I mean, it's clearly there.
Thanks.
Are there other questions? Yes. Up there. Yep.
Wow, that's high up. Get your exercise.
Do you have any ground-based validation of these signals by GPS or ground-based radar?
Yeah, no.
No.
No, I mean, we do a lot of GPS, but we always put it in really solid bedrock because we want to measure tectonics. But I went to visit this area, these valleys, this last month, and took some photos. They were just, these photos were better than mine, so I used those. And I was thinking about putting down some stakes or something like that. But I had my old parents with me, and they wanted to go home, so I didn't really have time to to do all the things I wanted. So next summer, I think we need some ground truth.
What do you think? What's the reason for this movement? Is it there forever, or is it related to permafrost thawing?
Yeah, so that's a good question. I mean, one might argue this could potentially be increasing in recent time because we are losing permafrost in Iceland above certain elevation. But most of the things I showed you are in fact below the permafrost threshold. So I think it's just the ongoing erosion that you're seeing. I mean, this is of course not a very fast motion, but you have rocks rolling down, adding to the soils and breaking down and adding to the soils, and then the vegetation builds on these lower slopes, and then it just creeps to the bottom of the valley. So I think it may be amplified, particularly now if you have years in which you have a lot of rain and the soil moisture increases. We try to look into that a little bit. We do see some variations in some places, but not systematically looked at it enough. But I think it's just, there's nothing new here. I think this is just a natural process which has been ongoing for centuries.
Thank you, Sigurðin. Let's move to the third presentation.
Our next presentation will be from Sida Shabica from TTC. Apologize if I've said your name wrong. And she will be talking about tools to use European ground motion data to find more information from them, usable information.
Thank you. I'm not Saide, I'm Anna Barra, sorry, but Saide couldn't attend, so I'm the second one. We are all from CTTC, and so I will present the work. So I will start contextualizing and motivating the objective of the work. Then I will present the methodology from EGMS to generate potential damage maps. And we will see that we have two approaches, the active deformation area approach and the building-wise approach. They will be presented through showing some results in Spain, in Granada region and Barcelona municipality, respectively. Then I will point out some remarks and conclusions. So the context, as we all know, the availability of displacement maps that are generated based on satellite interferometry is increasingly strongly, and also mainly also with ground motion service at regional and national scale. And since 2022, we have the first continental ground motion service, which the European one. And as we have seen, it gives us a reliable displacement maps based on Sentinel-1 data. And so we have billions of measurement points, which gives us information on displacements with millimetric precision. The important aspect is that it is totally free and open to anyone that can visualize and download this data. So these maps are going to be updated annually. So it is valuable information that allows to detect natural and anthropogenic ground motion phenomena. Also over having a global overview, but also reaching the detail of single structure and infrastructure. By the way, this huge amount of information is underexploited because mostly over wide areas, the analysis and interpretation is difficult and time-consuming. So, and also a high level of expertise is needed. So the idea that we want to maximize the EGMS data exploitation and their uptake by non-expert users. To do that, we want tools and methodologies to automatically extract and make an interpretation of this data and to generate operational maps that can support hazard and exposure or risk assessment. This is the idea which is behind the ongoing project, DG ECO project RAS tool. So in this context, so improving the operational use of EGMS information through the generation of secondary products, this work proposed a tool to automatically identify buildings and structures that may be at risk of damage, so generating the final output, which is the potential damage map. The idea behind is that we expect a higher damage level if a structure is affected by differential displacements than if the same structure is affected by a uniform settlement. So the main information that we want to derive from displacement map and from the EGMS data is the spatial gradients of displacements, which generate a differential settlement for the exposed elements. So the main inputs of the methodology are just a PSI displacement map, in this case with a specific focus on EGMS data, and a shapefile building inventory. In this case, we use the OpenStreetMap, which is also freely available globally. Then we have two approaches. The first one is at the active deformation area scale. So we start extracting the active deformation areas, and then we use all the information related to this moving area. The second one is at the building scale, so it's more detailed. It's building-wise approach where we use only the information which belongs to each building. Once we have selected the points that we want to use as input, the next steps are the same. So we have the rasterization and interpolation of the displacement information. Then we derive the gradients maps, and based on this information, we classify the buildings, and so we have the final potential damage map. Let's see the first approach, the ADA scale approach. Here we see an example in the area of Granada, in the south of Spain. Here you see the input, the displacement map. So as I told you before, we start with the automatic extraction of the active deformation areas. This is performed through the use of the ADA Finder tool, which has now been adapted to the huge amount of data of EGMS, and actually it has been applied over the whole European Ground Motion Service extension. So in this case, you see that we have several moving areas, and let's focus on one example. The classification is the quality index, which assess the reliability of each area. So these tools and extraction allows us to only use the measurement points which are related to each ADA, active deformation area. So next step are done only on those areas, the rasterization and interpolation, and then the gradient map. Let's see a detail. Here we see how in the same area we can distinguish now areas where the gradients are higher, so where the exposed elements are more, where we expect a higher damage to those buildings that are located in those areas, in buildings and wells, streets and so on. So based on this information, together with the building shapefile, we can classify the buildings based on the potential damage that we expect. The results have been validated through field survey, and so over, if I remember well, over 5 urbanizations that are affected by slope instabilities. So we made a visual classification of the damage level based on the classification proposed by Cooper. And here you see just 2 pictures to show an example of serious damage, that's a crack, and the class 6, which is partial collapse. There is, well, the results have been validated and published in this work if you want more details about the methodologies and the validation results. So then the idea is if we have enough information, we want to distinguish the information related to the ground from the information related to the single building. Why? Because we can have different cases, just to conceptually show the idea. In the case 1, the house is moving together with the ground subsidence in this case, but we can have that a structure is stable even if the ground is having a movement. And in case 3, we can have also a very local settlement, even if the surrounding surface is not moving. So this is why if we have this detail of information, we want to use only the measurement points that are related to each building. So here an example in the an area of Barcelona. We perform some steps to ensure that the measurement point is related to each building. Then we, as before, we generate the gradient maps, and based on this, we can classify the building. So this methodology has been implemented and optimized to work with the EGMS data and over wide areas. So actually the idea is to apply this approach over the whole EGMS data. And just to see the main points of each approach, the ADA scale approach gives us a less detail of information, but it is applicable everywhere, or even if we have small buildings in small villages and urbanization and, for example, in urban areas. While the building-wise approach is more specific and detailed, but we have seen through an uncertainty analysis that we need a minimum number of measurement points for each building for having a reliable result. So this means that we also need bigger buildings to use this approach. For example, in industrial buildings and in a very urbanized area, this approach is the best one. So here we see that we have applied the building-wise approach over the whole Catalonia, and just an example of the final potential damage map. So the buildings which are classified in low, medium, high, and very high. We see that if we consider only buildings with points with more than 15 points, which is the threshold for having a reliable result, the number of detected buildings that are potential damage are around 300. So we propose a tool which for generate this kind of map, which are the potential damage maps. These kind of maps are a first step toward a vulnerability assessment. Of course, we are now, it's just a first level of information because we are now using only remote sensing data. And this kind of map can support risk analysis, urban planning, and territorial management. And it is also a clear information that can be read by different actors like public institutions, civil engineers, and insurance company, and so on. So that's it. That's the presentation. Thank you.
Thank you, Anna. Very interesting, and looking forward to seeing the full-scale results, European-wide. Any questions for Anna?
I may start. I have a question on the use case on Barcelona. You showed probably a couple of industrial areas, and one of them was classified as not reliable for the gradient. The cause for this scoring was because there weren't enough PSI points over that building, or?
You mean the green class?
No. I mean in a previous slide. This one.
Sorry.
Yeah. So you see the gradient intensity not reliable on the right.
In this case, we need like a minimum gradient value. If we measure gradient values that lower this is like the sensitivity of the approach. We cannot rely on very low values of gradients.
Okay, because from the pictures on the left, I inferred that there was also a few points. So I thought that was the cause.
Also, but this was then a second step, like, okay, if I use all the PS, even if, well, since the beginning, we need a minimum number of points, but then after the analysis, we could say we need at least 15, and so we remove also this. So it has a double reason of being not so reliable.
Thank you, very clear now, thanks.
Thank you.
I think it's okay. Thank you, Anna. And now, again, Urs, we move from X-band to L-band now. So ground displacement mapping with L-band persistent scatter interferometry. So the floor is yours.
Thank you again. It's embarrassing to stand here again. At least it's a different frequency this time. The work is on ground displacement mapping with L-band persistent scatter interferometry. Actually, it was also done to a large degree in this same project. This part was not considered really the very innovative new thing, but rather the more standard working approach. But in the end, it's definitely the element that showed all the excellent results which we keep using. So I can very much recommend that you look into L-band interferometry. So I will quickly say something about the data used, the methods, results, and conclusions and outlook. So we have a long record of working with L-band data. So over Switzerland, the situation is that we have L-band data primarily from the Japanese emissions, so JRS between 92 and 98. Some scenes, but you can still do quite nice work actually. And then Pulsar 1 strip map mode data between 0.6 and 11. We have small stacks. It also includes a longer baseline, so it's a little bit more challenging to work with it, but I will show a result. Then Pulsar 1 ScanSAR, the bursts are not really synchronized, but there are examples where it happens to be synchronized. So there are some nice results for some earthquakes, for example, and we looked into this, but for a more operational application, it's not really so suited because it's in general not synchronized. Then there's a Pulsar 2 strip map between 14 and still ongoing. So there are stacks for some areas in Switzerland. So you don't have very good stacks everywhere, but where you have stacks, it's very useful data. And the baselines are generally short enough, so smaller than 1 kilometer is very useful for L-band data. And then there's some Pulsar 2 ScanSAR data between 2014 and now. And there's a complete coverage of the Swiss Alps. The data is always synchronized starting from 2015. The stacks are small, so in descending orbits it's more than 10 scenes, and in ascending it's fewer than 10 scenes which were acquired, but we used this data and I will show some results. So here you see the coverage for the ScanSAR data over Switzerland. So in red, it's the descending geometry, which provided the larger stacks, and the smaller stacks for the ascending shown in blue. And the southern part, so the alpine part of Switzerland, is fully covered by these data sets. About the processing, we follow two different approaches. So we can either do the merging in map geometry. So you do co-registration of SLCs and then interferogram generation per subswath, and then you geocode these differential interferograms and merge it and do then the further analysis like unwrapping and so on in the combined data set. Or you do the merging already at the SLC level. So this results in very large files, but it is still more convenient because it's fully consistent then. So in our software, we consider this as ScanSAR data with a single burst, and then that means we can use a lot of our tools that we have for ScanSAR data interferometry, and so it's very standard then the processing. So in the time series analysis, I want to speak about some characteristics here, and I would generally recommend that people do this and not just give names because names are typically not so meaningful. Espace means many different things, and so it's good to characterize a little bit what you really mean in your specific case. So here we use single pixel faces, for example, and we use both single reference and multi-reference stacks. So that depends on the number of scenes available. So for less than 10 scenes, we use the multi-reference stacks to have just more points in the regression analysis. And an early step in the processing is then to find suited candidates, and they are selected based on a spectral coherence criteria. So that means we favor point-like scatterers, and what we find is that the selection is very good, so many of the candidates will then make it to the final result and show very low phase noise over time. So it's more easy to develop the solution, and the time series are small, so intensity variability criteria are not so well applicable. We remove some linear trends in slant range and azimuth geometry. We think that relates mainly to processing as effects and not so much to ionospheric or atmospheric effects, but of course includes some of these. And we work with winter data only. We are interested to have coverage in the result up to higher elevations, and so winter data is affected by the presence of snow, so it decorrelates, and and even worse, it affects the phase, and so it's more robust to only select the summer data, summer and fall. In the case of short baselines and accurate DEM heights, it's actually possible to often operate only with a one-dimensional regression, so you don't estimate also DEM height or point height corrections, which makes it also more robust for small stacks. And we do this with our software, with the IPTA software. So in the point target candidate identification, we use the spectral coherence to identify point-like scatterers. Then the big next step is to get interpretable interferometric phases. So this includes the regression analysis to unwrap phases and estimate average displacement rates and residual phases. Then from these, we estimate atmospheric phase delays, including height or topography-related component, and more just turbulent component, which is estimated typically by using spatial filtering on the residual phase. And we do some iteration and quality control on this. The displacement rate accuracies depend mainly on the total time period covered, and not so much on how many scenes you have. Of course, also a little bit on the number of scenes. But having, for example, 7 years of data is very important. So that's better than 100 scenes over 1 year. I list here some capacity and efficiency considerations. So in our approach, we don't work with the full 2D SLCs, which are very big. So for the area processed here, it's like 20 gigabyte per SLC if we include 80% of the frame. And so we use a vector data format with only the point candidate lists and the phase values of these. So it reduces from the 20 gigabyte to 80 megabyte if we think of 10 million candidates. In the end, it was using more like 50 million candidates, but still, yeah, you see the very big reduction of the size, and of course that also affects the efficiency of some steps. The regression analysis, unwrapping, checking of the unwrapping of residual phase, atmospheric phase delay estimation are all quite robust and efficient for L-band data, so it's more easy to process these data as a general comment than C-band or X-band data. because the error terms are typically small compared to a phase cycle, while it is at the level of a phase cycle or half a phase cycle or so with the other frequencies. Data volume and processing time was not found to be a problem. So the robustness depends a lot on initially selecting high quality candidates, and this was possible here. And to have short baselines and an accurate DEM also facilitates the processing, and we were also in the lucky situation that this was the case with these data sets and the DEM access we had. At L-band, the residual atmospheric phases are smaller than half a phase cycle, and so somehow easy to filter and integrate and so on. And the unwrapping is simpler and more reliable than at C-band. For the quality depends, of course, on your thresholds used in the processing. So you have the possibility to select phase standard deviation thresholds, and based on this, of course, you get a higher or lower accuracy. But generally, at L-band, of course, the sensitivity is lower, and so with the same phase error, you get higher displacement errors, but you can work with smaller thresholds, and so you can get to similar qualities, or you do a compromise and you get a slightly lower quality, but you get much better spatial coverage, including coverage in vegetated areas. So here the result, the displacement rate for one of the descending of the two descending tracks of the Pulsar 2 Scansar data over Switzerland is shown. So you see more or less a wall-to-wall coverage, and if you look into more details in small sections, what is striking as compared to our experience with C and X-band is that you really have also coverage for many of the forested areas. And in Switzerland, we could do nice work in the past, mainly above the tree line, and it was and maybe below the tree line for villages. But many of the active landslides are also in these regions, and so now with the L-band data, we get a much better access, and we see most of the known landslides easily, and can further study it here. A section over Grindelwald is shown, and I think most or all of these displacement processes are in forested areas. Or I looked at the area outside Switzerland. In Switzerland, European Ground Motion Service result is not available, and so I looked outside Switzerland, Austria or South Tyrol, I don't remember. And here is the L-band result that clearly shows quite fast-moving landslide processes. And in the same area, the result from the European Ground Motion Service, maybe the visibility is not so great. It has big gaps, and the gaps are quite where you have the landslides. And it's, of course, the forest is the main reason that the information is not there. And you see maybe a few points at the outer edge of the landslide that indicate there may be a landslide, but I would not dare to really classify it and be sure that there is a relevant big landslide present. And in the L-band result, it's very obvious. So there are advantages over vegetated areas and also for faster movements with the L-band, in spite of doing this with between 10 and 20 scenes instead of several hundred. With Pulsar 1, the situation is a little bit more tricky. There's nice coverage only in ascending geometry, and the stacks are also smaller than 10 scenes. And so because of also the larger baselines, it's a little bit tricky to get to a result. But I got one. It was not validated fully and used, but it's also confirming the high potential of L-band data in general over alpine terrain showing here in detail, you see also many known landslides and rock glacier processes present. So compared to C-band, L-band, PSI shows better potential for faster and non-uniform motion and for vegetated areas. Using a small stack with less than 15 L-band scenes over more than 4 years, a very useful displacement map over the Swiss Alps could be generated. So that's a result that can be really used. PSI was found to be overall more straightforward at L-band, so the processing was rather simpler than with the Sentinel data, and phase error terms are small compared to a phase cycle, which facilitates filtering and unwrapping steps. In addition, coherence over vegetated areas is higher, and mainly we got a result there. As an outlook, Pulsar 3, so the next Japanese L-band SAR, will be in the same orbit as Pulsar 2, so slightly different modes, but you can possibly continue time series, which is very important concerning the accuracy of displacement rates that you estimate. NISAR, of course, will provide frequent global coverage, I think with 12-day repeat. Free and open access is also a very nice characteristic. So we see a very, very high potential there, and have only some questions. In some presentations you see 3 years mission and consumables for 5 years. So I hope it's at least 5 or more likely 10 years or so, because I think 5 years is the minimum that you really get the full potential for displacement mapping. And ROSE-L is also at the horizon. Besides, we should not forget there are other L-band sensors already in orbit, like SAOCOM and Chinese Luton 1. And they already provide results. So here you see a very nice interferogram with SAOCOM. You see rock glaciers, landslide. You see a lot of phenomena. It's, I think, 42-day difference or something, relatively short intervals, or good coherence and a lot of information. And similar with the Chinese satellite LT1, I don't know what the access possibilities will be for non-Chinese users, even not for Chinese users. I know it, but it's initially it was in a tandem mode. So you could generate digital elevation models, and if I understood correctly, it was done for China. And now it's in it's 2 satellites 4 days apart, so it's L-band with 4-day interval. So if you get such data over your area in every cycle, it would be a dream. So here I was lucky, and data I got access to, there was in fact, zooming in, there was an area that showed like half a phase cycle difference over 4 days. So that's about 1 centimeter per day displacement. So must be a relevant process. I checked in Google Earth, and you can see a road is crossing the structure, and you see that like at the entry point to the moving part, it's like fixed several times, and it makes a curve to still hit the road, which was already shifted away some meters. I don't know how relevant it is. I don't have a place to submit it or so. Okay, thank you for your attendance.
Thank you, Urs. There's time for a very quick question from the audience.
You didn't say anything about the ionospheric corrections.
Sorry?
Do you do any ionospheric corrections?
In this work, we didn't do any ionospheric correction. We have cases of pulsar data where very obvious ionospheric anomalies are present, and we did quite some work on it, but here it didn't seem to be an issue at all. So that doesn't mean that there is zero phase variation caused by the ionosphere, but if it's a small change, then it's very similar to atmospheric effects. And no strong effects, I think, were present.
Yeah, very quickly, because we are short of time.
Sorry. Is that reason because you were doing spatial filtering and basically you removed it just by low-pass filtering of
the ionosphere? Yeah. Yes, of course, slight effects I don't see or I cannot discriminate with other low-frequency phase, but strong anomalies, of course, are obvious and need different treatment. But that was not necessary here.
If it's very quick, we can. Okay, later on? Okay, thank you. Thanks, sirs.
Okay, for the last presentation of the day, my colleague Diodato will take over and present work from Central Mexico using Sentinel-1 INSAR.
So good afternoon. Many thanks for attending the session till the last presentation. I will be pleased to present also on behalf of the lead author, Francesca Cigna from the National Research Council of Italy. I will talk about Mexico, and in particular the issues related to groundwater exploitation and the consequent aquifer depletion. The initial figure, which tells us very much, is 40% of the consumed water in Mexico comes from aquifers. So you can immediately understand the value of groundwater resource. On the left, you see a map that we published last year in GRL, showing the hydrological regions by which Central Mexico is divided by the National Waters Commission, CONAGUA. And you see how it's distributed in terms of groundwater usage and amount of renewable fresh water per capita. On the right, you see the distribution of the annual groundwater availability index, DMA, which is an index that CONAGUA basically releases regularly by issuing the water management reports. And this index comes out from the equation between recharge minus natural discharge minus the amount of water pumped from licensed pumping. And every time that the pumping rate to the recharge ratio is above 1.1, we can call those aquifers overexploited. And the numbers are immediate, because you see that 57 of the more 100 aquifers that are overexploited are located in central Mexico. So it's clearly a pressing issue. Again, using CONAGUA official statistics, we can look also at delta S, the volumetric difference between recharge and natural and anthropogenic discharge. And again, you see from the map on the left, not only the amount of this difference, but also the fact that the major issues are all concentrated in certain hydrological regions. And of course, we all know the impact. We know that the sandy layers lose storage, and consequently the confining clay deposits compact, and all you know, the various impacts on infrastructure, not only in Mexico cities, but also in other cities across central Mexico. So we ran a quasi-continental Sentinel-1 INSA survey. At that time, but I guess still now, it's probably the hugest effort in terms of Sentinel-1 INSA processing over the whole country. We exploited ESA geohazard exploitation platforms, and in particular the parallel SBAS workflow that my colleague Manuela Bonanno this morning showed you very well in her presentation. Using this continental survey map, basically we identified more than 30 subsidence hotspots, and surprisingly, not only those that are very well known, like Mexico City, but also other cities, basically telling us that the problem is actually sparsely distributed across central Mexico. With this data, and also the data coming from the CONAGUA official water management reports, we derived semi-theoretical relationships between what we can observe from INSAR deformation estimates and the water balance and aquifer system balance parameters. So you see on these plots basically how INSAR-derived vertical velocity correlates fairly well with total extraction volume and delta S. And in particular, we found the three hydrological administrative regions, and not surprisingly, those including the majority of the subsidence hotspots that basically show the highest correlation. And similarly, when you basically compare the aquifer system compaction derived from satellite measurements with all the water balance parameters, again, you see a fair correlation, I would say even better than the previous plots. And you see that single aquifer systems often compact more than others. And we see also steepness of these rates up to 3 times in certain hydrological administrative regions. So that's an example, a concrete example of the value of processing the large amount of data the Sentinel-1 has collected over years across the whole country. And if we combine these quasi-continental survey with very fine-scale analysis, in that case extending over the 2 years that we selected intentionally to match the CONAGUA management reports values with other data. For example, like in this case, in Aguascalientes, we could basically assess the accuracy of these INSAR measurements. We all know that sometimes it's very difficult to access GNSS data or geodetic leveling monitoring data that are so dense to actually make an accuracy assessment which is extended across the whole INSAR dataset. And that's what we were very lucky to do in this case in Aguascalientes, thanks to INEGI, the National Institute of Statistics, Geography and Informatics, which collaborated with us in order to achieve these values. So 8 to 10 millimeter per year as standard deviations and relative errors less than 20% for those locations that subside more than minus 15 millimeter per year. And that's another key message that we would like to advocate for, making these data available, so improving the collaboration so we can match satellite observations with ground-based data. I'm now picking up some of the hotspots just to show you how this data can be helpful to prototype some downstream application products that could be helpful for local administrations in order to cope with the issues induced by groundwater exploitation and aquifer depletion. We all know the situation over Mexico City, not surprisingly, was used as a test bed since Sentinel-1 was launched. In our research, we found that the compaction rates correlate with the aquitard thickness according to a power function that you see on the bottom right of the slide. And also in Ana Barra's presentation, we heard about the differential settlement, so the impact that land subsidence can cause on buildings depending where they are located. And that's something that we have retrieved from INSAR data, measuring angular distortion. So basically quantifying the amount of this differential settlement between 2 neighboring points. And coming up, according to this risk matrix, to a map that basically, in a very intuitive way for local administrations, can show where the majority of the population and properties are mostly affected by land subsidence as the consequence of groundwater displacement, overexploitation and consequent displacement. And based also on the data that the statistics department from Mexico offer in terms of basic geostatistical areas, we can provide quantitative figures that directly feed into the reporting documents that all these local administrations should produce in order to better monitor the situation and also propose remediation measures. The second hotspot is about the relation between land subsidence and urban growth. We always think about land subsidence as a consequence of the fact that water demand increases and therefore we need to abstract waters. But there's also another causative factor upstream of the process, urban growth. So if you basically increasingly urbanize your area, you actually increase the number of properties demanding waters and, of course, the number of properties at potential risk. And that's something that could be very well seen in Morelia. Morelia was one of the cities in Mexico that was very first studied in the INSAR literature on Mexico, but never the studies related land subsidence with urban growth. And as you can see from the map, we identified not only those hotspots that were already known in an area where land subsidence is strictly related to the tectonic structure of the landscape, but also like in Villa de Pedregal, in the southwestern part of the city, we found a very fastly and rapidly subsiding bowl. And not surprisingly, this happens in one of the largest new neighborhoods of all Mexico. This area, basically, through Sentinel-1 data, either from interferograms or S-bus measurement points, basically showed a clear evolution and expansion of this subsiding bowl as soon as the construction lots were completed and they were sold, so people started populating this area, and the water demand increases with increasing amount of licensed wells. So again, another type of products that could be helpful for local administration who first authorized this new neighborhood and now has to cope with the consequences. And if this single situation is reported across the whole scale of the city, in this case also benefiting from the accessibility to open data at urban block level, we can basically do something similar that also Anna Barra showed in her presentation. We can basically classify the individual blocks. And finally, hotspot 3, Aguascalientes, I mentioned before, this is an area that is very strongly structurally constrained in terms of land subsidence patterns. And surprisingly, until 2 years ago, there weren't so many papers investigating the east-western component in Mexican cities, although several papers investigated within SAR this type of process. In this case, it's pretty evident that it's not possible to make a reliable assessment of risk without accounting for the east-western component. And in this case, the risk matrix is adapted to this situation. So the risk matrix is the same, but we add a further level anytime we are aware that the properties are basically affected by a significant horizontal strain higher than 0.03%. So in this case, you see the value of producing spatial maps and associated statistics. The associated statistics would probably lead to a misunderstanding because the total amount of properties scored between R3 and R4, so between high to very high risk. Overall, it's not so high, but the important thing here is where they are located. They are all concentrated along the tectonic faults. So in the perspective of suggesting remediation measurements, the local administration should be guided to prioritize those areas, even if in total the amount of properties is limited over the total amount of properties in Aguascalientes. So the key conclusions and messages to the roundtable. You are all invited to join us at 5:50 for the roundtable of this session. The quasi-continental survey that we did in this research led us to go further the mere observation of the hotspots and derive semi-theoretical relationships because we had also the possibility to access open data in terms of water management values. So we can use these semi-theoretical relationships to assess the compaction rate and the volume as soon as we know how much groundwater has been overexploited, and of course the surface deformation has been measured. And that's a recommendation, we need Sentinel-1 observation continuity with the new missions, because if we want to update this assessment over time, as things change in these cities, we need continuity. Of course, it's heavily and highly demanding in terms of processing resources running such quasi-continental surveys, and equally run several local scale assessments at full resolution in so many hotspots. So another recommendation is the crucial role that platforms and services hosting insert processing routines can play in that to facilitate the possibility to process such big amount of data. I stress the point, both when we look across an entire region and also at very fine scale, but repeated in several hotspots. And of course, all of these, and more importantly, the observation continuity is key if we want to continue developing these downstream application products and provide a continuous support to policymakers and regulators. Of course, one key point from a technical point of view that should be improved, we need, of course, very high resolution SAR data if we want to even more finely define which buildings are affected. This is important also for insurance companies. And of course, the statistics that we retrieved are based mainly on the total number of properties. But as we see also in a previous presentation in this session, there are also other information of buildings that we need to know. So building age, height, maintenance status, because provided that they are basically located in the same area affected by the same type of process, it depends on the type of foundations and how they are maintenance. And you can find all the references and details in the published papers that are open access, and you are very welcome also to approach me for any questions. Thank you.
Thank you. We have time for a few questions.
Thank you for your presentation, very nice. I was curious about the hotspot number 2, where you mentioned it's following a new construction site. So it's like very localized signal, and I think the explanation you mentioned in our slides were relating to new wells being drilled due to increasing water demand. I'm curious because from my understanding that water use, so that will, like the signal will be confined, like will have the shape more or less of like the underlying aquifer shape. So why would it be so localized and moving? So that's my curiosity.
Thank you, because this question also helps me to also make a clarification. This is a country where, of course, there's a management at national level of the amount of water that is pumped. But as you saw, we have very localized spots because actually, in reality, there are several wells that are drilled and operated by private, not only by the public companies. And there's a full registry of all these licensed pumps. But the reality is that this is what we know from the official registry, but there are even more. also your question about the typology of the aquifers and the local situation, and that's where I believe the advantage of retrieving at the same time an holistic view and fine-scale assessment with Sentinel-1 is very advantageous, because this is a situation where if you just look across the whole city or the whole region, you of course end up with an overall assessment, but you will never understand precisely the situation. In Morelia, you saw it was a direct relationship as soon as local, very local wells were drilled, because residential privates started populating the area, the depletion started immediately.
Time for one more question.
Hi, thank you. That was really interesting. Have you had the opportunity to communicate your outputs with policymakers and regulators? And if so, what was their feedback and which outputs did they find most useful?
That's currently what we are doing at the moment, because all these several pieces of the research basically feed into a coherent research line, and we have started in the past year to establish contacts with the local administrations. Of course, we were hampered in the past 3 years by the COVID-19, so we couldn't also meet with them, but we are starting actually asking them how they would use these downstream products if they were provided systematically. Because the main point that they raised is that, of course, they are a very interesting and useful snapshot of that situation, but because the situation is rapidly evolving, they of course need more like a service rather than static maps.
Okay, thank you, everybody. We'll break for coffee now. After coffee at 4:10 will be Earthquakes and Tectonics 1 in this room. And please come back at 5:50 for the roundtable. Thank you.
Yes. So Katerina has not struggling to get her Wi-Fi to share.
I did send it. I think I sent it to everyone from 1 to 3. Yes, just like 5 minutes ago.
Okay. So we had a go, but that's a few now. Yes, we were a bit confused. Oh, yes, with us. It's not. This is them.
Yes, this is them.
Yes, and then we're, which makes much more sense.
Because I collected this maybe some things that came up in other sessions. Check some of those other sessions.
Okay, who's the first speaker? Hi, Louise. Okay, hi. You're set? Yeah, I've checked. I think they've got all the files. We'll give you a nod when it's 15 minutes.
Okay.
And then, we'll get the book out.
No problem with that.
At some point. But we'll tell you when it's 15, so you've got
Okay.
to go.
Okay.
Right. Good afternoon, Leeds. How are you all doing? This is the first of 3, I think, Earthquakes and Tectonics sessions. We're going to be chairing this. I'm going to introduce the first couple of talks. Then Katerina is going to introduce the remaining talks. So without further ado, the first speaker is Louise Maubon. Over to you.
Hello, everyone. Hello, everyone. Today I will discuss the importance of using INSAR data in mapping subduction zone, and I will show you the example of the coupling over the Ikurangi subduction zone. So the seismic cycle can be described as a loading phase, which is called the interseismic. This phase is when the stress is accumulated over the interface between 2 plates, and at first approximation, we can observe in geodetic data a linear trend. We observe that in this station here. So using the surface deformation, we can calculate the coupling map, which is between 0 and 1, and a region which be coupled, like we can observe in this map, in red here. Sorry. More it will have the potential to release stresses in seismically form. But today, we know that the seismic cycle is more complicated than that, and we know that transient deformation happened in the seismic cycle. These transient deformation are not hazardous for people, but what is the impact of on the plate coupling? So the first scientific motivation we wanted to answer with this study is if the deformation evolved through time, which observational period should we choose to recover the plate coupling? Shall we use the long-term period with more than 10 years of data? Shall we use the period between long-term slow slip events or the period between every slow slip event? The second question is, by looking at different time periods, can we determine a kinematic coupling, and can we determine if a region will release stresses aseismically or seismically? And finally, the spatial extent of coupling is directly linked to future seismic hazard, but does GNSS provide sufficient resolution to accurately recover coupling? So to answer to this question, we propose to do a geodetic study using GNSS and INSAR time series with Sentinel-1 images. And then we propose to do a geodetic inversion to retrieve the slip deficit on the interface and then the plate coupling. So here we study the Ikurangi subduction zone, which is situated beneath the North Island of New Zealand. This region is very interesting because we have several slow slip events which happen there. On the East Coast region, these slow slip events are shallow and short term. They happen every 6 weeks to
12 months. We also observe deeper and longer-term slow sleep events in Kapiti and Manawatu region. This event happens every 4 to 5 years and with an equivalent magnitude of 7 to 7.5. So on our study, we use 92 GNSS stations. We didn't take account of the GNSS station in the topo rift here because they are sensitive to the volcanic deformation and we want to observe only the subduction signal. We use two Sentinel-1 tracks, one in ascending and one in descending. We use long temporal baseline to mitigate biases in our time series. We correct the interferogram using ERA5, and we construct a time series using a small baseline approach. Finally, when we obtain the time series, we want to extract the linear velocity associated to the subduction. For that, we use a trajectory model, which is very simple. We describe the displacement as the sum of a linear trend and the constant. But on this GNSS time series, we can observe that the observational period we will choose will strongly impact the velocity we will recover. So the next step is to choose the period we want to study to determine the plate coupling. We can study the long-term period, which is between 2006 to 2016. So we observe very well here that the slow sleep event will impact the linear velocity estimation. We didn't take account of a longer period because there is a Keikura earthquake which happened in November 2016, and we don't want to take account of this earthquake and the following post-seismic. We can also study the entire deep slow sleep event, which is the period between slow sleep in Manawatu and Kapiti area. Using this period allows us to observe 4 years of the seismic cycle between 2018 and 2022. But we can observe on the north that the GNSS time series will be impacted by shallow transient deformation. However, if we look at the INSAR time series associated to this region, we observe a very good correlation with GNSS data, and we also observe that we will be able to retrieve velocity which will be coherent because we have enough dates. And then we can also observe the inter-slow sleep event, which is the period between every slow sleep event. This period will be between 9 months and 1 year. So the problem by doing that is we will need different period window for every region of slow sleep events, and it will be very difficult to estimate a velocity in region with short-term slow sleep events using INSAR data. So like we can observe here, if we want to estimate a velocity in this period, we will be strongly impacted by a seasonal signal. So also, it will be very difficult or quasi impossible to determine a coherent velocity and vertical displacement on the GNSS data due to different noise such as the seasonal signal. So instead of doing that, we choose to study the entire major slow sleep event. So we can observe that there is slow sleep events which are bigger than other. And this period allows us to observe 2 years of the seismic cycle, which is enough to obtain coherent velocity over our INSAR time series. So just to summarize, we have 3 options. The first one is to study 10 years of the seismic cycle, but using only GNSS data because we do not have INSAR during this time period. The second option is to study 4 years of the seismic cycle between deep slow sleep event with GNSS and INSAR data. And finally, the third option is to study 2 years of the seismic cycle using also GNSS and INSAR data. So here are the results for the 3 options we have of the GNSS velocity estimation. What we can observe, it's during 10 years, we have a smaller velocity in our GNSS linear estimation than during 4 years or 2 years. It's what is expected because 10 years of observation is impacted by slow sleep events in almost everywhere in New Zealand. If now we look at our INSAR data, so on the left are the velocity map over 4 years of observation, and on the right is the INSAR time series for the station TAC. So first we observe a very good correlation between GNSS and INSAR data. We also observe that we are able to detect the slow sleep events in the Manawatu region. So we do not have the beginning of this event because Sentinel-1 began after the slow sleep, but we can recover the end of the event. And what we can observe we have a good estimation of the velocity during 4 years of observations. If now we look at on a station which is located on the shallow slow sleep event area, we also observe a good correlation between INSAR and GNSS velocity, but it's interesting to notice that we are not able to observe slow sleep events in this region. The slow sleep events here are small in amplitude, and there is almost no vertical deformation associated with these events. So finally, we need to correct our time series from the plate model. So we decided to convert our time series in the block model, which has been published by Wallace et al. In 2010. And what we observe is when we correct our ascending data, we remove almost every deformation because most of them is associated to an horizontal displacement due to the rotation of the North Island. If we do the same correction on the descending track, we still observe the same pattern before and after correction because descending track are less sensitive to horizontal displacements. Finally, if we compare our different data sets between 4 years and 2 years to validate our results, we observe that we have some residual ramp in INSAR data, and we also observe some unwrapping error, like here, in our velocity estimations. If we compare GNSS time series over 2 years and 4 years, we observe that only this part of the subduction zone is impacted by the slow sleep events, the shallow slow sleep events. So finally, now that we have all these data sets, we can perform an inversion to retrieve the coupling at depth. We use an Okada dislocation in a linear inversion. We impose the sleep direction for each patches, and we did the initial assumption that the model is coupled between 0 and 20 kilometers of depth. So then we obtain a map of sleep deficits that we need to divide by the velocity of plate for each patch to retrieve the coupling. So here is the result of the coupling by using only GNSS data. We observe a coupled region in the deep part of the subduction zone, the part of deep slow sleep event. And in the shallow slow sleep event area, we observe 2 patches of a null coupling or negative coupling here, which is expected because here we didn't take account of the slow sleep event during this observational period. So now if we had INSAR in our inversion, we observe that the coupled deep patch here is more correlated to the slow sleep events than using only GNSS data. Our inversion doesn't change a lot of things in the shallow part of the subduction because the INSAR data doesn't cover very well this region. Now if we compare a model using only INSAR and a model using only GNSS, we observe that in the Manawatu region, we will not be able to retrieve coupling using only GNSS data, but we are able to retrieve all the coupling of these patches using INSAR data. So using INSAR allows us to obtain more detailed coupling map. So we did the same inversion for the 2 years observational period. We still observe a coupled region in the deep slow slip event area. So here we have a smoothing which is more important because we have more dispersion in INSAR data, and so we have bigger errors. We still observe some uncoupled patch here because there is still slow slip event we didn't take account. But we now observe a coupled area here because we took account of these slow slip events. So finally, we can wondering how representative are this coupling map of a long-term coupling. So we compare our results to a coupling map over 10 years using only GNSS data this time. And what we observe is we have a non-coupled patch in the deep slow slip event area. In the shallow slow slip area, we have also uncoupled patch, which is expected because we observed a lot of slow slip events during this time period. So finally, if we compare the sleep deficit over 10 years and the sleep deficit over 4 years, we are able to retrieve slow sleep events in the deep part of the subduction. If now we look at the amplitude associated with these patches, we retrieve an event with 18 centimeters of sleep, which is exactly what has been observed before. So finally, to conclude, we can go back to the beginning. So if deformation evolves through time, which observational period should we choose to recover plate coupling? There is probably no good answer because the interseismic period is not stationary in time and space, and we should probably be careful when we compute plate coupling over faults. Secondly, by looking at different time periods, can we determine a kinematic coupling? So comparing different time periods help us to observe which region can seismically slip and which other region doesn't slip seismically over a different time period. And finally, the spatial extent of coupling is directly linked to future seismic hazard, and does GNSS provide sufficient resolution to accurately recover coupling? It's probably not the case even in regions like New Zealand where the network is very good. And we know that INSAR will probably not replace GNSS network, but it can provide a very essential information in our coupling estimation. And finally, if we are not able to retrieve slow slip events with INSAR data, like here, because we're missing the beginning of the event, we are still able to recover the events by comparing different coupling observational period.
Okay, thank you very much. We've got time for some questions. There's a question over there.
Hello, thank you for the talk. So I had a question on the period between the major slow slip events. Did you select the images beforehand that you wanted to use and constrain the time period that way? Or were you able to detect such an event in the time series and then throw away the data that is not contained in the period of interest?
So here we are able to retrieve this event with our INSAR time series. So what I don't show, it's not this track, it's his track. But we were not able to use the velocity map because it was too noisy and we had too many unwrapping errors. So on the track I used to do the inversion, I do not recover, I do not observe the slow slip event signal. So I didn't trunk my INSAR time series. I just choose the period between 2019 and 2021 to do trajectory model.
Right, so in a sense, beforehand, you select the periods that you're
Yeah.
interested in for the whole area.
Okay, any more questions? I've got a question, if there's none in the audience. So, have you considered whether, do you think the data has enough power that you could resolve for the slip history on the fault? So instead of doing these fixed periods, just actually get a movie of which bits are slipping at different times?
Yeah, I think adding INSAR is very helpful for the depth part of the subduction, because finally the GNSS network doesn't go so far here. And with INSAR, we help the inversion to retrieve slip at depth.
And do you think you could resolve, if you took the fault patch,
Yeah.
And you took an individual patch, do you think you could resolve how much that fault patch slipped through time as a full time series?
I would like to do it, but there is still some seasonal signal in my INSAR data. But it's something we think about.
Okay, great. Any other questions? If not, let's thank Louise again. So the next presentation is a talk. Is going to be given by Raphael Grandin. This presentation prepared by Margaret Matte.
Exactly.
Okay. Très bien. Nod on 15 minutes.
Okay, thank you.
Speak nicely and loud.
Okay. So hello everyone. So I'm gonna talk today about the deformation in northwestern Tibet, and use a Sentinel-1 time series to constrain slip partitioning, deformation, slip rates, arcing depths of faults in this area of that you see on the map. So it's between the Tibetan Plateau and the Tarim Basin. So before I start, I would like to acknowledge my co-authors, and especially Margot Mete, who could not be here, and that's why I had to step in. So first, the area of interest. So as I said, it's northwest Tibet, where there is a very well-known fault, the Altin-Tag fault, that you can see here, and that delineates the border between the Tibetan Plateau and the Tarim Basin, which is much lower at lower altitude. It's a desert with sand dunes. And we're interested in trying to constrain the deformation to the west of the Altin-Tag, in this area here, where things are much more complex. There is not a single fault. You have several segments that split, especially the Karakash fault here, and the Longmu-Gozako fault. That's the main interest of our study here. There are also tiny volcanoes around here. And so it's an interesting region, because there is a considerable uncertainty about on the slip rates in this on some of these faults, and disagreement between studies that look at deformation over the Quaternary and more recent geodetically based studies. And in particular, this area here is very poorly known because it's very remote and because of high elevations. So we are interested to see how INSAR can be used to constrain the slip rates and seismic hazards of this area. And beyond the specific regional case here, we would like to design a method to be able to separate tectonic processes from other processes that we see in our images, as I will discuss in detail in the rest of the presentation. So we will use Sentinel-1 because it's a very powerful system to constrain deformation at these broad scales. It's still a challenge because we need to deal with a very large area. It's 1,000 kilometers wide. So we have to combine data from 10 different tracks, which is a challenge. There are large topographic gradients. Even if Tibet is a good area for INSAR, there are problems. There is snow, there are glaciers, there is some vegetation in the lower parts in the Tarim Basin, for instance. There are sand dunes. So all of this conspires to having many problems combined in our images. So to process all this data, we rely on a service that has been launched in 2020 that provides automatic processing of very large areas based on a selection of projects. So we had 8 projects. These are the red areas here in 2020, and then there are 9 projects that are currently being processed across the world. And so our primary target here today is this one. So there is so the automatic processing is performed on the high performance computing facilities of CNES, the French Space Agency. We use NSBus with tropospheric corrections to remove topographically correlated signals. And the result is a time series in the line of sight for each track in the area. So as I said, here we have 10 different tracks. So what we will do is that we will start from the time series for each pixel and try to go up to measuring strain rates or slip rates. So this will be basically the roadmap of the presentation starting from now. So our first step is to mask the bad pixels, and for this we rely on the auxiliary information that is provided by the FlatSim service. So basically there is the number of interferograms, the time series inversion RMS, and the temporal coherence. So combining this information, we remove many pixels, especially in the Tarim basin. You will see that this is an area that we cannot really constrain. And then we reference all the tracks together, separate the signals between linear and seasonal components, then make an east-west, up-down decomposition, and then get to the tectonic interpretation. So first, the referencing. So we use GPS velocities that we project into the line of sight. So these are the colored dots that you see in these 2 images. So on the left-hand side, you have the ascending mosaic. That's the result of the mosaicing. And on the right-hand side, the descending. So you see that there are quite, well, the coverage by the GPS dataset is quite complete, but it's still relatively coarse. So that's showing the interest of having INSAR. So to perform the referencing, we just remove bilinear ramps in azimuth and range. And just by looking at these 2 images, we see very clearly that there is a contrast, in color contrast, about 5 millimeters per year in the line of sight, it depends, ascending, descending, across the Altin tag. And it goes to the west, up to this area here that we will focus on. So this is a zoom on the left, on the western termination of this contrast that we see at broad scale. And so if we make a cross-section across the fault here, this is what we have in ascending and descending. So here you have the ascending. Descending is on the previous slide, just for you to see. It's here. So what we see very clearly on the ascending is that there is a very sharp contrast. You can see here a step. Whereas on the descending, it's not so clear. So this looks not so consistent at first sight. So we will focus on this area, try to understand exactly if there are other processes in addition to the tectonic processes in this region. So I will focus on this diamond-shaped area here. And why is that? It's because it's a place where we have 4 different tracks that cover the same area, 2 ascending, 2 descending, so they all overlap. And so we have a very redundant information. And we try to understand what's going on. And to analyze the data in this diamond-shaped area here, we first remove a step that we believe is the block motion across the fault, about 5 millimeters per year, to be able to highlight the more high-frequency information and remove the broad-scale tectonic deformation. And so this is what we get if we remove the step. So to the left, on the left, you have the 2 ascending tracks, and on the right, the 2 descending tracks. And so what we see is that, so the block motion is removed, you don't see it anymore. It's supposed to be here. But in detail, you see very consistent patterns across the 4 geometries, and especially in this rectangular area here, you see that there are blobs that are not tectonically related. And this is showing this is the line of sight velocity, by the way, I didn't say it. And so what we try to do is to interpret in detail what's happening in this area and use it to maybe correct the interferograms and extract only the tectonically meaningful information. So what we do is that we extract the linear component of deformation plus the seasonal component of deformation for these 4 different tracks. And then we combine them together to have the linear component for the vertical, linear component for the east-west, and then seasonal terms. So that's what you see here. So to the left, you have the linear, so the velocity, mean velocity in vertical. Here you have the velocity on the east-west component. And then here you have the seasonal terms, but I show here only the vertical one because the east-west seasonal doesn't show any significant, well, meaningful information. So let's try to interpret the 2 maps on the left, the linear terms, vertical and east-west. So if you look in detail in this rectangular area here, on the left-hand side you have the same information but overlaid on topographic gradients, just to see what the topography looked like there. And what you see is that the blue areas, they are going down, and they correspond to topographic heights, so mountains. And if you look at the horizontal component here, you see it's red to the west of the mountains, and it's blue it's red to the east and blue to the west. And so the interpretation is that we have something that is moving downslope, but we see it only for mountains that are aligned north-south on the track, because we don't have any sensitivity to north-south motion. So our interpretation is that this is due to gravitational motion. And now if you look at the 2 other images here that show the seasonal term for the vertical, what we see in certain areas, especially in this area here, is that we have something that is going up and down in a flat area, and that is that corresponds to a basin, or at least some area that is between 2 mountains. So we interpret this as hydrological motion. And so we use this rationale to correct to say these are the non-tectonic processes that we want to get rid of. And so we use this specific example to apply a filter on the whole track. And so this is the result of the filtering. So to the left, you have the linear east-west velocity without any filtering. Then here you have the components that we believe in this map that are related to non-tectonic processes, and we decide where they are on the basis of the analysis of the topographic slope. So when the topographic slope is steeper than 30 degrees and the slope azimuth is aligned plus minus 30 degrees with respect to north, then we say that this is an area that we cannot really trust. It's probably corrupted by topographic gravitational motion. So we just remove it. And so this is what we get after adding back the step that represents the block motion across the fault. And this is the same map after removing non-tectonic processes. And we see that this map is much clearer and represents, we believe, with more fidelity, the tectonic component in our velocity maps. And so we expand this methodology to the whole track and apply it to the whole mosaic. So this is our final result. So this is an east-west velocity map for the 10 tracks merged together after removing these areas where we think that there is something that is non-tectonic that is happening. And then finally, we can make these cross sections across the fault at 3 different places. So across the Altin-Tag here at the bottom. So here you have Tibet to the west, to the left, the south here, north here. And so we see a very clear, well-known arctangent pattern that we interpret as a slip at a rate of about 6 millimeters, 7 meters per year. I don't remember exactly the number from the top of my head. And a locking depth that is deeper than 10 kilometers. And then when we move into to the west, profiles 2 and 3, through 2 and 1, you see very clearly that the gradient is much sharper, and then we end up having a creep across this this Gozako fault here at a rate of 5 millimeters per year. So the conclusion is the transition from, there is a transition from localized deformation near this area, and then it moves into something that is more diffuse further to the west, and we lose the deformation around this 81 degrees longitude. And our secondary conclusion is that maybe the Caracas fault here is maybe less active than the LGC fault here, at least today, based on geodetic information. So these will be the conclusions of the study. So we were able to separate tectonic from non-tectonic signals by analyzing the patterns of deformation in topography and get to measure deformation, or velocities at an accuracy of a few millimeters per year using this automated processing service. But this involves quite a lot of, still a lot of post-processing. So that's all for me. Thank you for your attention.
Thank you, Raphael. We have some time for some questions again. There we go.
Nice talk. How do you explain that you go from almost like 0 millimeter per year deformation to 5 millimeter per year, like in the diamond area, like very sharp, like no, you can go back to the last slide.
Last slide?
Yeah, you have on the Longbow Cove fault, you have almost no deformation, and very quickly you go to like 5 millimeters at least. How do you explain that, like geophysically, like where does it go after the deformation, like before, on the western part?
The question is, how do we go from a very sharp gradient?
Yeah, I mean, I don't really understand like how, what kind of like process can explain like that very quickly the deformation dies when we go westward.
Change in speed.
Well, I have no simple conclusion. I mean, one possibility is that the locking depth goes deep quickly, but then if it goes too deep, then it's as if there is no fault anymore. So, well, there is no, I don't have any clear explanation for this. It's an observation at this point.
There was an earthquake roughly there, wasn't there? When was, I forget which earthquake and what year, but am I misremembering? I'll have to look it up. But I think there might be a bit of post-seismic that's still in the Sentinel data. And that would explain a little bit of it being faster.
Perhaps, yes.
Yeah, but I'd have to.
There is a slide where you have recent earthquakes shown.
There's another question there.
This one.
And then Eric afterwards.
Hi. So, correct me if I'm wrong. So you're using a block model to calculate what the slip rate should be, removing that from the INSAR, and removing everything for it, and then adding the block model back in.
Yes.
And your final answer is the same as the block model. Is that?
No. Sorry, maybe I wasn't clear. The removal of the step function or a block model, in my view, is just for communication purpose. It's just to show you that if you keep the block motion in the images, you will not be able to see what I'm trying to explain. So we just remove it and analyze the residual and see that there is a systematic pattern that is related to topography. And so once we have understood this, then we go back to the original data without removing the block model and do the corrections.
I see.
So
Okay.
no.
Could another approach be just to do a bandpass filter either side of the fault of all the data of anything smaller than a certain wavelength?
Well, if you do that, maybe you would just destroy a little bit of the signal, especially if it's really at short wavelength, like creep. So I would not advise to do that. Maybe by playing with the direction of, well, maybe we could try this.
Okay, I think Eric has a question, but you can see the earthquakes on the map, look.
Yes.
There we are, so there were some.
But they are not in
They're
this.
maybe not in the right place.
No. So these are mainly by the way, it's interesting, normal fault earthquakes on the Ashikole segment. These are really big earthquakes, but they are not strike slip.
Did you look at the phase closure bias on these data?
It's one of the byproducts of the processing, but we didn't really look into it in detail. It seemed, well, still, I mean, geographically, at least, I can say that it was relatively negligible on the Tibetan plateau part of the area. But in the Tarim Basin, we had large biases. But in the end, we removed this area because the overall coherence is low. But we didn't really look into this in detail.
We saw the strong correlation with the phase closure bias of being different on the east and west sides of the ridges.
So what you imply is that maybe this signal that we attribute to gravitationary motion may be due to some bias. Okay, that's interesting. We could discuss this.
Okay, any final questions? Time for one more very quick question. If not, I shall pass over to you got one, sorry.
If no one else has one, I have one. I'm sorry if I missed this, but did your processing apply any kind of tropospheric correction, particularly to deal with topography correlated atmosphere signal?
Yes, it's part of the processing by flat sim. We use the ERA 5 ECMWF corrections.
Got it. Thank you.
Okay, I'm going to hand over to my co-chair to introduce the next speaker.
That would be me. So our next speaker is Natalie Forrest from the University of Leeds, who's going to talk to us about post-seismic deformation on normal faults.
Okay, hi everyone, and welcome to my. Welcome to my talk. My name's Natalie, and I'm a second-year PhD student here at the University of Leeds. So today I'm going to be talking about 30 years of post-seismic deformation of a continental normal fault as measured by multi-satellite INSAR time series. So I've been using 3 different generations of SAR satellites, so ERS, Envisat, and Sentinel-1. And I've been using the resulting INSAR time series to be looking at the dynamics of historically understudied dip-slip faults. So the last talk was quite a good example of how historically we tend to look at strike-slip faults and tend to overlook dip-slip faults a bit more. So by creating a 30-year time series, I hope that we can look at like the later stages of the post-seismic deformation. And again, a lot previous studies tend to look at the first few years of post-seismic. And unfortunately, I have to mention the magnitude 6.8 earthquake in in Morocco on Friday. It just demonstrates how dip-slip faults are capable of producing a large amount of devastation. And this is particularly true in an area such as in Morocco, where you don't tend to get such large earthquakes as often. And so the population is generally underprepared. So hopefully by doing further study into dip-slip faults, we can better understand the dynamics and then communicate the hazard in future. Okay, so to start off with, I thought we'd look at some normal faults in the field so we can get an idea of the scale of the deformation that we're looking at. So here's a normal fault from the Gulf of Corinth in Greece that I took on a field trip. And here you can see the normal fault trace along the base of this hill. And over multiple earthquake cycles, the footwall has uplifted several hundred meters and the hanging wall has subsided down into the valley. This is similar to the fault that I've been looking at in Greece, so it's a similar geological and tectonic setting. However, this is not the fault I've been looking at. And then we also have this picture from Italy, from Laura Gregory. And so this is from the 2016 Central Apennines Italy earthquake sequence. And this picture was actually taken 2 days after the 30th of October earthquake. So this is like very fresh slip on the fault. And you can see the person in the background is like 1 to 2 meters of slip. Okay, so just to go through a simplified earthquake cycle model. So this is looking at like a one-dimensional how stress accumulates on a fault over time. So firstly, the fault will break in an earthquake when the maximum strength is reached. and then there'll be this very quick drop during the co-seismic deformation period, so the earthquake. And then the section of the earthquake cycle I'm interested in is this faster post-seismic recovery time. And here the stress will recover slightly faster, but then over time, this will decay to a slower interseismic deformation rate. And then this cycle will repeat over multiple earthquake cycles, and you'll get variable earthquake size and also repeat times between them. However, this is based generally on strike-slip faults, and the strength of the fault might vary through time, and also the geometry might be a bit different when you incorporate dip-slip faults. So yeah, earthquake cycle models tend to be based on strike-slip faults. So you have this very simple idea where you have this constant simple geometry, which will go for thousands of kilometers. And these faults also tend to host quite large earthquakes. As we saw with the Turkey earthquakes in February, these were up to magnitude 8 almost. Additionally, we tend to have quite fast slip rates on strike-slip faults. So there'll be up to tens of millimeters per year of deformation. So the real question here is, do earthquake cycle models, can they also be applied to dip-slip faults? So the general aim of my project is to study normal fault dynamics, so take concepts about the earthquake cycle from strike-slip faults, combine this with 30 years of geodetic observations, so primarily INSAR, and then see if we can better understand normal fault dynamics through time. So there are two primary post-seismic mechanisms on dip-slip faults. So firstly, you have afterslip, which occurs on the fault interface around the co-seismic slip patch. So this can either be seismic slip in aftershocks, or it could be aseismic slip, which won't produce aftershocks, but you'll still get slip on the fault. Additionally, you can have viscoelastic relaxation. So there, as you go below the fault zone, the rocks are actually hot enough to flow on longer timescales. And this viscous flow occurs over like several years, depending on what the viscosity of the material is. So during the earthquake, there is a stress gradient imposed elastically on this area, and then these stresses are relaxed as the rocks flow over time. And talking a bit more about viscoelastic relaxation, there's two end-member models of this. So you can either have broad deformation, so this is a distributed longer wavelength flow throughout the higher viscosity ductile substrate beneath the fault. And with this, if we link it back to INSAR, the expected surface deformation is that you get a broad zone of post-seismic uplift around the fault. Alternatively, there could be a narrow zone of viscoelastic relaxation. So this could be focus flow directly below the faults, where you have a slightly lower viscosity, and it could be like a down dip shear zone. With this, we expect a much narrower zone of post-seismic uplift around the fault. So how did I pick which normal fault I wanted to look at in more detail? Firstly, INSAR doesn't really work so well over water, so I wanted to pick an earthquake on the continents. I wanted also to be able to measure a significant amount of post-seismic deformation, and you tend to get this with larger earthquakes, so I've filtered for ones that are bigger than magnitude 6. And looking at the INSAR that's now available, I wanted an earthquake that happened about 30 years ago so that you can look at both the very early post-seismic and also the later post-seismic, so looking 30 years around now as measured with Sentinel-1, see if we can link those observations together. And additionally, we wanted an area where there's good INSAR coverage, so with the C-band, you're not necessarily going to get good coherence on the scale that I'm looking at, where there's glaciers and vegetation. And it would be good if there was some GPS around to help ground truth our measurements. So I've settled on choosing the Grevena earthquake, which was a magnitude 6.5 in May 1995. So this is an ERS interferogram created by Tim. And so yeah, there's quite a few co-seismic studies on this earthquake. The main fault strikes west-southwest, dipping to the north, with basically purely normal fault motion. And there was a couple of meters of slip at 6 to 15 kilometers along the fault, and there was this shallow slip deficit. Additionally, there was this GPS campaign, which is really interesting. So you can see in the first 4 months of post-seismic, there was roughly 8 centimeters of displacement measured on the fault, and this was primarily after slip, we think. And then throughout the rest of the year, there were still like centimeters of deformation displacement happening. So yeah, as I mentioned before, the previous studies on dip-slip faults tend to focus on like the very early post-seismic. However, now the INSAR data is available for nearly 30 years. So this is a conceptual timeline of how the Grevena post-seismic deformation may have evolved through time. And the geodetic techniques I'm going to use are the GPS campaign, ERS 1 and 2, ENVISAT, and then Sentinel-1 and Sentinel-B, 1A, 1B. Okay, so the GPS campaign and ERS should look at this early after-slip periods. ENVISAT might be able to show us some later viscoelastic deformation through time. And then as we're getting into Sentinel-1 and close to the present, the real question is, has the deformation finished, and would we be able to see if it has? So yeah, my aim is to build this really long-term post-seismic time series. So this is a co-seismic interferogram that I've created using gamma. So this shows the co-seismic deformation and also the first 3.5 months of post-seismic. It's a north-dipping normal fault, so you can see there's a lot more deformation to the north of where I've marked the fault. There's roughly 12 fringes, so this represents 35 centimeters of displacement in the line of sight. Sorry. And there's also ERS interferograms which show very early post-seismic displacement. So this interferogram spans 6 months to nearly 2 years after the earthquake. And there's 1.5 fringes here, which you can see it go from purple on the fault, going back out to purple again, which represents about 4 centimeters of displacement in the line of sight of the satellite. Here there's a very sharp interface, and the length scale of the deformation is about 10 kilometers. So this represents early after-slip. Okay, so here's a network that I've been building in order to create an ERS post-seismic time series. So here's all of the SAR acquisitions for the descending frame over Grevena. And after 2000, we had the gyroscope failure, so I haven't been including that in my time series for now. And yeah, so there's a lot more spread with the perpendicular baseline and the temporal baseline compared to Sentinel-1, which tends to be 6 to 12 days repeat time and a couple 100 meters probably at most for the spatial baseline. So I filtered for interferograms which have a temporal baseline of less than 3 years and a spatial baseline of less than 300 meters. After running all of the interferograms which fit those criteria, which are highlighted in gray, I've got 6 interferograms which show good coherence, and I've put these into a small baseline inversion in stamps, which just has the effect of reducing the noise, increasing the coherence. And here's the resulting time series, which shows quite a strong signal of post-seismic deformation. There's roughly 10 millimeters per year on average of line of sight displacement in the hanging wall subsiding, and also slightly less than that in the footwall uplifting. So this spans from 4 months after the earthquake to 4.5 years after the earthquake, so roughly 4-year time series. And there's, again, a very sharp interface around the fault, and the deformation extends 15 to 20 kilometers north of the fault. So this is probably predominantly after slip, but there could also be some very early viscoelastic relaxation happening there too. Okay, so that was ERS, and now I'm moving on to ENVISAT and processing the post-seismic time series for that. So this is a single interferogram, which is from 11.5 years to 12 years after the earthquake. And you can see the fault is roughly located where the arrows are. You could maybe convince yourself there's a bit of a discontinuity happening there. You can't really make any strong conclusions because there's quite a lot of noise. So I'm now constructing the time series for the ENVISAT interferograms using the same criteria for spatial and temporal baseline as ERS. And these are all of the interferograms which fit that. And the green ones are the ones which have good coherence. So it's not quite as good as ERS, but I'm going to process those in the future and create an ENVISAT stamped time series. Moving on to Sentinel-1, I've created a time series using the LixBus software, and it doesn't seem to show any displacement at the moment. So this is 19.5 to 26.5 years after the earthquake, and there's no measurable post-seismic deformation around Grevena. So does this mean that the post-seismic deformation has now finished? Or is it just that post-seismic isn't necessarily observable 20 years later within the uncertainties of INSAR? We've also had quite a few talks about the European Ground Motion Service, so I've had a look at this. And again, it really doesn't look like there's any measurable deformation using Sentinel-1 in this area. Okay, so bringing all my observations together, the question is, does the decay of post-seismic deformation, is it more exponential or does it fit a logarithmic trend? So we have roughly 10 centimeters a year measured in the first year of the GPS campaign, which plots around there, and also 10 millimeters a year of displacement measured by ERS, which fits roughly around there. Oh, sorry. So at the moment, it looks like it's more of an exponential decay rather than a logarithmic decay, but we'll take the ENVISAT data and see if that can help us better understand the long-term time series. Okay, so to summarize, I've been creating this 30-year time series of post-seismic deformation on a dip-slip fault. I've been using 3 generations of STAR satellites to measure the post-seismic deformation following the magnitude 6 Grevena earthquake in 1995. By generating a 30-year time series, hopefully we can better interpret the relatively understudied dip-slip fault dynamics. And next, I'll run some forward models to see if you can distinguish between whether there's narrow or broad viscoelastic relaxation, and then further compare this with strike-slip faults. Okay, thank you for listening.
Thank you so much. We have time for questions. Yes.
Hi, thank you very much. That was truly interesting. So I have 2 questions, if that's all right, both related to how the displacement at the surface relates to the strain at the fault, at the contact. So I can imagine if you have movement across the fault or you have slip, that relieves strain, at least that I would imagine so. So if you have, for example, slip right after the earthquake, after slip I believe you called it, does that relieve strain over you had this conceptual curve where you had a sharp drop in strain during an event, and then you had a gradual buildup of the strain before the next big event, right? So if you have after slip, how does that relate to this buildup of the strain?
So it depends on the actual geometry of where the slip is. If it's around like a locked area, then it could potentially reload that section of the fault, but if it's on the actual co-seismic slip patch, then maybe it could build up. It depends if it's, yeah. If you're looking at 1 dimensions or 2 dimensions, it gets slightly more complicated. But yeah. Did you have a second question?
Okay, yeah, no, that's all right. But I have a follow-up that's related. So if you have a look at the Sentinel data, let's say, and you say there's not a lot of movement anymore, does that also necessarily mean that there's not much strain buildup anymore? Because I can imagine that there is still strain buildup, it's just waiting for the next big event, let's say, right? But how do you tell how far you are to the next big event if you are looking at displacement and it's a proxy for strain in a sense, right? Do you get my question?
Oh yeah, I see what you're saying. Yeah, I mean, I could probably try and calculate what the strain across the region is as well. But at the moment, just saying it's 0 velocity.
Sorry, actually, I said strain. I meant stress. Sorry about that. It's, so if there's stress buildup in the fault, then you don't see it in the displacement, right? But the more stress there is on the plane, the bigger the next earthquake might be, or the more likely, I guess. So, yeah, I guess the question is, how do you relate the displacement to the strain on the fault?
Yeah, so one way we could do that is by running some forward models and then seeing what the stress could be at depth and then what the resulting expected surface deformation is. Or yeah, you could look at the strain potentially. But some of these displacements are quite small, so I don't know if you'd be able to like have a very good idea of how big the stress changes are and like whether it changes over time. But yeah, it'd be quite hard to, because you don't necessarily know when a fault has finished building up stress until the earthquake happens. So I don't know if the rate of stress accumulation would necessarily affect how big or how quickly the next earthquake is.
In a sense, that's like the million.
Yeah, yeah, exactly.
Thank you. Anyone else? Yes.
Hi. For the ERS process, you only showed like a mean velocity map. Did you look at the time series, and in your time series, can you see the decay of the displacement? Do you have enough like observation to already see a slowdown of the velocity?
Sorry, what was that? The coherence?
No, like you only.
Oh, I see.
Can you already constrain the shape of your deformation with time, with the time series? Because you can't do it with only the mean velocity map.
Yeah, so at the moment the map just shows the average displacement, so it's basically interpolating a straight line. But yeah, the individual time series, I'm working on averaging them because there's a reasonable amount of noise, but we know that there's a good signal. So yeah, hopefully by, as you say, looking at the time series in a bit more detail, we'll be able to actually constrain the shape of the decay.
Great. Any more questions? We have time for about, yeah, go ahead.
Some of these normal faults are routed into a décollement, and so there is a change in the dip angle when you get under the seismogenic depth, let's say. So to what extent would you be able to capture a tiny slip occurring in this décollement, on this décollement, at the same time as you have after slip at shallow depths? To what extent does the slip at shallow depth may hide some signal routed deeper into the fault?
Yeah, so it's quite difficult to tell the difference between like deep after slip or slip on in a shear zone at depth. So yeah, at the moment probably a lot of the ERS signal is overprinted by shallow after slip, but if we're able to run some models, we could maybe do like a sensitivity test to see if you can actually tell the difference. You might not be able to, but we could see. But yeah, good point.
One more question.
Yeah, thanks for an interesting study. No, I wouldn't disregard all the post-2000 ERS data, because you can pick scenes or pairs with similar kind of Doppler shift, and then you could have a disconnected network. So it's something you could try. But the question is, I mean, how long is your PhD? Can you put up a continuous GPS right in the middle of the subsurface pole?
It was suggested. But yeah, it's quite expensive to go out there and put a GPS station. But yeah, we'll see. There might not necessarily be enough slip over 4 years. So yeah, I have another 2 years of funding. But yeah, we'll see.
Oh yeah. Should we? All right, one more. Last one.
Last one?
Yes.
Well, it's a good occasion. Yeah, very nice talk. And, but you began by mentioning the Moroccan earthquake, which is a thrust fault.
Yeah.
And it's a thrust mechanism. Do you think that you would do the same job for the thrust faults in general?
Well, thrust faults, it was kind of 50-50 whether I chose to look at thrust faults or normal faults.
50-50.
Because they're both dip slip
50-50.
faults. But yeah, thrust faults tend to be a bit larger than normal faults. But other than that, we have the data available for the 30 years, so we should be able to come up with some similar ideas.
Yes, well, there are many thrust faults around the world. And the one thing to go to along with the question of the strain and stress, of course, the mechanical behavior between the thrust faults and normal faults are totally different, right?
Yeah, they probably behave quite differently, but I have focused mainly on normal.
How much time you have left for your PhD?
Look at every thrust and normal fault.
Thank you, everyone, for the great discussion. Thank you for the good talk. Our next speaker is Leo Marconato from University of Grenoble, and he's going to talk to us about Sentinel-1 time series on the North Andean Slur.
Thank you. Good afternoon, everyone. So I'm Leo Marconato, PhD student at ISTER, Université Grenoble-Alpes, and I will talk to you about part of my PhD project on the observation of North Andean sliver motion using INSAR time series analysis. So to locate a little bit the study, we are looking at the western coast of South America in Ecuador and Colombia, where the Nazca plate is subducting below the South American plate at about 5 centimeters. It's not close enough. At about 5 centimeters per year. And this subduction motion is actually oblique, as you can see on this map. And this obliquity causes the through partitioning of deformation causes the individualized motion of a block, a continental block that we call the North Andean sliver, that is in red on this map. This block is moving at about 1 centimeter per year towards northeast with respect to stable South America. So more precisely, we are here looking at the western part, the western boundary of this block that was shown to be the deformation of the block, of the western part of the block is mostly localized on the fault system called the CCPP fault system, standing for Kosanga Chingwal Payatonga Puna fault system. And that's where we are focusing in this study. Very recently, first attempt of block modeling at the scale of Northern Andes was published by Harin et al. And is proposing a geometries for several blocks within the North Andean sliver, especially, for example, this Quito Latacunga microblock that is individualized within this western boundary. So this was constrained using only GNSS data, but we thought that adding INSAR with higher spatial resolution in such an initiative could be very interesting. So that's what we tried to do. So, however, INSAR is a rather challenging technique to process in this area for several reasons. We are in a very mountainous area with strong topography and strong elevation gradients that can make the processing complex. Also, we have dense vegetation, especially in the lowlands, where it's mostly equatorial forest because it's very wet, and this vegetation can totally make impossible the processing of INSAR. Moreover, even at high altitudes, we have often cultivated lands because there is no snow, even at 4,000 meters in Ecuador. Also, we are not so far from the subduction that causes tectonic events. I will talk a little bit more about this later. And with all these issues, we are also looking at not so huge deformation rates. We expect a few millimeters per year in the line of sight of the satellite. So it's on the edge of the detection threshold of INSAR. However, using Sentinel-1 and the large archive that is available now, we could process some results. So this is the data I processed. So I used 3 tracks in this area, 2 ascending tracks and 1 descending track. And we used the full archive of Sentinel-1 since 2014, so it's about 8 years of data that represents 200 to 300 acquisitions for each track. However, we were not able to process velocity map on all this image coverage because of problems of coherence due to vegetation. You can see that on this interferometric coherence map, there is a bimodal distribution on the lowlands. The coherence is very bad due to dense vegetation, while on the Cordilleras, on the high elevations, the coherence becomes medium to sometimes very good, and then we are able to process. So the area we could really image is the intersection of this good coherence area on which we could unwrap up to 1 year interferograms. So it's about above about 2,000 elevation, 2,000 meters of elevation, and also the area where we could have two viewing geometry. So it's an area of about 100 by 400 kilometers. Regarding the processing strategy we use, so we use the NSBAS processing chain developed in Grenoble, which is an NSBAS strategy. And we took care of the proportion of long baseline interferograms that we included in our interferogram networks in order to mitigate as much as possible fading signals. Another issue that we faced is that in 2016, so in the beginning of the period of acquisition of Sentinel-1, there was a large megathrust earthquake on the coast of Ecuador, namely the Pedernales earthquake that was magnitude 7.8. And that produced, as you can see on this GNSS time series in Quito, a large seismic displacement, even very far from the coast. So in Quito, we have about 6 centimeters of displacement towards east, which is not negligible. And moreover, we have a non-negligible post-seismic deformation. So in the first, we divided this post-seismic period in two phases. So the purple one that is very non-linear, and the yellow one, the orange one, that is more or less linear at the scale of the 5 years on which we had Sentinel data. And you can see that even on this second post-seismic period, we have not, there is still a difference with the velocity before the earthquake. So we are still undergoing post-seismic deformation, even if it's roughly linear in time. So the strategy we adopted, as we have not enough Sentinel-1 acquisitions before the earthquake to derive a robust velocity, is to compute this velocity on the third period, on the yellow period, and then to correct using GNSS this velocity to retrieve the interseismic deformation. So our workflow basically was to compute interferograms using the NSBAS processing chain and ERA5 tropospheric corrections. We also optimized the weighting of pixels during multilooking using temporal coherence to overweight the stable pixels, also to avoid to mix biased pixels due to phase closure into the multilooking. From those interferograms, we computed the time series of deformation, of loss deformation. And for each pixel of this time series, we extracted a linear velocity in this orange period, so the period where the post-seismic effect of the Pedernales earthquake is mostly linear. So it's the period starting in mid-2017, so about 1 year after the earthquake. Then we referenced our velocity maps into a stable South America reference frame. To do so, we used a GNSS time series extracted on the same period as the INSAR velocity map. And then we decomposed the ascending and descending geometries into east plus vertical components after the removal of interpolated north component of GNSS reflected in loss to a straightforward decomposition. And finally, the last step is to correct the velocity map from this post-seismic effect. So we know, as we have GNSS velocity before the earthquake and after, we can make the difference and interpolate it and remove it from the INSAR velocity map to have an equivalent interseismic deformation map. So here are our results. We compare them to the prediction of the block model published by Khalin et al. This year. So here it's only for the east velocity, as it shows most of the tectonic deformation, and as the vertical is much more noisy. So we'll focus on the east velocity. On the left, it's the prediction of the block model, together with the GNSS velocity field that was used to build this model and the fault geometries that were used. And on the right, it's our results, so the velocity map for the east component with the same color scale. It's at first order, you can feel that it's about a good agreement, but to look into more details, I made a series of profiles that are perpendicular to the main faults of the area, on which we will be able to see a little bit more precisely. And so here are the profiles. So the white envelope represents the velocity of the block model. The point cloud is the INSAR data, and the dots are the GNSS velocities, so before the Pedernales earthquake. So overall, we have a good agreement. The integrated gradient over the Cordillera is well constrained by INSAR, or at least it's in agreement with the GNSS and with the block model. And even in some profiles, such as the 6, 7, 8, this one and those two, we have some gradients on main faults that are constrained by GNSS, and so that are shown in the block model that are reproduced by the INSAR velocity maps. However, in some other profiles, such as this one and this one, the 3 and the 9, we have large discrepancies that we interpret as simplifications that were made in the geometries and coupling state of the faults during the block modeling, because it was also a block model made at the scale of whole northern Andes, and because GNSS spatial density was not able to resolve these parameters either. And so we think that now, on this kind of example, INSAR will enable better resolution to improve this block model, and it's something that we'll probably work after. So to conclude, we produced the first INSAR velocity map of the Ecuador-Colombia Cordilleras using Sentinel-1 data. We developed a strategy to correct the results from the post-seismic effect of the Pedernales earthquake using GNSS time series. And the results show good consistency with GNSS velocity and with the block model. However, this block model will probably be refined by the spatial resolution brought by our velocity map. Thank you.
Thank you. We have plenty of time for questions. Who's first?
I can start, I guess, if there's no other questions. So if you go back to your comparison of this figure. So I guess around profiles 8, 9, it looks like it's more red. It's further east.
Yep.
So have you got an idea of what geological structures might be responsible in that area?
So it's about the same area as the profile 8, 9. It's more clear on the profile 9 here, where we have a strong gradient that is further east of the main structure, that is the Payatonga fault that was seen as the main structure of the area. And actually, it's also a structure that is rather important in the morphology and in the geology of the area, that is called the Peltetek fault. But that was not extensively studied because the Payatonga fault produced to be a large earthquake in 1797, I think. And so it's the main structure from what was known from paleoseismology. But the other one could be a parallel strand or something like en échelon fault that could be probably accumulating more deformation at right now, at least.
Looks like there might be an inconsistency between the INSAR and the GNSS there as well.
Yeah, indeed. What we are trying to think is that we have another inconsistency on the Quito profile. So GNSS on the profile 5 on the left fault, you can see that GNSS and the block model were predicting creep on the Quito fault system that we are not resolving at all in our velocity maps. And we start to think that maybe the assumption we made that the interseismic long-term motion and the post-seismic effect are not totally independent, and that this post-seismic strain is probably modifying the behavior of faults. That's one of the hypotheses we can do now.
Great,
Thank you. Yes, I have a question up there.
Okay, thank you. As the area that you were processing was highly decorrelated, I was wondering how effective was the use of long-term interferograms in dealing with the fading signal? I mean, were they coherent enough to provide some information to mitigate this bias or not?
Yes, the answer is that on the area that on which we process the map I show you here, the area that is shown is area where even the 1 year interferograms were unwrapped without problems, without unwrapping errors. Like the coherence is sufficient to really have all the 1 year interferograms totally unwrapped and robust. So we think that they are constraining enough the network to avoid phase bias.
So I have a related question actually. So in these mountains, presumably you have snow. Did you look into the individual dates and interrogams to see if that's causing some of your errors?
I'm not sure I understood you.
You'd have snow on these mountains,
No,
so in some
I think
periods.
you misunderstood this. So I told the opposite. We have no snow at all, except really at the top of volcano. There is no snow below 6,000 meters or something like that. So snow is not a problem in Ecuador.
Great. Any other questions? Okay. Oh, Eric, go ahead.
Did you look at any L-band data?
Yes, I have a poster about that. I tried to process ALOS-1 data before in Ecuador. And for that, we had to develop a ionospheric compensation procedure because the ionosphere was huge and very turbulent. However, given to the number of acquisitions in the ALOS archive, like about 20 acquisitions, it was not enough, even with the ionospheric correction, to derive velocity resolving 3 or 5 millimeters per year of deformation. We were able to monitor some volcanic inflation if it was several centimeters per year, but not millimetric precision.
Thank you. Any more? All right. If not, thank you very much.
Thank you.
We're going to move on to our next speaker, who is Dohua Wang from the University of Leeds. He's going to tell us about strain accumulation along the Altentag fault.
Okay. Hello everyone. My name is Dohua Wang, and I'm now a PhD student in University of Leeds. And today I'm very happy to share the information about the strain accumulation along the Central Eastern Altentag fault. Yeah, thanks to the second presenter, we know that what happened along the Central Western Altentag fault. Now let's talk about Central Eastern Altentag fault. So. So we know that there are some large-scale structural faults in the Earth's crust, and these faults are responsible for a significant portion of the world's earthquakes. And the well-known examples for such faults include the San Andreas in California, and also the North Anatolia fault in Turkey. But today, let's talk about the Altentag fault, which is also well-known structural fault working as a boundary between the Tarim Basin and the Tibetan Plateau. Previous INSA research have achieved some results based on the data from ERS, MSI, and Sentinel-1. But most of these results are focused on relatively small areas. So leaving the question about how the strain accumulated along the fault unresolved. So we processed the data covering the whole Central Eastern Altentag fault. And we, besides revealing the strain accumulation along the fault, we also, we processed the data and we we generated a 3D velocity map with high spatial resolution cover this area, and we will also use this velocity field to generate strain rate maps. So besides revealing the strain accumulation along this fault, our results also have other applications. For example, we can use this to localize the shear zone location, localize the shear zone, and we can use this to help us understand the deformation pattern around the active fault bands. And we can also use this to evaluate seismic risk and understand regional mountain building. So we know that to get a better velocity field, we must have better data. So we collected the GPS data from 1998 to 2021 from the CMONOC project, and we processed the data and we obtained the 78 3D GPS velocities. So these velocities are brand new and haven't been published. And compared to previous velocities, our velocities are 3D. It's unique. And also, compared to previous velocities, our velocity will have a lower uncertainty because we have a larger time span. And also, we include 17 published regional GPS velocities because we can't get this velocity. So we use this to let our velocity be better constrained. So we processed and acquired our data based on the Comet-Lix Sentinel-1 portal. So this is a frame-based automatic INSAR processing system, and all the information in this portal is produced using the LIXA processor, and all the products are multi-locate to a resolution about 100 meters. So and we use geckos to correct the atmospheric related noises, and also we use XPath to do time series analysis. And more details about this can be found in the website. So in this research, we include 7 ascending track and 6 descending track, and we totally processed 20 frames. And for each frame, we used nearly 180 epochs between October 2014 to July 2022. So we know that normally LIXA generate interferograms between epochs and 4 consecutive epochs, both forward and upward by default. But in this research, we choose to use a very densified network combining a normal LIXA network with 1 year to 7 year long temporal summer to summer baseline. So this will help us to reduce the potential phase biases related to relatively shorter temporal baseline. And we also want to use this to reduce the impact of the snow cover in winter, because we want to know the signal on the mountain top. We need to understand the mountain growth. And finally, this kind of network is compatible with our aggressive notify strategy. So this table shows the statistics of all the ascending frames. So you can see that we use about 2,000 differograms in each frame. So it means that totally we processed about 35,000 differograms in this project. So let's talk about unwrapping errors, because this is very annoying. So normally in LIXBus, we use the loop closure phase of 3 images to identify the unwrapping error. So it means that if the loop closure phase is near 0, it means that there's no unwrapping error. But if it is integer multiples of 2 pi, it means that there are some unwrapping errors. So normally in XBus, we just abandon the whole interferogram based on the RMS of the loop phase images. But this will generate some problems. For example, we will abandon a lot of interferograms and generate some gaps in the network. And also, the abandoned interferogram will have some good data. And also, the kept interferogram is not perfect, still have some unwrapping errors. So we want to solve this time once for all. So we use another method. So we just abandon all the pixels in the interferograms that are related to unclosed loops. It means that we only keep the perfect interferogram in the time series. for each pixel. So what is perfect interferogram? It means that all the loops related to this interferogram should have a loop closure phase of 0. So based on this method, we can see that before this method, we have a lot of unclosed loops in the frame. But after this, all these unclosed loops are be 0. We don't have this problem. So we have escaped all the unwrapping errors. We keep more interferograms. We have better coverage. Also, we have a lower uncertainty in the final velocities. So this is our workflow. So we use Lixar generate interferograms, and then we use Lixbus combined with geckos and plane motion correction to generate line of sight velocities. But we know that this line of sight velocities are independently referenced. So we use VLMAP to do the velocity field inversion. And in this inversion, we try to remove the order reference frame adjustment ramp. And also we try to remove linear with height atmosphere noisy. So after this, we will go to reference line of sight velocities. And we know that if we want to do the decomposition, this equation is unsolvable because we have 3 unknowns. So we use the north to south velocity field model from VLMAP to constrain the north to south velocities and got our east velocity and the vertical velocity. So this is our 3D velocity models. And we compare this with GPS state, and it shows that the average of the difference is about 0. And the standard deviation of the difference is about 0.7. It's very low compared to the uncertainty of the GPS state itself. And this is our final ascending and descending date velocities. And this is our east velocity. So from this velocity, we can see this left lateral motion along the fold very well. And we can also see that how this left lateral motion diminishes at the east end of the fold. And this is our vertical velocities. So we can observe some short wavelength noise substance related to permafrost, but we can also see some long wavelength uplift related to tectonic motion. For example, the uplift in the Arton Sound range, and also the uplift inside the Chilean Langsang thrust belt. Yeah, when we zoom in this velocity field, if we use some profiles across the major restraining bands, we can see that all these bands are uplifting, except some short wavelength substance related to permafrost or landslide, suggesting that there's a very high compression and causing regional uplifting around this band. And also we can see that there's a higher uplift at the inside corner of the band. All this shows that there's a higher uplift inside the inside corner of the band. So this is consistent with previous research, which showed that the strongest shortening should happen within the inside corner of the band. So if we not believe that this is tectonic motion, we can also use some finite element modeling to show that. So if you build a finite element modeling, we will show that we can observe some uplift at the inside corner. So it means that this is due to tectonic motion. Let's talk about strain rate. So we calculate all strain rate maps using the gradient. And this is the maximum shell and dilatation. So from this maximum shell, we can observe the shell are just located on the Auditorium fold. And we can see some relatively high shell rate around the restraining band, the biggest restraining band. And we can also see how this shell strain become absent at the east part of the fold. And also, we can look at the dilatation. We can see there is a very high compression inside the quantum basin. We can also see some short wavelength compression inside the Chilean Langsang thrust belt. And this compression just located at the fold, some fold. So it reflects the shortening on the fold. So we can also look at the secondary variant. We can see that most of the high strand rate are just located at fold. So we can use this to localize the shear zone. And we can also use this to estimate the dipping angle of the fold. And yeah, you can also, this is not very linear. So you can see some places near the fold also have a very high strand rate. It will reflect the width of the shear zone because of the branches that parallel to the main fold. Some branches parallel to the main fold will cause the width of the fold is changing. Also, let's look at the beautiful map. If we zoom in this area, we will find a very beautiful strand partitioning at this area. So this has not been well revealed in previous research, but in this strand rate map, we can see that how the strand partitioned along other fold. We can see most of the strand rate accumulated along the Danghe Nanshan fold, and also accumulated along the Yama River Dashueshan fold, and a very little strand rate accumulated along the North Altai fold. So that's very important because in previous GPS research, we cannot identify that. For example, if we use there's a profile A across this area, which we think that have strong strand partitioning, they will got a slip rate for this area. But the problem is that now the story is different. If we use GPS, we cannot identify that. So we are thinking that all the strand accumulated on the North Altai fold. So you calculate slip rate, and we will get a very high slip rate, about 3.8. Now, but also, even we know that there's another fold, the GPS can also do that because it cannot calculate the slip rate because there are two spots. So with the INSAR, we have the chance to calculate slip rate on these two folds separately using some profiles across these two folds. And we can use some Bayesian inversion to calculate slip rate. So we can get that slip rate on the North Altai fold is about 0.9, and slip rate on the Yama River fold is about 2.4. So, and yeah, you can also look at the profiles. Yeah, this kind of destructive motion actually exists. So, is there any other research to prove our result? Yes, we have. So this is a result published in 2015. It shows that the slip rate on the Yama River Dashueshan fold is about 2.8 millimeter per year since the last Pleistocene. So this 2.8 millimeter per year, okay, is very consistent to our 2.4 millimeter per year. So it means that this strand partition is happening, and we have consistent result. So this we can do the Bayesian inversion for all of profiles along the fold, and we can show that the spatial variation of the slip rate, locking depth, location of shear zone, and also for specific polygon profiles, we can also estimate the creeping rate. Yeah. So there are some conclusions. So we think that a pixel-based aggressive notifier method can use to remove the unwrapping error. And we have a 3D velocity map, and we can use this to reveal the spatial variation of strand accumulation and mountain growth. Yeah, we think that there are some important strand partition happening along the central eastern Altai fold and should be carefully considered. But that is not the whole story. Now, let's compare this with all other researches. And we see that the red diamond is our interpretation, and the other previous result, our result, and the pattern of our result will be shaded using some color. And we will see where the slip rate decreases, where have the slip partitioning, and where have some slip transfer. But yeah, we do have more details to show, and I'm welcome to have more discussion. Yeah, that's I think that's all.
We have time for some quick questions. Yes.
Fascinating talk, and thank you for showing such incredible data sets. I'm wondering whether if there have been any historical earthquakes on this fault and your variation in the strain rates along it, if there's any spatial relationship between the two?
Shift to the what?
To historical earthquakes along the fault.
Old earthquakes, no. Since the last 100 years, there is only a very big earthquake happened. Yeah, we can show that in the first figure. Yeah.
Thank you.
Can see that there's only one strongest earthquake with a magnitude about 7.5 happened along the near the Yama fault, the Chama fault, sorry, and the other earthquakes are not too strong. And we can see more earthquake happen near the Australian band, and yeah, not very big earthquakes.
Thank you. We have time for one more. This is the last question. No pressure. Anyone? Okay. Here you go.
Curious, following some of the other talks earlier, they're also looking in similar areas and further along. Have you seen any of the east-west slope correlated signals in the horizontal on either side of the fault in your area?
You mean some east, west to east? I'm not follow that.
So have you seen any signals which are, say, I think eastward motion on the east side of slopes, westward motion on west-facing slopes, as we've seen in some of the other presentations today?
I haven't catch that signal in this research.
Thank you.
All right. Thank you very much, everyone. Thank you to all the speakers and all the discussion.
Thank you.
I just want to say that we're going to give this room up for a roundtable related to the displacement and deformation sessions, but our roundtable is going to be tomorrow after the other two tectonics and earthquake sessions. And we have plenty of discussion questions for you that we're curious to hear about. So please come.
So I guess thank you to everyone who's stayed for the displacement roundtable. We do have some seed questions to discuss. We have 4 chairs and 2 seats. So I guess we could share microphones.
Plus the audience is going to do the talking, right?
Yes, absolutely. We're hoping that you guys are going to do most of the talking. We've tried to come up with some questions that encompass the various themes that came up in both of the sessions on displacements and deformations. It was quite a disparate group of talks on quite a lot of different things, but hopefully we can pull out some common themes and some recommendations to feed back to ISA. So the first question that we had was, which recommendations does our community give to ISA in this domain? So what targeted R&D activities in the short, the medium term, what do we need, what can we do in preparation for biomass, Roselle, Harmony, Sentinel-1 next generation to support the future of what we're trying to do?
That's your cue.
If I can kick off the discussion, in some of your presentations, there were already some clear recommendations. So for example, the observation continuity. So talking about Roselle, Harmony, Sentinel-1, NG, I guess we are already talking about the future programs that should ensure the continuity, which was anyway one of the key objectives achieved with Sentinel-1 compared to ERS-1, 2, and MVSAT. So that's certainly one point that emerged from several of the presentations.
Yeah, I fully agree. That's definitely important for the Sentinel next generation. So to have continuity, not just the same frequency, but it's like the same orbits and compatible data, that time series can be continued. With the other missions, it's a little bit more open. I mean, you can try things with Harmony, and it has first to be tried and developed, and then really how to make best use of it will be possible to decide. So maybe more flexibility is important on the agency side. And with the L-band, there is already quite a lot of experience, and then with NISAR there will be much more experience probably before the launch of Roselle. And so there it's a little bit a question if it should just be another mission, or if it should split the responsibility between the different missions. So there may be even considering not just decisions by one agency, but by the JAXA, NASA, and ESA would be helpful if best use of the great times with a lot of L-band data could be made. So maybe something along this line, like coordination between the agencies for the L-band operations might be something we could state.
Maybe following up on that, Urs, you had some recommendations today, and you showed some very interesting work using L-band. Next year, our friends across the ocean are going to be launching NISAR. This is a perfect opportunity to, of course, experiment with L-band before Roselle. Can you think of any particular way that ESA can support us in that?
So I think one of the very important aspects is the availability of the data, and I think that should be great if it's what is promised. And then to have somehow good
data, which means for these applications time series, and that should also be guaranteed without intervention. So maybe what may be helpful is some budgets for some groups, for some research, but I'm pretty positive that even without this will be done. So I think it's a quite good situation, but maybe to direct a little bit some questions. I don't know, it may still be helpful to have some possibilities.
I would recommend to do more research on ionospheric corrections if you're going to be dealing with L-band data. This is very important. I'm not sure whether Roselle is going to have the extra band that NISAR is going to have to better do the ionospheric corrections with the split spectrum method. But that's something that you should be looking into if you're going to be using L-band data.
Just to answer, so I'm involved, I'm not ESA, but I'm involved in the development of the GP ROM prototype processor. I know they are foreseeing also this dual band, so dual chip transmission. They're just using the full 85 megahertz. Not necessarily for all subswords, but for all of them. So in the others, they will use a larger bandwidth, which will give enough sensitivity then for ionosphere. And I heard from the presentation this morning that an ITT will be issued about ionosphere in the frame of Roselle this year. So I confirm the first 2 points.
Okay, so perhaps we can move on to the next question then, and that's... Yep, good point. Does anybody have anything to add about
Maybe
biomass?
I can say something. So somehow politically it is more correct at the present to sell missions as targeted, so there will be this global biomass map and so on with this accuracy. And I'm missing a lot the aspect it's just a new frequency, and so we can do a lot of nice tests and developments of algorithms for different applications, the ones that have been named, but also the ones that have not been named may be interesting. So there, I'm sure there will be good access to the data, but maybe to have the possibility to propose some small studies to investigate something would be fruitful, and also to somehow on ESA side collect the ideas or collect, like having a workshop. Things like this could be very beneficial to accelerate a little bit the understanding of what can be done, and different groups can motivate each other in showing results over one surface versus another one.
Any more comments on biomass or anything else we may have missed on that first point before we move on? Okay, so I guess the second question is, for people who were in the first session, I touched on it a bit in my talk, but what requirements are there for the smaller scale applications? So things like small scale infrastructure, mining, places where elevation changes very quickly through time, but much down at the small scale. And how do those use cases compare to the big earth and environmental applications where we're looking at continent scale, global scale, country scale? What are our different use requirements if we're looking at building scale or site scale things?
Well, maybe one of the reasons of this question was that maybe the community of geologists interested in large-scale phenomena is dominates a little bit. So we would like to ask if there is any way to accommodate the two types of requirements for the two types of communities.
And also, I believe, based on what we have seen today, that a way to accommodate these different needs is also working with contributing missions. Because if we talk about small-scale infrastructure, building stability assessment, for example, Sentinel-1, we all know does not perform as other types of SAR missions in terms, for example, of height estimation of the position of the persistent scatters, for example. So I believe that the accommodation could come, of course, if we continue investing in the complementarity between Sentinel-1 and all the contributing missions, and also we have seen today that the newly coming contributing missions like ISI is also providing further add-on to the current capabilities. So let's continue along this route.
Okay, this is a very quiet crowd. So let's move on to the third question. In situ instrumentation, ground-based radar, auxiliary data. What can we gain from these? How can we use them in our studies with satellite data? Just a general question out to the audience. Any suggestions? Anything we need more in terms of support for ground-based systems? Anybody in the room besides Urs who uses ground-based radar?
I think it's very complementary. So it's somehow the answer is already in the question. So it's important in the sense that it is very complementary. So with the satellite data, for example, for landslides, you get an overview over active cases. But if it gets dangerous, you want to have a more immediate access to the information. And so you put maybe an alarm system with where ground-based radar can be an element, but there are other elements, cameras and traffic light that blocks the road if the rock starts falling down, because there's half a minute time until it reaches, and that may be enough. So it's different responsibilities for the two things in this case, and so I think it's really nicely complementary and not in competition with each other so much. But there is overlap, so one can be used maybe to optimize the other one, or to validate some information, or to get different components of a motion over a landslide or a mine or so. So there's many possibilities, and both should be definitely done, and it's really complementary.
So maybe we can say, continuing what we said before, that maybe Sentinel, very large scale, then contributing X-band missions go to smaller scales, and ground-based measurements, even smaller, even more detailed. So there is this kind of complementarity. Yeah.
I don't see it as a scale thing. Also, I mean, to
Not
look
only
at
as a
more
scale,
detail,
yes.
you saw L-band results and you look at details. So you don't necessarily need the high resolution sensor, but maybe you need it. So it's again complementary, but it's not that one resolution is only supported by the spaceborne. It goes, even the Sentinel type resolution goes quite in a detailed scale.
Yeah. Also, not only the space resolution, there is also the temporal temporal sampling.
An archive is another important aspect, which is more difficult with the high resolution, with the private run missions. You don't have these nice archives typically. So there maybe they can learn a little bit from Cosmo or TerraSAR, who do a little bit of archive, or who do, I mean, a lot of archive, but it's still difficult to have good archives ready if there's a process starting to become dangerous or important.
I think that what you said also is very important. Of course, we are all aware that the complementarity sometimes is hampered by the fact that ground-based systems are certainly not accessible as satellite data are. So probably this question about complementarity should also bring us to discuss how to, if there's a way that ESA can help with that, how to increase the accessibility of these facilities, because otherwise they would be confined to small case studies rather than a more common approach.
In addition to ground-based INSAR, are you including ground-based corner reflectors as part of this question?
By all means.
Yes.
By all
Yeah,
means.
so that's a whole, we had several talks about how to use the corner reflectors to better determine where things are. So I think that's clearly part of this. I thought that was part of this question, but it wasn't clear.
Yeah, just to be clear on that, by ancillary information, we basically mean anything else that we would want to use with it, whether or not it's ground-based or other satellite systems, anything.
Yeah, and probably this morning we saw also one talk specifying how, based on empirical data, how to better plan and task how to position corner reflectors, because it's pretty well established across the community how to design this component on the ground, but probably we are still far away from common guidelines, basically because there are only few groups using corner reflectors. It's not yet probably something that is shared across the community. So another recommendation could be, for example, investing on projects that favor validation using corner reflectors and at the same time defining guidelines.
So jumping back to the second question a bit there, and sort of speaking a bit further to the resolution question, the ground-based radar, really the demand for, in the small-scale infrastructure, the demand is always going to be resolution, which is not really something that the big global missions can do. So we need to be asking almost a slightly different question of sort of, are there things that we can do with existing large-scale mission to optimize it so that we can use it in edge cases for small-scale infrastructure? And there it's looking for things like data availability, data subsetting, being able to just pull out little pieces of the data rather than downloading the entire data set. As you said, baselines, some diversity in baseline at some point during the mission.
and I'm sure there are other things like that out there. But if we just ask what do we need for small scale infrastructure, the answer is always going to be resolution to start with. But that's not really the domain of these global missions that EAST is launching.
You bring up a good point about being able to pull out smaller amounts of data, because of course right now if you want to process a small area you have to pull out an entire frames with 27 bursts and so on. Even going down to a burst level would make things much easier if you had a burst size products. But of course data cubes would be nice. And what about moving towards what is planned for NISAR, which is these geocoded SLCs? Would that make life easier for people here? That's controversial, but there are some advantages in terms of ability then to access smaller.
Usually in these smaller scale environments, the elevation models aren't good enough, as Rachel was saying earlier. The geocoded SLCs aren't going to perform as well. So that's kind of the worst of both worlds, really.
Right. But at least access to burst level would be proper.
Absolutely. And that's not going to happen with the Sentinel missions, but we should be planning for things like that with the future missions.
Well, and we also saw a very good, interesting presentation earlier this week from Descartes Labs, where they have basically indexed a global index of all the SLCs, and they themselves are able to reach in and just grab the bits they want simply by indexing it. That could be perhaps something that was supported by ESA.
Providing that data retrospectively for the Sentinel archive would be very useful.
I think we should move to the next slide. So the fourth question is, what are the main issues for making INSAR more operational and respond to user needs? For example, is more important revisit time, spatial resolution, or other features?
If I speak with our surveying authorities, which have the intention to set up some monitoring system in Baden-Württemberg, then they ask, will be data available in the long future? So I think it's clear that we all want this, but I wanted to state it explicitly.
For disaster response, it's revisit time is the key, and latency of processing. So that's especially a problem now that we only have Sentinel 1A.
Yeah, I think not only for disaster response, I mean, for monitoring any kind of motion, revisit time is really probably, I mean, resolution is good enough already. Also including the other missions, the X-band missions. So revisit time with the same angle, so interferometric revisit time is the issue.
Yes, which could be achieved either in constellation mode or with the flexibility and agility of the same mission. Because if we talk about global scale missions, of course, the observation scenario is mostly fixed. So it's just a matter of having more satellites working together in a constellation rather than for missions that are designed, again, as constellations, but to work in a flexible way. So here, probably, we have two main routes to achieve the revisit time, which I do agree with Mario. It's pretty crucial in most of the deformation and displacement type of applications.
I think considering also the private or national initiatives, just stating that short enough baselines is relevant, is important. We have plenty of examples of the newer satellites where this is not assured, and so you cannot use it. And that makes a big difference, so of course. So you have maybe nice parameters concerning the resolution and so on, but you cannot serve the user needs if it's not baseline suited for interferometry with ground motion information.
I would also, I think, confirm what came out of previous fringes, that if you're looking for something that's operational, then the routine and the boring, making things as boring and regular as possible is probably the way to go. I don't think that's changed.
Well, if, I don't know, if there are no other point on this, there is the question number 5, which is very different from the other questions. It's about if we think that it's important to invest in post-processing to extract information like warnings and alarms about stability of infrastructure, landslides, whatever it is. I mean, to bring this information in a way that is more easily accessible by end users, or which I think is the case, or if on the contrary, we are okay with providing measurements.
Yeah, so I'm thinking also about false positives in this sense, because we've seen a talk earlier today about DEMs and the relevance of them being up to date. And let's say you raise a tailings dam, you might show in your INSAR results that there's something going on here, even though, well, there is something going on, but it's planned and it's okay, right? Like, it's been raised, something has been happening, and your dam might not be up to date. And so your INSAR results might show that, well, there's something to be concerned about, right? So you might raise an alarm or a warning, even though if you then talk to the people on site, you will find out that actually there's nothing to be worried about. So while it is a nice goal to strive for, I think it's tricky to do this without like talking to the people involved in the assets that are being monitored for these alarms.
Yeah, in fact, I think this is an extremely difficult task. So, and in fact, related to this is the other question, because I think it's very hard to pass from measurements to warnings, or so. This would require really a lot of research and effort and fundings from agencies like ESA. We are far away from this, I think. But I don't know what is.
Yeah. And also we need to engage with users because, for example, in Italy we have made several projects at national level to basically identify thresholds that are relevant to the users instead of defining top-down thresholds based on purely a scientific approach. Because in the end, you warn someone about something. So the main actor should be the someone you are going to warn, and that would be the clear point in my opinion. So investing in this aspect means also creating a way to engage with final users. And in this way, I guess, we can also solve the issue of false positives, because sometimes we just look at the data, see changes that are actually unrelated to the type, for example, of structural behavior of the object that is managed by the users. So I guess it's also an aspect of engaging users in the full process, so training them in understanding what we could provide, but basically they should be the designer of the warning system rather than just passive user of it.
Just quick question, who are those users you're talking about?
Sorry?
Who are those users you're talking about?
For example, in the cases that I was mentioning, where institutions, for example, those managing historical buildings in city centers, so they wanted just to know if satellite data could help them to prioritize restoration interventions. And sometimes what INSAR shows is just the normal behavior of the structure, especially if it's an ancient one. And so defining a threshold, for example, just converting the experience gained, for example, with modern architecture does not suit at all the purpose. Other type of users, for example, are ministries in charge of managing through their regional authorities infrastructure. We saw several case studies in the presentations with regard to motorways. Again, that's the type of user we are targeting, and in particular the technicians and the technical offices that are by statutory rules in charge of making monitoring and surveillance routinely of all these infrastructure, and satellite data could be one of the layers, the informative layers that they should use to come up with a reporting stating whether then the infrastructure needs further investigation or not. So these are the main users that we have interacted with.
And this aspect is related also with the success and the diffusion, the spreading of this technology, because you know, if we want that this technology become really used by many people, we need to make a step to make this information useful for the users, the final users that don't care about satellite interferometry. They don't even know what interferometry means. They want to know if a structure, an infrastructure, or a landslide gives some concern or not. And if we are able to make this step, the INSAR will become a powerful and very much used instrument, like GNSS is now. Otherwise, we remain confined in a small community.
I'm wondering whether this is, are you including EGMS as you're talking about post-processing of the EGMS data in this question, or is this post-processing of the basic Sentinel data? I wasn't clear what this question was about.
I don't know. I think also EGMS, but any kind of INSAR measurements. EGMS provide millimetric measurements, but who is going to look at all these millions or billions of measurements? No one. So if we could extract from this data some information for the end users, this is extremely difficult. But this will be, it is necessary to do this if we want that the decision makers, the governments, continue to put money in these satellites, because if it's only for the scientific community, at a certain point they will say, we put even too much money on this.
Mario, I disagree to some degree. I don't see it as our responsibility or as our task to go further steps, but we provide deformation information and quality for this information on this product. I see it more, Daniele mentioned in the same direction. So the user has to take this information as one of the several information sources, and it takes time that he trusts the information. So he needs cases he knows, and he sees that the cracks in the houses are where you see the gradients in the displacement. And so he starts to use it. But I don't think we should try to take over this role as well. Maybe very few are maybe in this other community, but most of us are more understanding interferometry to the level of the displacement map and quality of this information. And often I think it's good if you keep it this way. So in the landslide work in Switzerland, we don't try to provide the interpretation. Even so, we have geologists working with us, and they know the language. They have seen so many cases, so they can actually contribute a lot, but it has to be the Geoinformation Office or the natural hazard section of a province and so on who uses it. And it took 20 years. Now it's happening a lot. So suddenly it is really a very good situation, and they all want to solve questions with interferometry.
I agree, and also no one wants to take the responsibility of giving information that is difficult to give, and also this step must be done. I agree with you. We cannot do, the interferometric community cannot do this step alone. We need also the contribution from the geologists, the engineers, who are more in the
I mean, I agree this step has to be done, but they have to feel they did it. Otherwise,
but I think we have to contribute, because we are the one that.
But they have to have the feeling they have made this step. That's my feeling from Switzerland.
Just to rebound off what you said, I think we should resist to compare INSAR and GPS or GNSS. I mean, that's and we will never achieve with INSAR what the market of GPS did, because we, as a scientist, we use GPS to look at the Earth deformation, but that's real byproduct of what GNSS is. I mean, GNSS has been developed to localize the Earth surface on Earth, and that's something that everybody can understand, and everybody wants to know where they go and where they are. And with INSAR, we don't look at that. And that's why GPS has such a big market, because it gives this information. And as INSAR, we never provide something that's such interesting, so I don't think we should look for like having a growing market for end-up users. And the users that can be interested by our data are, as you said, like institutions for like monitoring for that infrastructure and public infrastructure. And the second big users are insurance company, but that private business, and basically we are giving away some like public money to private interest. And to me, it's like kind of problematic, because with our data, that can impact the owners of a house and all, and I don't know, I think it kind of a touchy subject, and yeah, I don't feel very comfortable with that. That open, like with public money, we open the full data, and it serves some like private interest in it. A lot of repercussion on like people actually.
No, just to complement. So if I'm before the break, we had a presentation where they are already working on these EGMS to produce this warning for buildings. So I mean, it's already going in this direction. So it's a post-processing, and they stated that this will be integrated in the chain. So this is already going in this direction. So the other question is, okay, this is 7 in this geohazards exploitation platform. As far as I know, they just produce interferograms. The question is if they want to produce more things. But anyway, the EGMS already is going in this direction. I understood right.
Just to clarify, is a geohazards exploration platforms also produce more than interferograms, so you can also access some tools to achieve PSI rather than SBAS. So just to make you aware of this.
So current.
This is the absolute last question. We're over time, and they want to close it.
Yeah. So currently in several German states, there are established organizational units which try to exploit INSAR data for their purposes. And I think there is still a need to help, maybe I should repeat it. So in Germany, there are currently several states establishing organizational units at the surveying authorities which want to exploit INSAR data. And there is still some gap how to exploit them in a useful way and to define products. And as has been said here before, to define products, there is needed the knowledge of geologists, engineers, and those people who do the practical surveying work at, let's say, bridges or roads. And I think it would be helpful if there would be funding for projects where INSAR experts and such stakeholders would work together to define products.
Thank you. Just one last comment then?
Yes, well, I'm an end user, okay? I'm a geologist working on tectonics, and I'm very interested by the way you process the data and everything. Just recently, there was a paper in Science done by 2 of my colleagues. I'm working in France, and it's about the GNSS. And they say that they have a signal, a pre-earthquake signal. So it's kind of a warning. And so it's in Science. So I don't agree with the comment that we should just restrain and just go just on the calculating displacement and period. I don't think this will be useful. And it's like you asked me also to just do my work, and then I'm not interested by what INSAR is. I am interested by INSAR. I even teach INSAR, so it's but I'm not a specialist. And then I think the two communities needs to mix together and prepare projects together even. I don't agree at all to this frontier or boundary between on one hand INSAR and on the other hand the end users. Thank you.
Thank you very much, and thank you everybody for contributing, and we'll see you tomorrow.
Thank you. Bye-bye.